just curious. Okay. Okay, this is working. Hello, everybody. All right. Okay, I think we're going to kick off. Henrik, are you all ready? Yeah. All right. Welcome. You are now at the ZK Summit 8. I want to ask a question. Who stayed up all night to wait for the merge? One person. Okay, the different crowds. Wrong question. Okay, who has been to a previous ZK Summit? Okay, this is the right question. There's a lot of people who've done that. Okay, cool. I do want to somehow find a reason for you to clap. So who was at ZK Summit 1? Clap. No one. Okay, wait, ZK Summit 1. Yeah, you were there. Okay, who is at ZK Summit 4? Clap. Okay. Who watched ZK Summit 6 online? Yeah, okay. Who was at ZK Summit 7? Okay. So this is a new crowd. This is good to hear. All right, we are at ZK Summit 8. It's kind of wild that we're here. The event started, so I do this biannually. It's not that it's been running for 8 years, although that would have been cool. It's brought to you by the Zero Knowledge Podcast, and I always use this time as people are arriving to share a little bit more about the history of the podcast and the general ZK community, because it's booming. So, in case you don't know, the podcast actually started October 2017, which is 5 years ago. It's kind of crazy. But at the time, it was sort of an experiment. By January 2018, we started to do it weekly. The first ZK Summit was March 2018. And I'm going to tell you a little bit about ZK Validator and ZK Hack. These are different organizations, but all related around the ZK community. So the ZK Validator launched in 2019. And the ZK Hack, which is an event series, happened in October 2021 and March 2022. And then this summer, we launched something called the ZK Whiteboard Sessions, which is an educational video series. So let's talk about the podcast first. There are 248 episodes and counting. So we're almost at 250. I think I have to do something special. I don't know what yet, but here's some of our top episodes. Howard, yours is still ranking. So Introduction to ZK SNARKs. I think that's the earliest one on this list that's still kind of one of our top episodes. And yeah, it changes every time I do it. The Distilling DeFi Primitives with Guillermo popped up this time around. But yeah, it's really cool. So I mentioned ZK Validator. ZK Validator is a validator. It runs validators on L1s. We're on 10, actually L1s and collators. We're on 10 networks currently, as well as on a number of test nets. And the reason I'm telling you this is the ZK Validator has a number of initiatives that might be interesting. So for example, right now we're doing the ZK Tech side round, where we have 45K in matching funding. So I don't know if you've ever donated on Gitcoin, but you can make small donations and they're matched through the matching funds. Our partners on this are 0x Park, Risk Zero, and Scroll. And if this is actually live now, it runs for like a 2-week period. I think it's still running until next week. So if you want to donate to early stage ZK Tech or tools, this is a really cool thing to check out. It's on the Gitcoin site, grants, you'll see ZK Tech. And because of what happened about a month ago with the OFAC sanctions against Tornado Cash, so this is the ZK Legal Working Group. We started this a year ago, but it was very small and there wasn't that much energy behind it. But with what happened, we decided to really reboot it. And so this is much more active now. If you are interested in potentially participating, this is a group of people in the industry who want to understand what the problems are, challenges, can kind of work to talk to regulators, work to understand what's going on there, and help push ZK forward. Yeah, just wanted to let you know about it. Oh yeah, also one last thing about ZKV, there's some of my colleagues and co-founders in the audience, so it's nice to see you here. Yeah, ZK Hack. So this is another project. I'm actually wearing this shirt, and I matched my hair to. Anyway, I wanted to. So ZK Hack is it's sort of the learning hub for ZK Tech. It follows very much with like this event, actually. It started as an event series, like a multi-week event series with a CTF hacking in between. So we were like doing ZK puzzles. We did one in the fall of last year. We did one in the spring. We have another one coming in November, so look out for that. And we also, as part of ZK Hack, have a really active Discord, and we started what I mentioned before, this ZK whiteboard sessions. If you haven't heard about it, please do check these out. These are educational videos. The first 3 are with Dan Bonnet. The rest are with the Polygon team doing interviews around a whiteboard with some of the experts in the space. This is meant to help you understand the fundamentals of ZK. This is meant to onboard you. I know a lot of the content here today is going to be quite advanced, but this is a great way to understand what people are talking about. And this is the Discord, and I think that works. And if you're not already in it, do join it. We have study clubs there. We're really trying to build this up as like the hub for learning and sharing information about ZK Tech. So I'll leave it just for a second. Yes, last thing. Okay, there's a jobs board. If you aren't aware, if you're looking to work in ZK, this is a really great place to check it out, to find your next role, basically. We have top teams posting jobs focused on ZK Tech. All of it is on our Twitter account, ZeroKnowledge.fm, or ZeroKnowledge.fm rather, and there's a link tree there with even more links to things that we do. Cool. Okay, so so I think people have now arrived, so I'm gonna talk a little bit more about the program and what we have for today at ZK8. There are 3 stages. You're on the main stage here. There's a side stage downstairs, kind of across from where you walked in. And there's a breakout room off of the sponsor area, which is kind of like a club. It's pretty cool. These posters should be around the venue, and you can also find the schedule on zksummit.com. I know this is very small, so it might be better to take a photo of the actual programs that are hung around. This is the Wi-Fi. Oh, yes, it's corrected. Okay, small s on Summit there. I think there should be signs as well. If not, maybe you want to take a quick picture. This is the Discord again, ZK Hack. As I mentioned, there's main stage, side stage, breakout. There's the sponsors lounge. There is a cafe that's downstairs, and it will open, and you can buy things there. But that's not part of the event. So you would have to pay there. We will have snacks and lunch and all sorts of things here for you, and in the sponsor area. Cool. Okay, so now I want to say a big thank you to the people who made this possible. We have a fantastic batch of sponsors. We have our platinum sponsors, Alio, Anoma, and Polkadot, or Web3 Foundation, and you're going to hear from them shortly. We have our gold sponsors, Polygon, ZK Sync, and Risk0. And actually, all 6 of them, you'll see they have booths downstairs, and you can actually go meet the teams. I know a lot of them are hiring, so really good to chat with them there. I want to say thank you to the silver sponsors, Entropy, Geometry, Gnosis Chain, Jump, Manta Network, Polychain, Sysmo, Scroll, and 1KX, as well as our community sponsors, Aztec, Ethereal Ventures, Espresso Systems, Ethereum Foundation, Least Authority, Panther, Sunscreen, and Trapdoor Tech. There's a few new ones, so I want to say a big thank you to everyone who's come on board this time around. We will have a break in the afternoon that's sponsored by Ethereal Ventures. We will also have a drink sponsor at the end of the day, Least Authority, and I know they have some special gifts for us I'm very excited to see. Yesterday we had a speaker dinner. This was sponsored by ZK Sync and 1KX, and I do want to just do a shout out to 1KX. The first ZK Summit was sponsored by one sponsor, and it was them. And so thank you, 1KX, for allowing this to happen. And thanks for coming back on board this time. The team is, and I shouldn't even have myself on here because I did less on this event than I usually do. So Agnieszka, I don't know if you're in the room. Agnieszka really led this effort. Thank you so much for doing this. Cheers. Tanya worked with our sponsors. Thank you, Tanya. Rachel has been fantastic. I don't know if, are you in here? Yes, there you are. Okay, thank you, Rachel. And Henriks, the podcast editor, you hear me thank him kind of every week, and he's actually back there too, helping with the live stream. So thank you to the team who put this together. Yeah, we also have some great co-hosts on the side stages. So we have Alex and Luke downstairs. We have Ari in the breakout, and Guillermo's going to help me here. All right. How am I doing on time? Am I super late? I'm okay? Okay, so every time I do the ZK Summit, I ask a question, and I do this on the application form. And I will tell you a little secret. I do read those. Like, it matters. When you apply, if you have a good answer here, you're more likely to get a spot. So Okay, so the question was, how would you explain the vanishing polynomial to a friend? And we had some great answers. Now I'm gonna have to read a lot of like math stuff, so give me a second. Okay. Explain like I only remember middle school math level. Think of it as a curve on an y graph that is 0, intercepts at the x-axis when you plug in certain points. It's like playing whack-a-mole and hitting all the moles at once. I would ask aforementioned friend to kindly refer to the Zero Knowledge podcast episode with Mary Mahler. We talked about this in that. The vanishing polynomial is a way to specify a polynomial by telling you not what its coefficients are, but rather which points it gets to the value 0. For example, instead of telling you my polynomial is x squared minus 3x plus 2, I tell you my polynomial vanishes at the points 1 and 2. This means the polynomial is x minus 1 times x minus 2, which is x squared minus 3x plus 2. This is a very good answer. How would you explain the vanishing polynomial to a friend? Given a set of points from a finite field, the vanishing polynomial is a unique normalized polynomial that has exactly these points as zeros. Kills everyone in a group. Harsh. It's the Houdini of polynomials. Some call it the quotient polynomial. There's a little reference in there. How would you explain vanishing polynomials to a friend? People have said, I quit all friends who could not perform a Lagrange interpolation. I might use the Cinderella shoe analogy. Alternatively, one can create a story around the Schwartz-Zippel lemma. Okay, I said it right. Actually, when I read this question, I didn't know it. After a little research, now I know that I cannot explain it not only to a friend, but also to myself. So that was a hard one, I guess, this time around. Anyway, thank you so much for filling that out, and thank you for being here at the ZK Summit 8. Cheers. Cool. All right. Next up, I'm going to be inviting our 3 platinum sponsors to share a little bit about, what they're up to and also why they're here. So first, I want to invite Aleo to the stage. Alex, please share, what you have. There you go.
Awesome. Thank you much, and hey, everybody. I hope you're having a good morning. Before I tell you a little bit about Aleo, I just want to take a moment. I know Anna mentioned it, but I think we should all acknowledge via a round of applause the incredible accomplishment of the Ethereum community today with the merge. So, it's a huge moment. I mean, as all of you no doubt know, this is hundreds of people working millions of hours probably over the course of years. And I think, even whether or not you're part of the Ethereum community or if you are more so or less so, I think, for the industry as a whole, I think it's a really, really incredible moment. I'm here to tell you a little bit about Aleo, but not very much, frankly. I'm going to let Howard, who's following me up on the stage, tell you a little bit about Aleo in the context of demystifying zero knowledge. But just briefly, Aleo is a decentralized platform for private applications, inspired by some of the key ideas from Ethereum and Zcash. In fact, it's based on a paper called Zexy, which was written by several of the Zcash founding scientists. Basically the upshot is it's enabling user or developers to build applications with the power of zero knowledge proofs and making that as easy and as abstracted, the difficulty of that as abstract as possible. So, but we're very proud to sponsor ZK Summit. I'm proud to say that this is, the second time we've been a sponsor, or actually third time I think we've been a sponsor. And for me personally, it's special because I have been a fan of the podcast personally for a long time. And I've been helping out a little bit with this event, and it's been amazing to see the blossoming of this community and this industry. From kind of a really small group of hardcore people to a much larger set of folks, to the point where Anna even has sold out of tickets, I think, weeks ago, and so the demand for people who want to learn about the space and be a part of this community is really grown tremendously, and that's in large part due to the work that the ZK podcast, the work that Anna's done at ZK podcast and with all the other events that she mentioned. And I think one of the things that makes our community special is the contributions that we all make back to it. And so I'm just going to take a couple of minutes and go through some of the things that we have tried to contribute to the community at Aleo that I hope someone in this room, or many people in this room find valuable. So the first one is our setup ceremony. So without getting into the details about Aleo, we did a setup ceremony, actually 2 setup ceremonies, for Gross 16 SNARK and Marlin. So we have, these are parameters that are generated trustlessly via a powers of tau type ceremony that anyone else in the community can use for their projects. So, of course, like doing a setup ceremony is time consuming, difficult, and takes a lot of coordination. But we've done a lot of that work for you here, and we have SNARKs that we set up from Groth 16. We did phase 1 powers of tau that had 1,000 people contribute. Actually, we had two versions, one size 2 to the 19, one size 2 to the 20. 1,000 people contributed to that for phase 1. So anyone can take that and then adapt it to their own project. And then for Marlin, our setup has the SNARK that we did a setup for is size 2 to the 28. And we had over 100 contributors to that, actually 150 now contributors to that. So again, this is for a universal SNARK, so anyone can take that setup and use it for their own system. So hopefully this helps people bootstrap their own projects, is something that can be a public good for people to use. The second thing I want to briefly talk about is ZPrize. So actually, last ZK Summit, ZK7, I announced ZPrize, which was meant to be a collaborative effort among a number of participants in the industry to help accelerate ZK proofs. And the idea was to really use hardware and accelerate proving and verifying across different hardware platforms and different protocols. And I'm really happy and proud to say that effort is going fantastic. We started it, so the announcement was back in April for ZK Summit 7, and we've been running the competition now, which has about 100 competitors competing across 11 prizes over the course of 4 months, and the due date for submissions is coming up in the next few weeks. And so, these are for a couple examples. I don't know if I have them here. No, I don't have any examples of the prizes. But for example, some of the work that's being done is around accelerating multiscalar multiplications and NTTs on GPUs or on mobile devices. So some of these low-level primitives that apply across a lot of different proof systems and protocols is what we've aimed to try and incentivize the competitors to work on as problems for this competition. So I'm very excited. I think a few people in this room might actually be working on this, or be getting ready to do a submission in the next couple of weeks. And these submissions, once they're submitted, are all going to be open source for the good of the community. So I'm very hopeful that we'll be able to take what was previously the state of the art with regard to these primitives and advance them, hopefully by an order of magnitude, to make, and the ultimate goal is, of course, to make this technology more accessible and more usable and more practical for everyday applications. So very proud to be a part of that. Aleo is very proud to sponsor that, and we're even more proud to be here to sponsor ZK Summit 8 today. So with that, I'll conclude and I'll pass it off to, actually, before I do that, I did want to say one last thing about Aleo. So we actually are in the middle of launching our last testnet, and this is important and connects to the last slide because ZPrize, there is actually a category for POSW, which is the method by which we distribute Coinbase rewards. So if you're interested in learning more about that, you can check out aleo.org. We have some documentation about testnet 3, and you can use hopefully some of the open source work that people have contributed as part of ZPrize to participate there. With that, I'm going to pass it off to my friends at Anoma to speak about their sponsorship.
Something like this. Hey everyone, my name is Awa. I am one of the co-founders of Anoma, and today I won't tell you what Anoma is. Instead, you can talk to our team. They're all running around with different odd-looking t-shirts, or if somebody with really red hair, you can also ask him. But today, this presentation is actually the TLDR of the cryptography and the knowledge proof projects that we're working on at Anoma. So, I had to pick which ones to highlight, and I picked 2, but later on I'll walk you guys through the list as well. So the first thing to know about us is that every project and every product has a name, but it also has a mascot. So we have this project called Vampire, and for now, as of the last retreat, this is very recent in August, we picked this cat with vampire-like moles as the mascot, and it actually makes sense. So Vampire is a project that relates to category theory and how you should ask our team members. But for now, that is our mascot. And what is Vampire? Vampire is a universal language for arithmetic circuits. Actually, the very good entry point to the Vampire project is this talk that Joshua Fitzgerald from our team gave at ECC 5. You can check it out on YouTube. The motivation behind Vampire is that it turns out that as time passes, there is a huge demand for, or it is a common case where developers are working with custom circuits and writing circuits and rewriting them. And it's actually really hard because you're writing at a very low level. And a lot of times for testing and after customizing it, you actually have to go back. So it's a lot of work. And it's a common problem that many of you are probably facing, where it would be great to have higher level languages or different intermediate representations to make it easier. So that's what Vampire is about. And very important, Vampire is not ANOMA specific. Vampire sits, if you look into, we want to tightly integrate it with one high-level language that we're working on, which is Juvix. However, the idea is that it is agnostic and it is actually working well and integrated well with DSLs, higher-level languages, as well as other low-level parts. The other project is Taiga. And the mascot of Taiga is for now Joe. You might know Joe. Joe is one of the team members on the cryptography team. And this is a shot taken by Joe last time I saw him in person in Switzerland 2020. And Taiga is, according to Christopher, a dark forest of zero-knowledge programmability. The best entry point to Taiga would be to watch this presentation that he gave recently in Las Vegas. It is on YouTube as well at ZCon3. And if you want to check out the design and the why of Taiga, you can find the details in the repository. So there's more crypto. There's Fairview. Fairview is the DKG protocol, and it is a library. You can actually deploy Fairview if you integrate it easily if you run some kind of like BFD consensus. The idea behind Fairview is to allow some kind of front-running protection from validators. Fairview is, we're working on Fairview in collaboration with Dev. Oh yeah, you might know Dev from Osmosis. I think he might be coming around here. We've also been working on Plonk Up in collaboration with ZK Garage. If you've seen a guy with strip, Luke is running around and he has been leading also that initiative. I think he's the side stage I'm seeing over there. There is ongoing research and design around private bridges. This is actually very important because with the world of privacy sets at the moment, as long as they're deployed to sovereign chains, they will be competitive. But if we find a way of doing private IBC or private bridges, then all anonymity sets can be shared, even independent of which security model they're in and which layer ones they're in. There is the MSP and the convert circuit. This is actually some of the most boring projects that we currently have, but Christopher is going to give a talk about this a bit later and why we decided to build this and what for. The spoiler to this is that the circuit was actually audited by GP Amazon, and it's pretty good cryptography. More details about all these projects. All specs are open source, and all code repositories can be found there. And just why are we doing so much crypto? And trust me, it all makes sense. We actually need all this stuff one way or another, or at some point now, very soon, or sooner or later. And you can verify my statement by reading the white paper. This is where we walk through the entire architecture design, the entire vertical integration. There's a plan, and really, it makes sense. This is why we're not doing research for the sake of research. So check out the white paper. And the way we look at zero-knowledge proofs and cryptography is really that these are all public goods. This entire space and all the cryptography that we're building on were built on public goods that were initiated by researchers. There was open source research, there was open source libraries at the ECC by researchers like Howard, Dan Bonnet, Alexander Chiesa, Dev, so many. And we need to continue building them. So, and everyone here and all of you will be working on public goods. So let's build together. Anyways, the TLDR is ANOMA, too much crypto.
Thanks so much. Jonan, I'm going to invite you up. So this is our third platinum sponsor, Polkadot Web3 Foundation. Thank you so much.
Good morning, everyone, and thank you for having us. Really happy to be here. Proud members of the community for a long time. Super impressive community. I've met some really interesting people since we've been here. I understand we were maybe the second sponsor ever, so we'll be proud of our close second place. A lot of people have mentioned to me, or just straight out asked me, why are you here? Like, what does Polkadot have to talk about here? Well, we have a pretty exciting thing to talk about, actually, which is Manta Network. I don't know if many of you are familiar. Is Manta here yet? Where's Manta in the room? Sleeping is the answer. Manta is sleeping in because they had too much fun last night at the speaker party. But the Manta Network folks are here, and at least Kenny and Finch are here. Just walk around and ask someone if they're Finch over and over again. You'll eventually find him, probably. The Manta Network was part of our grants program. The Web3 Foundation awards grants to people who are looking to build interesting things that will benefit the network at large. So the Polkadot network does not yet have Manta, but I understand it's coming soon, and they are right now testing on our partner chain, Kusama, with the Calamari network. They do the ZK SNARK Tor Circuit VKF LEM. I don't know anything about what you all do, but I'm super impressed, and I'm proud to be here learning. If you want to teach me a little bit about what I just said entirely incorrectly in the hallway, I would invite your participation in my education. But check out Manta Network. They have, for those of us who are in my position, not terribly well versed in the cryptography world, they actually have a really good introduction on their website, and I can help you find that. If you come find me, we have socks to give away and many stickers. And once again, we're just really, really proud to be here and appreciate very much all of your support. So thank you. Have a wonderful day.
Thank you so much. All right. So I want to invite Guillermo to the stage. So Guillermo and I are going to be running this stage together this time. I learned the hard way at ZK Summit 7 that like one person should not do it the whole day. I like barely could leave. So now Guillermo's helping out. Guillermo, do you want to share who is our next speaker? Yeah. Actually, who's our first speaker?
Ooh, I think our first and next speaker will be Howard Wu, who will teach us how to demystify zero-knowledge programming. Please come on stage.
Thanks. So we'll hopefully new slides, demystifying. There you go. So I think this is your guy.
Thank you.
This is your mic.
Thanks.
Just make sure that's there. This is your guy.
Yeah, that's the right one. Yeah. Check system. All right. Hi everyone. I'm Howard. If you don't know me, I'm a co-founder of Alio, and today I want to talk a little bit about programming in zero knowledge and the programming model of zero knowledge. I think there's been a lot of discussion, especially over the past few years, about building out ZK virtual machines, and especially in light of the discussions recently with ZK EVMs, I thought it would be worthwhile and a good use of this opportunity to really talk about the challenges with respect to the account model, some of the ways to remedy it, and then more broadly speaking, how to build tooling and infrastructure around that. So to get started, a lot of the work that I'm going to be talking about today was actually born out of a research paper from several years ago called Zexy. It was published in Oakland 2020 and introduced a protocol that extended the zero cache protocol, or aka Zcash, to support general purpose applications. Before I do jump into things, though, I think that it's worthwhile, especially because there's a lot of newcomers into this space, to really go through how zero knowledge at a very basic level works. And before I even do that, I want to thank Anna for putting together this amazing community. It's been several years in the making, and the good news is, because not many people clapped for ZK1 when she was checking, I can reuse a few slides in here, which will be also very helpful, since I want to make sure everyone's on the same page about how zero knowledge works, what the concept of zero knowledge proofs is, and fundamentally, what are the assumptions, the trust assumptions between the prover and the verifier, which we'll talk about next. So let's jump right into things. In terms of the talk today, the content's going to be broken into three parts. The main thing that I really want to convey is that there are things called ZK SNARKs. My hope is to help you understand on a higher level how things work there, and then dive into the concept of a ZKL1 and how you can build a virtual machine around a blockchain that can be provably verifiable. And then lastly, to get a little snarky and talk a little about the way that we're instantiating things on Aleo. So let's jump into it. What are ZK SNARKs? Well, to even talk about that, we need to start with a basic premise, which is to say that cryptography is a really powerful tool for building secure systems. And much of the cryptography that we use today is really to give security guarantees about data. What do I mean by that? Well, for one, whenever you're transmitting information, say, over the web between two parties, one of the things that you really want to do is to encrypt your content so that only you, as the sender and the receiver, see this message. And so we use cryptography for encryption. The second way that it's commonly used today is really to offer security properties with respect to authentication. And what I mean by that is that when you have the sender and receiver communicating with each other over the web, you want to make sure that the receiver is really getting the message from the sender. And so, one way that you can do that is you sign the message and then send it over. And these are the two primary mechanisms that we use cryptography for. It's really about securing data, and data at rest, really. But the question is, can I use this type of cryptography to do even further, to really give guarantees about computation? And this is where the domain of cryptographic proofs comes into play. Cryptographic proofs can offer privacy-preserving guarantees for computation. And that's something that's, in my opinion, a very new field, a very new domain in terms of what's becoming practical and ready to use in the real world. In particular, a cryptographic proof is really saying, hey, I securely computed this equation f of x, and its result was y. And the goal is to convince other parties on the internet that I really did do this. And when you dive in and double-click, there's an even further kind of specific segment of cryptographic proofs called zero-knowledge proofs. And zero-knowledge proofs are there's a lot of jargon here, so let's break it down. Privacy-preserving cryptographic proofs of computational integrity. And this is really taking it one step further. And what I'm really saying here is to say, I know x such that y equals f of x, where x itself is a private input. And this takes that concept of a cryptographic proof and kind of takes it one step further. So when you're on the web, sometimes you don't want to share everything that you have or know, especially when it comes to personal information, PII, across the web to other people as well. But in order for other people to verify that you really ran this program and got this result Y, they need to somehow trust or believe that you used the right inputs. And if you don't want to reveal that, then zero-knowledge proof ends up becoming a very useful primitive for this. I think another way to frame a zero-knowledge proof is to say in English that I know the secret, I can't tell you the secret, but I can prove to you that I know the secret. And this is really getting at the heart of what zero-knowledge proofs are about. It's really trying to convey information to another party without revealing the full set of information that you want to reveal. So to give you a concrete example of it, there is a very canonical example that many of you may have seen on the internet, which is the Where's Waldo problem. And it says, the question goes like this: can you prove to me that you found Waldo without telling me where he is on the map? And you can take a moment to think about it. I'll give a quick fun anecdote, which is to say that when in creating these slides, I actually had to go find an image of Where's Waldo, and it took me quite a while on Google search to find a good image of this, because I had to keep checking whether the image itself had Waldo in it. I wasn't sure if there would be an April Fool's prank in there or not, so it would have been really nice if there was already a zero-knowledge proof for it with the image so that I could just pick one that looks really visually nice. But just to give the answer away, first off, Waldo's right there, and the way that you want to show to another party that you found Waldo is really as follows. You want to take a really big white sheet of paper and cover the entire screen with it, just the entire screen, something that's just much larger than the map itself. And you want to cut a little hole in that white piece of paper, just enough to fit the size of Waldo, so that when another person comes into the room and just sees a giant blank canvas with a little hole and sees Waldo sticking out, they can be really convinced that there is Waldo on a map, and Waldo truly exists and that you found Waldo. Then, if you ask them to leave the room and you remove the white canvas, when they come back into the room, they just see the basic map again and they can now take a stab at it. And that's one way to kind of convince you that, I really found Waldo. Waldo exists on the map and I know where Waldo is on the map, but without revealing where Waldo is relatively on the map. Where's Waldo? He's right there. So yeah, this is one canonical example, and I'll very quickly run through just another one, which is the Alibaba cave, which is also a classical one. If you go to the Wikipedia page, you'll find this one, and credits to Wikipedia for the images too. But just to give you some background context, this example actually came from a paper back in 1989 called How to Explain Zero-Knowledge Protocols to Your Children. I'm not sure whose children are learning about zero-knowledge proofs, but for them, I say I applaud you, and I'm very excited to work with you in the future. You guys are going to be geniuses. But the basic premise goes like this. You have Alice and Bob. Alice is basically walking into a cave. The cave has two sides, branch A and branch B. Both branches are actually connected by a door on the back side there. That's that black line. And once Alice walks in, Bob can flip a coin and say, I want you to come out of, say, A if it's heads or B if it's tails. And if Alice has the key, Alice should be able to walk right through that door in order to come out the appropriate side. So if Alice randomly said, I'm going to go in path B, and Bob says, come out of path A, well, she should be able to open that door and walk right through if she has the key. Now, as you can imagine, there are also, quote-unquote flukes where you could say, Alice walked in B, Bob flipped a coin, the coins had come out of B, and then Alice comes out of B without the key. And this is why this is more probabilistic. You want to play multiple rounds of this game. If you play multiple rounds of this game, probabilistically, you can bound the chance that she's really lying to you down to eventually zero. The limit goes to zero. And this is a very canonical way of kind of explaining how a zero-knowledge protocol really works, because most of the schemes, especially in the early days, were designed around interactivity and having this kind of prover-verifier challenge, as it's commonly called. But so yeah, let's dive right into things. So the first zero-knowledge proof was actually invented in 1989. It's by Goldwasser, Macaulay, and Rakoff. And back then, the model was basically this. You had a prover that had a function f, some claimed output y, and a private input x. You also had a verifier who knew the same function and the same claimed output. And the goal was to say, the prover says, I know some private input such that y equals f of x. And the verifier says, prove to me that you know x. And what they would do is they do this multi-round interaction and communication. So the verifier would effectively send challenges over to the prover. The prover would evaluate those challenges, send responses back to the verifier, and do this several times. And similar to that Alibaba cave example, if you did enough rounds of this, the probability bounds got you to the point where you could feel confident that, well, the verifier would be convinced that the prover must have the secret. If the prover doesn't have the secret, they couldn't answer all of these queries in a go. And so that was the way that this was designed. But this, as you can imagine, from 1989, had a lot of trade-offs. First off, as you can see, it was interactive. And if you imagine that this is on the internet and you have two random strangers on the internet, asking both of these strangers to be online on the internet at the same time to communicate is a pretty big ask. And interactivity, foundationally, is therefore a challenge. The second main thing is that, well, this design itself was not succinct. And what that means is that the actual proof itself to verify took roughly as long as it would take to compute the function f itself. And so if you wanted to, say, outsource some work to another party and have them compute it for you, well, to check that they did the work correctly, you'd basically take as long as it would take for them to actually produce the proof. And that's not a great guarantee as well. And the last thing was to say that it had very poor concrete efficiency. So the prover took a really, really, really long time to generate the proofs for you. And therefore, this was really impractical from a real world context. It was incredible, though, from a pure academic and theoretical construct to say that you can use math to even make claims like this. So in order to remedy some of the issues I just talked about, actually in 1994, Silvio Macaulay published a paper that showed the first succinct non-interactive ZKP. And the idea there, again, was to say that there was a prover, but now the verifier was actually really, really small. And so that's the succinct property. And diagrammatically, I show that the verifier, therefore, is much smaller. And the prover actually made the same claim as before. It says, hey, I know some x such that y equals f of x. And the verifier once again said, prove to me that you know x. And now, instead of doing multiple rounds of interaction, they use basically a random oracle. You can think about it like SHA-256 or Poseidon in this case, as we now use today. But the premise was that instead of having to have the verifier come up with some random challenges that then get sent to the prover, who then evaluated it, who sent them back to the verifier, who then sampled some new challenges and sent them back to the prover to send more responses, they could both agree on, for example, a hash function and say, hey, like, here's the pre-image we're going to start with. If we both agree on this, we can then hash from here and use the same assumptions for what you should be evaluating. And then, therefore, the verifier can just say, well, I knew what you were starting with, and I can iteratively check that you actually use the same call functions to do the actual interaction part normally. And this saved on the actual need for both parties to communicate with each other. The end result is that the prover only had to send over one proof to the verifier. This ended up being a non-interactive scheme because of that. And this was actually the first ZK SNARK. And so it's been, like 20, 30 years since we've gotten from the original concept of a zero-knowledge proof to where we are today. But there has been a number of things that have a number of advancements, especially in the theory and the engineering, that has gotten us to a point where we can now run this stuff in the wild, in the real world, on very expressive statements. But before we start talking about that part, I don't know how many people are familiar with ZK SNARKs in its entirety, and so I want to just give a quick definitional construct for it. So zero-knowledge proof itself, basically, ZK SNARK stands for a zero-knowledge, succinct, non-interactive argument of knowledge. That's a lot of jargon. What does it mean? Well, zero knowledge means that the proof doesn't reveal the witness. The witness is commonly the private input in this case. That's the secret that you don't want to reveal. Succinct just means that the proofs are small, so they're like, a kilobyte or less. And the verification is fast, which means it's like, 10 milliseconds, 20 milliseconds, something that's realistically practical and fast to check in your browser. The third is that it's non-interactive, which just means that there's no interaction that's needed between the prover and the verifier. And lastly, it's an argument, which just means that soundness holds against a polynomially bounded verifier. This is a more technical delineation because there are statistical bounds and there are computational bounds that one can give for the verifier here. And so this is one set of that. So hopefully that gives you some context into what ZK SNARKs are. And now I want to talk a little bit about how you can use ZK SNARKs to basically build a layer 1 programming model around it. I think the easiest point to start from, frankly, is the account model, because I think everyone here, or almost everyone here, has had some interaction with Ethereum before. So before we jump into things, I think it's well motivated to say that people really like to build applications in Web3, and there's many use cases for it. And the goal is to say, can we build a ZKL1 that can support every one of these? Yes, the short is you can, but it comes with a lot of limitations. The first is that, well, when building a decentralized ledger, we need to operate by verifying and confirming that each transaction works via re-execution. What do I mean by that? You have a user who's submitting a transaction, and it's composed of the application, the input, and the signature, and the user broadcasts this transaction to the network as so. And each node on the network then re-executes the associated computation in that transaction. If the computation is correct and the signature is valid, well, the application gets updated. And as you can already begin to see, there's a lot of re-execution that's going on in this model. And so let me walk you through some of the limitations of this. First, it's that ledger re-executions really hurts scalability. So in general, every transaction rerunning computations on every node on the network will result in a lot of wasted work. In fact, if you just take the Ethereum structure from ETH1, and I realize that post-merge we got to redo the numbers here. This is 3,000 nodes. If we just assume that there's like 5 seconds of computations in each block, and this math already adds up to 15,000 seconds, or about 4 hours of re-execution. That's a lot of wasted work. And you can naturally see just from the previous slides on what a ZK SNARK is you probably want to try to, kind of give a proof about it so you don't have to recompute it and everyone doesn't have to recompute it. That's like a big deal because this model here is, well, wasteful. The second thing is that ledger re-execution hurts privacy. And what I mean by that is that, like, in the existing models of decentralized applications, you learn everything. You learn who's the caller. You learn who's the receiver. You learn what program you're calling. And you learn the logic of the program as well as its data. And like this is something that I think requires a lot more nuance if we're going to take this out into the web. The classical example that I give is to say, if I want to send you money and you give me your bank account number, knowing your bank account number reveals nothing to me about how much money you have, how much money you make, how much money you spend, where you spend it, when you spent it. It doesn't reveal to me any of these things. But if you give me your Ethereum address, now I know all of these things about you, and I can track you also for the rest of time with that. And so this is fundamentally just a UI UX challenge that Web3 introduces that we need to kind of think about if we want to take this technology out into the real world. And so we built something called Aleo. Aleo stands for Autonomous Ledger Executions Off-Chain. Aleo itself is a decentralized ledger and enables users to execute programs off-chain and finalize state on-chain. The ledger provides several properties. The first is that we achieve scalability, meaning thousands of transactions per block. The second is that we preserve privacy, meaning the resulting transaction reveals no information about off-chain computations. And lastly, we have succinctness, which just means that the resulting transactions are small in size and fast to verify. Concretely, for reasonable parameter sizes, we get transactions that are approximately 1 kilobyte in size, and they can verify in less than 50 milliseconds. And so our programs also provide us with several properties. The first is, in terms of functionality, we enable arbitrary user-defined programs. And while isolating malicious programs from honest ones, and we enable program functions to communicate with one another in a secure manner. So to see how we arrived at this design, let's start by analyzing this popular framework called the account model. So in the account model, you basically have a decentralized ledger that's tracking global state. And to perform a state transition, the user usually signs an input, transaction, that produces a request to say, hey, please execute this program with the given input fields. And once the transaction's been verified, well, it's confirmed into the next block by the ledger, and the account state updates itself automatically. It's an internal operation, and it transitions from the previous state into the new state of the program. The intuition here is that users invoke programs with these inputs via transactions, and the ledger updates that internal state based on the outcome of that transaction. Naturally, one of the biggest benefits of the account model, as you guys know, is simplicity. It's really easy for developers to coordinate and manage state between multiple parties. But there's a few trade-offs, of course. One is that there's kind of a scaling problem. There's also a high fee problem, and they're duals of each other in the sense that complex tasks can be time-consuming, and large queues of unconfirmed transactions can build, which causes significant spikes in the network fees to occur. And the last one, naturally, is that there's just no privacy in the account model today. And what do I mean by that? Well, transactions reveal the contents to everyone on the network. This means the sender, the receiver, the program inputs, outputs, and state are all publicly known. So what do we want to do? We want to redesign this ledger, and we want to minimize the re-execution and maximize privacy. And so how do we do it? Well, let's just sprinkle some ZK SNARKs on it, of course. We want to extend the account model and see where we land here. So let's take a first attempt at extending this. And the intuition is to say, let's start with private smart contracts. Instead of revealing in the transaction your value, the data, the call data, and the signature, why don't we move things over into saying, let's commit to the values, let's encrypt the data, and instead of using a signature, let's start using cryptographic proofs, as we talked about. And for on-chain state, with your account, instead of publicly showing your balance and publicly showing your code and publicly showing your storage, why don't we commit to the balance? Why don't we create a predicate about your code, and why don't we encrypt your storage? Then from here we could say, now when a user is creating a transaction, they're really revealing a transaction that has very little publicly reasonable data. And what's being updated on chain is not the actual data itself, but commitments and encrypted data from the previous state into the new state. That's the rough intuition on doing this. Now, if it were this simple, I don't think I would need to be here talking about this design. So let's start thinking through some of the properties here in this design. Why this doesn't work? Well, for one, concurrency is a really big problem. Let's say you have user A who wants to make an update, So he calls with transaction 1, update program A. If party B comes and says, I also want to update it in the second transaction, this actually doesn't work. Because the entire state is now encrypted, only one party at a time can actually go and update that state. Because you have to Merkleize things in a cryptographic system, and your root is effectively expiring as you're making that state transition. The second issue is that we still don't have full privacy in this account model. Why? Because everyone can see that user 1 updated program A. And the reason for that is, if we go back just a few slides here, the transaction still reveals the address, not only the address of the user, but the contract address that you're referring to. And so if I were in that bank account model saying, I want to send money to you, give me your address, I might not know anymore how much you're spending or how much you're doing, but I clearly can see you're using this account, and I can see which applications you're using, and I can still cluster and deduce how frequently you're transacting and where you're transacting. You can also still figure out who's paying you for your salary, and also who's paying you in general to say pay back debts or pay back loans. And this then therefore says this is not full privacy, at least in the canonical definition. So let's analyze the properties more concretely. The first is to say, we have no more ledger re-executions. Why? We use a zero-knowledge proof, and with the zero-knowledge proof, we're able to achieve scalability and succinctness. The second thing is that we achieve data privacy. As we said, there's no account privacy, but we do have data privacy because we're using commitments and encryption to hide program state itself. But as we just said, the address can't be encrypted because in the account model, you're indexing by address. And so as part of that, the ledger fundamentally relies on it to index into global state. Fourthly, we have a lack of efficient state updates. Why? As we just said, we have to consume the entire program in order to make one state transition about it. That's not a great model. Like, imagine if you want to update your UC20 and you have to reason about every other person's account as well in order to make one cryptographic update. And lastly, of course, there's no concurrency, because when one person makes the full update, you invalidate the ability for another person to update the same state at the same time. So the proposal that we came up with was to say, let's introduce something called the record model. What is the record model? Well, in the record model, the decentralized ledger still tracks, or now tracks, the records of each account in global state. And to perform a state transition, users generate a transaction computing a zero-knowledge proof that attests to the state transitions for the given execution. Once the transaction has been verified and confirmed into the next block of the ledger, the program updates itself internally. And this transitions that previous state into the new state of the program. The intuition here is that the users only consume the records that are necessary to make the state transition that they want for their program in their context. And this no longer requires you to consume that entire state. So because of that, you actually get concurrency, because I'm only reasoning over the records in the account that belong to me. And then I'm going to take those records and produce a state transition out of it. The second thing is that this also enforces double spend conditions. Why? Because your account state is now properly indexed using records, if I'm going to try to spend this record twice, it can be easily detected on the network that this record was previously spent, and I can't respend this record again. And this model then gives you some way for consensus to easily check cryptographically that indeed this state was only used once without actually seeing the contents of the record. So when we come back to it, now that we have abstracted into a record model, we actually get account privacy. Why? Because the decentralized ledger indexes global state based on these program IDs. These IDs end up becoming the actual clustering point as opposed to your account address. And that fundamentally changes the assumptions that are being made in the privacy model of programming. We also get very efficient state updates because you only need to consume the records in a program that belong to you or the ones that you actually want to use in order to perform the state transition. And lastly, you can also do simultaneous updates because within a program, you now have this record system which says that you only need to consume the records which belong to you in order to perform your updates. And other people can touch their records to perform their updates. And this type of isolation is what enables multiple parties to interface on the same application at the same time. So hopefully that helps give you some color into how you design the record model in this context. And lastly, I want to just say, like, We want to instantiate this. So how are we going to instantiate it? Well, in order to instantiate it, we have to use a lot of technology, a lot of disciplines in order to come together and build this thing. And Aleo is at the intersection of several different disciplines. Everything from everything from mathematics to complexity theory to cryptography, computer security, and programming languages. We sampled curves that enable SNARK-friendly cryptographic primitives. And namely, we sampled a 377-bit curve with embedding degree 12, which we call BLS12377. This curve is great because it supports fast proof verifications in our construction. We also sampled a twisted Edwards curve, and it's useful for efficient Peterson hashes and commitments, as well as signatures. And in general, Edwards BLS12 enables efficient circuit operations. Finally, we instantiate our SNARK. Our SNARK here is Marlin. Marlin itself was published at Eurocrypt 2020, and Marlin's great because it requires only a single trusted setup for all programs. This is the universal setup that Alex previously was talking about. If you'd like to see our work, the good news is it is open source. The work here that we have is with respect to Leo, Aleo, and the AVM itself are all on GitHub. And the rationale is to say I can take a very high-level piece of language called Leo, a piece of code in Leo, compile it down into an assembly-like language called Aleo instructions, and from there serialize this into AVM bytecode, which then can be deployed on-chain. So earlier when you saw with the programs and records on there, the program itself contains a predicate that's represented with respect to that AVM bytecode, and all of the code prior to that is from off-chain, from the developer themselves, writing out exactly how the two parties should be interacting. To give you just a small taste of what this looks like, this is the syntax for Aleo instructions. You can see here function main, and my inputs start off with registers, register 0 and register 1. In this example, what I want to do is multiply these two numbers. So I can pass in a public field element and a private field element. I can multiply these two things into register 2. And then lastly, I can output as a private register the field.private, basically, the result of that multiplication. Because this is adhering to the account model, what this actually does is say, when I want to broadcast on-chain the private state, I need to encrypt this, and this will get encrypted under my account address. And so only I, using my account, can go on-chain and see the result of this computation with my view key. This is the difference between existing programming models in kind of EVM-based systems and the new set of ZKL1s that I believe will use a model similar to this. Lastly, I want to say thank you. Aleo is proudly written in Rust. We have written a ton of lines of code. We probably need to do some refactoring, but there's been a wonderful community of 40+ contributors who are building on us and helping to make Aleo happen. We are available at this URL, github.com/AleoHQ. And lastly, testnet 3 is live, and for those who are interested to play with our network, the developer docs are available at developer.aleo.org. And with that, I want to thank you for your time and attention, and hope you have a wonderful day. Thanks.
Thank you so much, Howard, for this wonderful talk and starting us off. All right, I'd like to introduce Omer Shlomovitz to the stage from Igonomia. I always have trouble pronouncing it, sorry. He's going to tell us about Fantastic Beasts and ZK hardware. Welcome.
Thank you. Thank you. So my name is Omer. I'm the founder of Ingonyama. This is how you pronounce it. The talk today is going to be packed. I'm going to try to get to as much information I can and infuse it to you. If I'm missing something or if you have questions, feel free to reach out later. I'm going to start with the scope of what do I mean when I say zero knowledge, ZK, ZKP. I'm going to use this word many times in the talk. And obviously, we have many ZKPs, like in different shapes, forms, and we can, I don't know, maybe divide them into several families. So we have this line of work, Quicksilver, Mystique, Wolverine, Ant-Man, which is not the focus here. It's not about, these are, I think, you can classify them as interactive zero-knowledge proofs. We have also zero knowledge based on MPC in the head kind of line of work, Ligero, Ligero++, and so on. While fantastic work with really great performance. Again, not what we look into right now when we talk about ZK in the context of hardware, and even not Mali, Nova, GOT16, and variations of Plonk, which are the protocols that we base most of our systems on. What I'm trying to, or what I want to focus on is actual systems that are, let's call them production ready or close to it, and we have many examples to this in the space, right? Here I give a few of them. So these are systems that, besides just the ZK protocol that is in like the backend or something, there's also significant software engineering effort that we're put into making them meet real-world criteria. Right. So we are used, when we talk about ZKPs, we used to kind of discuss or to mention the benefits and all of the advantages we get with ZK and ZK SNARKs, stacks, and so on, right? It can be in small proof, fast verification, and so on. However, in real-world systems, we deal with asymptotic complexities that are no longer, right? Now everything becomes concrete. So we need to take into account all of this into our consideration, right? So what I mean by that, first, we want to focus on the prover overhead, the computation of the prover, which is the obvious kind of goal for acceleration in hardware. Based on Justin Teller blog for A16Z, he estimated 7 orders of magnitude overhead in terms of comparing to just running the computation on a CPU, right? He's done it kind of based on analysis of a front end and back end, as you can see in this figure. Now, what it means is that we want to try and accelerate metrics matrices such as latency, throughput, and even memory. I mean, this is surprising. There's this quote here from one of the papers that is not coming from the, it's more from, I think, from one of the systems that are for interactive SNARKs and our interactive ZKP, and they asked them to, in the reviewer asked them to kind of try and compare the memory for to other systems. There's a huge blow up. I'll touch a bit on this later, but we also want to try to optimize at least the memory consumption while computing a proof. Okay. Now, to do all of that, we obviously have algorithms which have been around for a few decades now. We have software engineering, and we have hardware, which is what we want to focus here. So, as I mentioned, ZK Prover is the main goal of what we want to improve is computation and try to accelerate it or make it more optimized or efficient. And let's try to analyze what does it mean, okay? So let's look at the cake. This is when we look at the actual computation that happens inside of a prover. So we have basically 3 parts. We have the multiscalar multiplication, we have the Fourier transform, the NTT, right? NTT is Fourier transform over finite fields, and we have what I call here fluff, right? So this is the rest of it, and I'll explain a bit about it later. So to give a concrete example, this is data from RapidSNARK. RapidSNARK is a backend based on GOT16. So we know that there's pairing, so we have basically 2 elliptic curves, so we have 2 times MSM, as you can see here, for G1 and G2, and the G2 is even more complex because it's over extension field computation, and you can see that roughly for different sizes of circuits, we get here like 90% MSM and 5% to 7 NTT, and so it means that there's also fluff, right? So it's, I guess, similar. I mean, it's an estimation. Obviously, it's nothing here is going to be concrete. It's just kind of to give you a high-level idea. Now, another thing that's important to say is that this is what, let's name it SNARK, okay, just for the sake of this conversation. We can also look at something called a STARK, where basically we eliminate MSM, and we are left only with NTT. We still have fluff, right? We cannot ignore it. And also there are systems like Nova, where there's the opposite, either there are no entities, only MSM, okay? So basically all of them are based on the same computational problems. Now, once we understand that, let's try to build together some idea on how to accelerate this prover computation, okay? Let's do it like step at a step step by step together. So we have the host and we have this box that is our dedicated hardware. And the first thing that comes to mind is obviously let's just accelerate the MSM, right? So we need to add some memory and then some IP core for the MSM. But this would give us, remember that we have like maybe 80, 90% MSM. So at the best we can get like 10x if MSM is completely eliminated. We get a 10x improvement. And this is not why we do hardware. I mean, 10x is not a good motivation for going into dedicated hardware. So the next thing that comes to mind is after MSM, let's also accelerate NTT, right? Obviously the second big like stone here. So let's imagine that we add another block of memory and then this IP core of NTT, right? Now here, surprisingly, we get another bottleneck, which is in the interface between the host and the hardware, right? So I mentioned there's a huge blow up in the data that we generate inside of or as part of the prover computation. And basically what it means is that the new bottleneck will become the speed in which we can send information between the host and the hardware, right? So again, we're gonna get stuck. So the only way that makes sense now is to also add the fluff, right? So let's divide the fluff into two parts. One is some modules that we can accelerate. Here I'm gonna use an example of hash function, a ZK-friendly hash function that might benefit from acceleration inside of the fluff. Again, for some systems, this might be much more than 5%, but for our mental model, this is enough. And also for some just field computations, let's also add some CPU, like ARM or RISC-V core, okay? So now if we look at what we got, we basically have this chip, right, that has ZK end-to-end, right? We just give it the input, the statement, the problem, and then we get as an output the proof itself. Now, once we have this idea in mind, let's try and look at specific hardwares that we have available for us today. And the first two I want to discuss are GPUs and FPGAs, okay? So graphical processing units and field programmable gate array. And let's try to do like a very high level comparison between the two. So one thing is that GPUs are almost a commodity at this point. They are everywhere. Most of you guys have GPU accessible to you in your Mac, in your phone, and so on. And it's not the case with FPGA, although now we see this FPGAs in the cloud. This is kind of becoming a trend, and it makes the accessibility of this type of hardware significantly better. Another thing is the technology in which we use to generate, to actually produce, to manufacture these chips. So GPUs are a few generations. This is just an example. You can find FPGAs with different technologies and also GPUs, but basically here you can see the GPU, I mean, just like out of the box gives you way better performance, you know, in terms of how many transistors you can stick inside a given area, which also impact power efficiency and so on. So this is another advantage for a GPU. Another thing to note is that right now when we work with GPUs, we usually use software. We write like libraries on top of CUDA and such, so it's a very smooth user experience or developer experience to code in a GPU. While in FPGA, it's still conceived, although there are ways around it, but it's still conceived like a one-time programming thing, and like each time you need a new design, it takes like a whole long time to actually get it done, and not as part of the same run. However, in both cases, it's going to be hard to implement ZK end-to-end for different reasons, right? So the GPU is simply not customizable enough when you think about doing together the fluff that I mentioned, the memory management, the MSM and the NTT. And for the FPGA, it's very limited in the resources that you get, right? So even elliptic curve addition, which is very important, as I'll show in a few slides, is something that can take up to half of an FPGA, right? And this is just like one very simple mathematical operation. So one thing that I want to also share is like where do we stand today in comparison of performance between the two. So I'm going to share some of our results from latest paper called Pipe MSM, and what we chose to highlight here is like the cost per running one MSM. So again, first, it's not an entire ZK, it's just like one multi-scalar multiplication of given sizes. You know, the size, the length of the MSM here is somewhat representative, although we're interested also in lengthier MSMs, but for example, Alio is focused on the 2 to the 15, to the 16 and such, so it's kind of like in the same where we are, it's in the interest area. And you can see that there's like this efficiency that you get when you use this FPGA. Again, what we measure here is this like integral of the over time of the power consumption. Now, few disclaimers. One, there's a huge variance when it comes to GPUs. I mean, in hardware, it's like the same thing every time, but the GPU, really different if it's a consumer GPU or if it's a data center GPU, and so on. Second, as I said, larger vectors are also interesting. And finally, I already know that both in FPGA and GPU, there are already way better results than what is presented here. And I hope that maybe in ZPRIZE and other, we'll see some of them. Right, so this is a good point also to mention a third type of hardware, which is ASIC, right? This is an integrated circuit that is very specific to the problem at hand. And this is probably the best chance we have to get this ZK end-to-end, okay? We know as kind of one signal that we have is that at least we know in terms of power consumption, we're supposed to be 10x better when it compares to an FPGA, which is already better than a GPU. So this is kind of comparing two papers that one was on ASIC, one on FPGA. It does not exist today. One of the reasons is that it takes like forever, like a few years to get it done, to get actual ASIC in the market. It can take 2-3 years even. And also there is this thesis that says that ZK, it's a risk because ZK protocols are like a moving target. Now, I don't think this is the case, but I won't try to argue it here. Happy to talk about it later. All right, so now I want to talk about specific implementations in hardware of ZK primitives, of the computation that we saw before, and kind of give you a sense or some intuition about what it means to write them down in hardware. So we'll start with the modular multiplication. So this is like a very basic primitive. We use it for all of the computation we do. So it's very useful to accelerate it. Basically, it's just taking A times B and do some modulo Q, okay? So let's develop it a bit, right? So basically, it's AB equals to some number that we don't know of times that we need to repeat Q.
Do you want to try this?
Okay, so as I said, this is the, when we try to open it up, this is what we get. And in equation 3, this is our estimation. So we don't know this number L, so we need to estimate it. So here we estimate it to be this L hat, and we also have an error, right? Because we might have some estimation error, which we note as K. Just rearranging the elements, we get that what we need to compute is this residue R, which equals to this expression at number 4. So what was commonly done before is the estimation was really tight. Like we wanted the estimation, or at least like previous generations of modular multiplication, wanted the estimation to be as good as possible. Our idea was to have more slack in the estimation. So we allowed the estimation to be with larger error, which eventually translate into this block here at the bottom. It means that we need to try different values of K. Now, what we gain is that in this estimation above L1 hat, we are able to break it down into two multiplications that are smaller over n or n plus 1 bits. So this becomes very efficient, right? So this is the trick that we are doing. We kind of pay in additions, but save in multiplications, which is exactly what we want to do in hardware. Another primitive that I want to discuss is what I mentioned about the EC addition. I'll show you next how it can be used, but first let's try to think what's the best way to implement it in hardware. So in EC addition, we basically have coordinates, and to represent an elliptical point, we can have few representations. It can be 2 coordinates, 3 coordinates. We use the projective version, which has x, y, and z coordinates, and this is the equations that basically gets us from x1, y1, z1, and 2 to the result, to x3, z3, y3. Now, this is the circuit that we chose to use. Now, there are 2 things interesting about it that makes it hardware friendly. One, there is some redundancy in this equation, so you can reuse some of the operations. The second thing is that it is highly parallel, right? As you can see here, even visually, it's very easy to parallelize this circuit and compute it in parallel, which gives us advantage when we work in hardware, okay? So this is the point I want to make here. Now, let's move on to multiscalar multiplication. This is the expression above, which is kind of like a product between, let's say, 2 vectors of, one of vector of scalars, one is a vector of elliptic of points. The common way to do it is by something called the buckets method, which is a variant of Pippinger. And this is our circuit. This is the core of on how we are doing it. So I want to explain it. There are 3 parts to do bucket methods. And basically the concept is very simple, right? So we want to break, again, do something that is highly parallelizable. So right now, the way to parallelize it is first to break each scalar into segments or chunks of size C bits. C can be, I think here is 9. And we can even do farther than that, like what's in step number 2, which is segmentation. Even after we break each one of the scalars into many segments, we can break it even farther and parallelize it more when we do the actual buckets computation. So to be concrete as possible, in this case, let's say that scalar are size 253 bits, and we take C equal 9 bits. So it means that we have 29 buckets, bucket accumulators. This is this block in, I don't know what color it is. And each one of these bucket accumulator can be broken down, as I said, into, let's say, M equal 8 segments. So in each one we have like 64 buckets. So this is exactly it. Now, what you can see is that first we have this EC addition here in green at the end. So this is something that we keep doing over and over again. This is like the main computation that's being done. So we translated MSM entirely into EC addition operations that are happening in parallel all the time. Finally, by the way, we need to accumulate all of the things together. This is step number 3. This is the final accumulation, which also takes some computation time. There is this cost function here at the end that kind of takes all of these parameters into account and allows us to also simulate and test many of the parameters. I mean, usually you don't want to just implement in hardware before you have your parameters fixed. Okay, let's move on to entity. So here I think, for me, the best way to explain what is entity to begin with is by just spitting out the algorithm, right, for Cooley-Tukey, FFT, which is the standard way we do today this mathematical operation. This is, by the way, used in ZK mostly when we want to multiply polynomials and so on. And the interesting thing to look at is lines 14 and 15. This is the main computation that happens here. This is a recursive algorithm, and you can see that you have this same operation of addition and multiplication in a constant, right? And the constant here is the roots of unity. So let's try to take the hardware look onto this problem. First thing we do is we unroll the recursion of Cooley-Tukey, and we have this nice structure. So from this structure, we can very easily see that there's this very basic building block, right, on the left, that is in charge of, or if you compose it in the right way, you can get larger and larger entity or vector sizes of entity. And this small building block, what it does is just this operation that I talked about before. It's addition or multiplication in a constant and addition, right? So the idea here, the simple idea, is just to have your hardware with as many parallel, we call them here sub-entity blocks as possible. Obviously, the sub-entity block can be not just the basic operation, but like one larger than that. Another parameter we can play with, except of the number of sub-entities we put in the hardware, is also in computing these constants. So one way to do it is by just writing all of them to memory and retrieving them from memory. But maybe you can also compute them on the fly. So here in our cost function here, we have this parameter, the parameter b, that gives us this idea of how many we want to compute on the fly versus how many we want to retrieve from memory. K here is for the, let's call it parallelization factor, and F is just the frequency, because obviously if we run in a higher frequency, we can have faster time. Finally, I want to talk about the fluff. So here I'm going to choose an example, the Poseidon hash function, which is a ZK-friendly hash function, and it's very common in today's ZK systems. So basically, a hash function like Poseidon is composed of 3 different parts. We have the nonlinear part, the S box, right, like taking something to the power of 5. We have the linear part, which is matrix multiplication, and we have some manipulation with addition of constants. So here is our design. And let me explain to you what we see here, because I know this is probably the most complex that we have here in the slides. So first thing to note is that this is a multi-core design, right? And why is that? Because usually when we use Poseidon in ZK circuits, in ZK computation, we have a Merkle tree, or this data structure, that requires us to take one input or one output of a hash function to be the input of another hash function. So this ring design of ring topology allows us to take one output and connect it to the next available hash module that can take it. It's also multi-threaded, right? So here in green we have few Poseidon processors, and the simple reason is that once you start processing a Poseidon hash, then it takes more than 1 clock cycle. So we have all of these operators or gates available at some point. So we want to utilize them as much as possible, meaning that once we have something free, we just start another thread with another hash. So it's a multi-core, multi-hash that allows us to handle these tree-like data structures, like Merkle tree, in a better way. And what's happening inside of this green box is kind of like a general operation that allows us to do all of the S-box matrix multiplication and addition of constants, all of them fit into this thing, okay? So obviously we need to handle memory. It's obviously important, but basically by having this A times B plus C, we can, and I can show you later if you want, how every operation can be handled with this specific box. Yeah, how much time do I have? Okay, so for final slides, I want to wrap up by just pointing out some products that are based on ZK hardware. It's, I don't know how much, if it will make too much sense, but kind of try to put it in a way from hardware that takes huge proofs and make them from hours to minutes, all the way to just already very optimized and small circuits that you want to kind of run without spending battery life at all, right? So obviously one of the products, the first one is this SaaS kind of thing, running ZK proofs as a service. And this is something that can help, for example, ZK VM. We also, as I mentioned, cloud-based marketplace or FPGAs is also something that we see on the rise. It can be very useful for ZK app developers that don't want, like they don't want to do the DevOps. They want just to get an infrastructure and just have a ZK in their application. There's also like physical, let's call it mining machines for some of ZK use cases today. And as I mentioned, there's IP core, like take just one function, let's say for decentralized identity that makes it like really, really smooth and just like use it in some other processor like what you have in the iPhone. That's it. Want to thank Lucas and yeah, thank you.
So I don't think there's any room for questions on this one. Thank you so much, Omer, for this wonderful talk. I guess you'll stick around if anyone has anything, so you can find him. Okay, I think we now have a break. There is one thing I didn't get a chance to mention to everyone. There's actually a co-working space like across the hall. So if anyone needs to do some work, there's actually a place for that. But for now, we're going to take half an hour, go downstairs, get some coffee, and we'll be back here in 30 minutes. Thanks.
You just need a better life than this. You need something I can never give. Fake water all across the room. It's gone now, the night is gone. But sometimes all I think about is you. Late nights in the middle of June.
Hello? Does your mic work?
Hello.
Very cool. Okay, let's go up. So, come on. All right, we're waiting for people to return. I'm just gonna kind of, maybe we should just like fill air a little bit. So I did want to share, I don't know if everyone's aware of this. I did say it at some point, but yeah, there's a co-working across the hall. There's a cafe downstairs where you'd have to buy stuff, but you can get nice snacks. There is an outside area. Oh yeah, in the co-working, there's actually a bunch of board games. There's like Sudoku. There's like Jenga.
Catan?
No, not long,
Oh, okay,
not
okay,
long
okay.
ones. There's Connect 4. It's quite odd selection. There's an amazing puzzle of ZK Hack. We got them made. So yeah, check that out in the break or at lunch. Cool. Okay, I think some people have arrived, so I think we'll kick off our program for after the break. Go ahead.
Cool. And so presenting now after the break is William from Polygon Zero, who will be selling us Apple's new AirPods Pro. Generalizing air to multivariate domains. Thank you. And I think I'll need this. Thanks.
Hi everybody, I'm Will. I work at Polygon Zero, and today I'm gonna talk about a project of mine called AirPods, which is about generalizing air to multivariate domains. So let's get some notations out of the way. I'm going to work over a field f, large enough for security. I'll have traces, which length is n, a power of 2. So n is 2 to the v. I'm assuming that f has a subgroup, multiplicative subgroup h of size n, and here's the vanishing polynomial over h. This set 0, 1 to the v, I'm going to call the cube of a dimension v. And at some point, I'm going to use this multilinear function beta, which interpolates the equality over the cube. So beta xy is 1, if and only if x equals y. Great. So the genesis of this work is R1CS. So when you have R1CS instance, first thing you do is you transform it into polynomials. And then you have two paths. Either you interpolate the polynomials into univariate polynomials, and then you get stuff like Marlin, which uses a univariate sum-check argument, or you can interpolate them as multivariate polynomials, and you get something like Spartan, which uses a multivariate sum-check argument. And so my question was, can we do the same for error-like arithmetizations? And by error-like, I mean error, so stuff like in SNARKs, but also Planck. And so how it goes now is we have error, we transform it into a problem about polynomials. If we go with univariate polynomials, we get classic SNARKs and Planck. But what if we want to use multivariate polynomials? As far as I know, like nobody has worked on that, and like the question is, what would fit in this picture? Okay, so first before error, I'm gonna start with a simple arithmetization. It's quite useless, but it's a good warm-up. We have an n by k table of field elements. We have a polynomial constraint over k variables, whose degree is quite small, much smaller than n. And then we ask that the constraint evaluates to 0 on every row of the table. So here you can already see that why it's very useless, because you could just have the same row over and over again. But how would we prove this fact, right? So you could just give the table, but that would be too large. So like we want like a succinct proof that we know a table that satisfies that. So if you choose to use univariate polynomials, you interpolate the columns as polynomials of degree less than n. You compute this composition polynomial f, which is just the constraint evaluated at all the column polynomials. Then you can prove that this polynomial vanishes on the subgroup h. Okay? This is equivalent to just saying that the constraint evaluates to 0 on every row. And this implies that z of h divides f, and we call q the quotient. Then you commit to all the polynomials. You send them to the verifier. Verifier sends you back a challenge z. And then the verifier checks this identity. And to check this identity, you have to open your polynomials at z. Okay? That's where you use your polynomial commitment scheme to open it. you send everything to the verifier checks the opening proofs and this equality. Great. So that's very similar to what's done in Planck and SNARKs, for example. Now, what if we wanted to use multivariate polynomials? Well, this time we interpolate the columns as multilinear polynomials. We commit to them and send them to the verifier. Then we consider this vanishing polynomial P. So it looks a bit scary, but really, if you look into the sum, all the C of F1 to Fk terms are 0, okay? And so this polynomial is actually the 0 polynomial. So we actually want to prove that it's the 0 polynomial to the verifier. And by a standard argument, you can do that by just proving that it evaluates to 0 at a random point t. Okay? Then that would imply that p is 0 with high probability. Okay, so you ask the verifier for a challenge t. You do a sum check protocol. So p as the form is like a sum over the cube, so you can do the sum check protocol. And then at the end of the sum check protocol, you have this final evaluation over a point z. And the verifier has to evaluate this expression. And for that, we have to open the f polynomials at z. All right. So we can see it's very similar between univariate and multivariate. The only difference is that in the univariate case, we use this quotient trick. And in the multivariate case, we use this trick using the beta polynomial. Great. So now we can go to R. R is extremely similar to the previous arithmetization. Only difference is that now we consider windows of 2 contiguous rows. Okay? So now we have a constraint over 2k variable. And we ask that the constraint evaluates to 0 when evaluated on the ith row and the I plus 1 row. Okay? So that's just basic R. We can easily extend R. For example, we can ask to, instead of looking at the next row, we could look at the next row, or like the kth next row. Another extension could be to look up a constant row in the trace. So like at every row, we look at the ith row and the nth row. Okay? And these extensions can be combined, right? So like for simplicity, I've only considered polynomials over 2k variables, but you could have like much more complicated constraints. So how do we prove R? This is what's done in SNARKs or Planck. It's extremely similar to what was done before. Only difference is that in the composition polynomial, now we have this term f of gx. So this is actually the same as taking your column, shifting it by 1, and interpolating it. Okay? You can prove that it's the same as doing f of g times x, where f is like the column polynomial. The reason is if you evaluate this at g to the I, you get f of g to the I plus 1, which is what you want, like the next value of f. And otherwise, everything is the same until the last check, where this time the last check also includes terms like f of g times z. And for that, we have to open our polynomials at g times z. So we open them at z and g times z. All right, and so that's basically SNARKs. Now, what if we wanted to do that with multivariate polynomial? Is it that easy to? The answer is no, because here we have the term g times x, which doesn't really make sense, because x now is like a multivariate. It's like x1 to xk. So multiplying by g doesn't really make sense. And if you try to look into like how would you do it, it turns out that, I mean, at least I don't know like how you would do it by just trying to take the previous protocol and transforming it for R. Okay. So we need to generalize a bit. I'm going to generalize using something I call endomorphisms, which is basically just functions from the set with n elements to itself. One example of an endomorphism is the shift, which takes I to I plus 1. And so if we consider any endomorphism sigma, so just a function from n to n, we can have this new arithmetization that I call sigma R, where this time we have our constraint looks at the ith row and the sigma ith row. Okay. So how does it look in practice? If we set sigma is the shift, we get back a regular R, right? If we want to use the kth next row, that's equivalent to setting sigma is shift to the k. So shift to the k just sends I to I plus k. Okay. If we want to use the nth row, that's like the same thing as setting sigma is constant at n, the function that sends everything at n. And so we have tons of choices for sigma n to the n. So which choices of sigma make sense? Which choices of sigma can you use to like actually build a real protocol? And we can actually classify them. We have this theorem that says that the proving system for error can be adapted to sigma error if and only if sigma can be extended to an affine function. This shouldn't make too much sense for now, because sigma is a discrete function. So what does it mean for it to be extendable to an affine function? You can define it in full generality, but I'm only going to talk about like h and the cube. Over h for unified polynomials, we look at sigma as a function from h to itself, and we ask for an extension sigma bar from the field to itself, such that sigma bar has the form ah plus b, okay? So just an affine function. Now, for multivariate, in the multivariate domain, we consider sigma as a map from the cube to itself, and we ask for an extension sigma bar from f to the v to f to the v, such that sigma bar is a function of the form ax plus b, where a is a matrix and b is a vector. Okay? So we get some linear algebra in the picture somehow. Okay, now we have a sigma arithmetization. We assume that this condition of linearity is satisfied. How do we prove it in the multivariate domain? Well, we can just take the previous protocol and just modify it very simply. In this p of t polynomial, we just add the variables f of sigma x, which now makes sense because sigma is a map from the cube to itself. And in the last step for the evaluation, we open our polynomials at z, but also sigma bar of z. Okay, again, this makes sense because sigma bar of z, sigma bar takes like elements of f to the v to f to the v. So everything makes sense. And with this linearity condition, you can actually prove that this proving system works. Good. So that's all very abstract. So like, what kind of sigmas can you actually choose in practice? So in the univariate case, you can actually prove that the only sigma that work are the shift to the k and the constant at k. Okay? So it turns out that the extensions of error I mentioned before are actually the only extensions you can do. Okay? It's just like looking up the kth next row or looking up a constant row. You cannot do anything else if you want to keep the same base proving system. And if you count how many sigmas how many sigmas that amounts to, there's like 2n, and n of which are bijective. What about the multivariate case? You can also like classify them in full generality, but like here an example is much simpler. Here's like an example of a matrix A and vector B that works. And what they do, if you do AX plus B, it just do a permutation of the coordinates. You bit shift some of them, and then some of them you can also set to constant if you want. Okay? And that's actually like all that you can do. Like in all the sigmas that you can do is like basically that, just permuting the coordinates and bit shifting some of them, and if you want, like set some of them to constants. And if you count how many sigmas you get by doing that, you get like these expressions. And then you can see, if you compute how many that is, that it's quite larger than what we got in the univariate case. So in some sense, by going to the multivariate domain, you get like more degrees of freedom in your arithmetization. Cool. Right, so like how does it look in practice? So you've chosen your sigma, you want to do like error on multivariate domains, and then you get something that I call error pods. You have your original table, your n by k table, and your sigma. You don't really know what sigma does, but like you can actually split your table into a bunch of smaller subtables on which sigma acts as a shift. Okay? So all these tables will be, you will get back actually original error. So like in original error, you just have sigma is the shift. So like by using this new sigma, you just get like a bunch of smaller errors. So that's a bad news in some sense because if you want to do like a large sequential computation, you won't be able to do that because the largest table size will be like much smaller. But you can actually use that to do like, in some sense, errors in parallel. Okay? So you just have a bunch of errors of tables in parallel that you can just prove into like one protocol using multivariate polynomials. Great. To conclude, to the best of my knowledge, it's like the first error-like arithmetization that works with multivariate domains. I've only focused on like H and the cube today, but like this can be generalized to domains in between. There's some compromise there, but like it could be like faster. All of this can be generalized to arithmetizations like Planck. Okay? So Planck is basically just error with a permutation argument. So like you can see it's you can very easily extend everything to Planck. None of this requires FFT. Okay? So you can work over any field, including fields that don't have a high two-adicity. And I don't have an implementation yet, but I'm working on it. All right. That's all right for today. I'll take any questions.
Cool. Thank you, William. Are there any questions from the audience?
So hello, thank you for the presentation. As you were talking, I was wondering what the utility of this is, and you earlier mentioned something about parallelization. So what do we get out of something like this?
So I guess it's like, this work is like much more of an exploration of what we can do with error, right? So like error in Planck is like 3 years old now, and it works with univariate polynomials, but like what if you really want to use multivariate polynomials? What if you want to take advantage of the fact that you can work over any fields, right? So I don't know like how it could be used yet, but like let's say you want to, there's like a new polynomial commitment scheme over multivariate polynomials that comes out, and that's like much faster than what's currently available, then you could use this new arithmetization in your protocol. Right?
Okay, dankeschön.
I guess I'll do it.
Have you considered using a higher individual degree and exploring trade-offs in number of variables and degree of a multivariate polynomial?
Can you repeat that, please?
Yeah, so you use multivariate polynomials of degree 1, multilinear polynomials. Have you considered using a bigger degree and reducing the number of variables?
Yeah. So like that's the this second point here. So like yeah, you could actually generalize this to work in between, like kind of like compromise between the degree of the polynomials and the number of variables. Yeah, that's totally doable. And you get like the same kind of linearity constraints.
Thanks.
Are there any last questions? I certainly have one, if there are no more. Okay. Actually, I do have a question. What's the intuition behind only the specific endomorphisms that you allowed? Like, why is that the case? Why can't you generalize to more affine functions?
Yeah. So the thing you need is that f of sigma x, so like if f is a degree n polynomial, or like less than n, you want f of sigma x to still be degree n. And like, so like if you have sigma is x squared, that won't work. So like you need like something like linear or affine to keep like the degree less than n.
Got it. So it needs to be degree conserving, which is exactly why.
Or
bounded.
Yeah, exactly.
Cool. Thank you. Any last burning questions? If not, then I guess we'll continue on to our next speaker. Oh, are we early? Oh, okay. Oh. Do we get to just like party?
Are there more questions?
I mean,
is our speaker here? Who's next? Chris. You want Chris?
All right.
Okay, thanks.
Woo! run at any percent. It'll be great. Don't worry about the completion. It's just about getting to the end. No, I think it's you.
Maybe we just wait.
We should just wait.
Yeah.
Like, whatever.
Chris, what if we start you like 2 minutes early or something? Do you think you're gonna go long? Like, do you
It's just
want
if you want time for
extra
questions.
You could have 5 more. Because we could start maybe in 2 minutes.
Okay.
Just because I know on the program it says you're starting now, and also the other talk downstairs probably isn't done. So you might want to wait.
Yeah.
Let's wait. But then the first time
Well, you could also, cheat this so like you have no questions at the end, and then no one can ask you annoying questions like me.
Yeah.
Just you have to be careful. Yeah, because I do ask annoying questions.
Okay, so generally, if there is for future, I should have told that. If there's like
Time left over.
that we do try to like include questions. I guess there weren't any.
There were like 2 or 3 questions.
I mean,
They're pretty good
that's
actually.
good.
But it's just I think the also the turnout was unfortunately post lunch.
Found. Saw that. Oh, okay. Yeah, I think for me, at lunch, they're gonna have to talk to Polygon. They sent a camera crew to tell us.
Oh.
That's what that was. And like they're filming audience members, and that's not okay. We don't do that here. I told my photographer like no pictures of people in progress ago. I didn't see them.
Yeah, I was like, wow.
It's because that's Polygon. And do we have anyone else from Polygon on the main? I don't know. Oh, Gersha. No, Poly's on there too, but it's like tell us.
Right, it should just be just speakers. That's weird. Okay,
It's
yeah.
weird, 'cause I just kind of gave them a talking to, but they're like, it's not us.
That was cool. Actually, I really did.
I have water. I want more, but it's I'm gonna be too wired.
Don't worry, I'm already pretty wired. I had an espresso shot, I had a coffee, I have this now. I'm just like,
You're wired. Your questions are gonna be on fire.
hell yeah.
There's a danger in using caffeine to try and counter jet lag.
It's true.
Works in ways.
Oh yeah. On Amsterdam, I was like, I certainly had enough caffeine in my bloodstream to like kill a small animal. Like guarantee. It was quite bad. I was like,
Thank God you're not small.
yeah. It was like a 400 milligram a day like regime. I was like, and then I would die at like 8 p.m. And it was fine. It was good. Yeah, exactly. It's not so bad. Yeah. Actually, so I get to cheat though because I'm actually coming from Portugal, so it's actually not so bad. Yeah. Oh yeah, that's right. You're cheating.
Okay.
Must let me know if there's anything sweet. Which I'm sure I have already.
What? No. I'm trying to make sure that people aren't. That was rude. That's some rude.
That is really.
That's like really. It's like in the middle of it. We're like. Well, so the Polygon crew sent a camera crew. They didn't tell us. I said, and the thing is, we don't film audience members on purpose.
Right. That's why I was surprised.
It's like so key, and he was like in front of the guy, and I was like, you can see everybody's face. There's been a rule in Ziki Summit forever. You should have, and like luckily, I didn't say that we don't. Like I usually announce the filming, I didn't, which like gives us a little more leeway, I guess.
But now next time you should say it. It's like if you see anyone filming, you should
Tell them to stop. Anyway, I just told them, and they're like, oh, we didn't know, and I'm like, okay, we didn't know. Like, who didn't tell us or ask us? Rude. Anyway. Sorry. This event planning has been one of the hardest, most fun. It's not anyone's fault. Like, our team did a really good job. It's like, it's tough, and it's super Berlin, and everything's last minute.
Berlin in many ways. Also, is this East Berlin? Oh, West Berlin. Out of curiosity.
Who?
I thought Alexanderplatz was East Berlin.
Thing.
This is what?
No, wait. Well, it's weird because Alexanderplatz was east, but it like cut. Kreuzberg across the river is west. What is here?
We are on
Mitte.
that side of the river.
East.
We are on
I think
east
it's
side of the river.
We
Is
could
that-
we
is that
could
what
find the
divides
map.
Is the river what divides east west? I actually have no idea. I've never been here.
Okay, we should.
So.
I think we're 2 minutes to go. I think we can probably do the intro. People are arriving, so.
Oh, perfect. All right.
I thought it was funny.
I realized that no one actually saw the talk title because none of us going to be out there.
Yeah, no. Oh, so it didn't make any sense.
Yeah, yeah. So it might not have made any sense unless you like already knew what the talk was.
AirPods must be like a registered trademark.
Yeah, it's possible.
Sure, yeah.
I did
But
tweet
it's
it.
fine. You can put it
Is
in
Henrik
the
there?
paper. It's
Hey,
fine.
Rachel, can you just get Henrik ready? I want to do it.
Especially if you use a funny capitalization.
I like this little.
Yeah,
it's very tidy.
I stole your idea actually.
Little tidy little.
Oh, I'm introducing Benedict. Wow.
Yeah.
Then I'm introducing.
Hello. Hey. Hey, Henrik. Are we all set? Great. Okay. So next up, we are going to be inviting Christopher Goes from Anoma to the stage to talk about Namada, sorry, asset agnostic interchain privacy. So welcome, Chris. Let's give him a hand.
Thank you. According to the schedule, at least lunch is directly after this talk. So now is a good time to sit back, enjoy, let your brain process a little bit of cryptography and prepare for lunch. And if you're really tired, lunch is coming soon. If you're standing out there talking, you could sit here and then you could go to lunch. It would be a good prep. Okay, I'm Christopher. I work on Anoma, confusingly because this talk is about something else, obviously, called Namada. We name all of our products different things and give them different color schemes, to be determined whether this is the correct strategy. But it is on purpose. And this talk, in contrast to many things here today, which have touched upon what you might call like new, shining, cutting edge, as in both it's new and shiny and it might actually cut you if you use it improperly, cryptography. Namada is about old and boring cryptography, except that old and boring in blockchain time means like 2 years, so not really old in other sorts of cryptographic time. But Namada is... here I'm going to refer to an excellent blog post by, I think, Moxie Marlinspike, the original creator of Signal, which talks about how in order to craft products which actually protects users' privacy in practice, you need to strike a really nice synthesis between designing the cryptographic scheme and thinking about the user experience. And you need to think about those both at once. Because if you don't think about them at once, you're going to end up with fancy cryptography that nobody uses, or you're going to end up with something usable that doesn't provide any privacy. And Namada, it's easier to do that when you use things which have been around for a little bit longer and think about a very particular product. So Namada is our effort to do that for interchain privacy. Now, let me explain what that is. But first, let me give credit. Namada is built mostly by people who are not me at Heliax, and you can see very small pictures of, I think, almost all of them here. But particularly you can find Awa and Adrian and myself, who are larger, not because we are more important, but because we are here, at least, so you can find us. And please ask us any questions. Heliax also does a lot of other stuff, and we're happy to talk about that as well. So I'm only going to spend one slide on this because I think it's preaching to the choir. But why does privacy matter? Why might you want to care about it or spend time designing systems which are private? I think there are more reasons than just protecting individual. Privacy is not only individual, it's also social, and perhaps sometimes the individual aspect is overemphasized. Particularly, privacy is important for national and community defense, for defending against kinds of propaganda, which really rely on the ability to collect a lot of data. Privacy is important, of course, for the protection of individual rights. That's probably the most common argument. I think it's important to protect against not only violations of sort of civil rights, but also surveillance capitalism leading to a kind of profit-driven nudging or mass propaganda, which doesn't in the individual instance necessarily seem so egregious, but can have pretty bad impacts over time. And last, but certainly not exclusively, at least, privacy is kind of the historical default. It's easy to forget that until recently, we didn't live in a world with nation states and great amounts of surveillance. And if you took someone from 50 years ago and plopped them in today, they would find this all very strange and wonder why we haven't overthrown our governments. And I've got to agree with them, to be honest. But okay, so probably you're already convinced, and I don't need to convince you anyways. Let's talk a little bit about what choices would you have as a user if you wanted to get privacy today in blockchains? And of course, many of the things people have talked about today offer additional options that aren't on this slide. The slide only includes things that are live and in production. So far, users have had the choice of really two kinds of privacy options looking at the interchain landscape. They've had the choice of a sovereign chain which reissues assets. Of course, first to the space and really the pioneer of zero-knowledge proofs in this distributed systems context at all was the Zcash project, then Ironfish, and some like Ycash, forks of Zcash, other kinds of sovereign chains based as Zcash was on the Bitcoin monetary policy and sort of single asset, single blockchain mentality, issue their own assets. And at least at the moment, the only asset supported on Zcash, Ironfish, Ycash, these other chains is the native asset. So if you want to, you can achieve full transactional privacy using these systems, but somehow you have to get the native asset ZEC in the case of Zcash, and you have to use it. And that is, comes with some trade-offs, which I'll discuss in a second. The other options available are privacy-preserving solutions which are built on some smart contract chain. So Tornado Cash, Aztec, there's some others on Ethereum which offer usually not quite as good privacy as Zcash, mostly due to gas costs and just the difficulty of constructing these circuits and interoperating with the curves supported by Ethereum, but much better privacy than you would get using public Ethereum. But both of these options come with trade-offs. So if you, as a user, choose to use a sovereign chain which reissues assets, you have to use the asset. And often the asset is not the one that you want to use. Like, this is not a super complicated argument. In particular, the economic properties of Bitcoin, while interesting, are just awful for spending money. Usually you don't want to hold a very volatile asset. Deflationary monetary policy is an interesting economic experiment, but it's really like, it's not necessarily going to be correlated at all to the cases or scenarios or sort of everyday contexts in which you as a user want privacy in particular. And like transactional contexts, often you want privacy for payments or privacy for things that you're doing other than holding the asset. And this monetary policy is not really well suited to that. Privacy solutions on smart contracts chains are generally much more flexible with regards to which assets you can use, but they tend to offer less privacy than Zcash. They are more expensive, at least on average at the moment. And as we've seen recently, they're somewhat more vulnerable to censorship, both perhaps because there are real reasons they're more vulnerable to censorship, like the costs of censoring and the ability of, say, Ethereum block producers to deep censor Tornado Cash transactions are kind of, it's easier to do that. And also, I think the optics of smart contract privacy solutions, as opposed to baking privacy into a full system by default, make it sort of more likely to be censored based on the way these systems are understood at the moment. So what do users want? We postulate that users want simple, understandable privacy. They want it for any asset, most notably the asset they want to use, but we don't really know what that is. As systems designers, they want it to be fast and cheap and strong security guarantees. Users want everything. Of course they do. And then the final piece of this kind of puzzle of trying to sketch what the design problem is that users nowadays live on the interchain, which is this sort of ephemeral space of a lot of blockchains connected in a lot of different complicated ways with a lot of assets. It's all very heterogeneous, but users live there, so we have to go there. Users are going to use many assets. They're going to use them across many chains and many applications, and most relevantly with regards to how we design private systems, users are going to interact with those assets across those chains kind of like auto-magically, by which I mean there will be, of course, systems of bridges and messaging protocols mediating all of these interactions. There's a specific way in which it happens in practice, but users are not necessarily going to understand it all of the time. They are going to click buttons and deposit into bridges and send funds, and they're going to have an asset because they know assets, and they're going to want it in a place like an application place on another chain because they know applications, and they are going to click the buttons that gets their asset there. And a user is not going to think every single step of the way on like what bridges are my assets being sent through? Do I lose privacy sometimes? What are the complex implications of this whole imperative execution chain? Users are just going to kind of click buttons and their assets will move. So we need to design for this world. If we want to provide privacy to users, we need to expect that they will not understand all of the functional details of how these systems work. Yeah, and adversaries are going to be smart, and they will target the weakest link. The weakest link is probably not, your cryptography assumptions. They would be great if it was. Eventually, hopefully, we get to that world. The weakest link is going to be a bridge. It's going to be an implementation bug. It's going to be like the query system by which users are fetching state. The adversaries are going to go after the weakest link. And the time to head off a future surveillance, as long as we're not already too late, is now. Okay, so this is what Namada is trying to do. Namada is trying to provide privacy to users in this interchain world, making these kind of very rough assumptions about how those users behave. And Namada has 3 phases of deployment, which I will outline in the rest of these slides, focusing mostly on the first. The first is a sovereign chain that provides asset-agnostic privacy. The second, sort of codenamed privacy-like company, adds a lot of bridges to interoperate with other systems. And the third, hint, hint, makes those bridges private because that makes privacy win-win. And later I will explain why. So let's go to the first phase first. Phase 1 is simply a blockchain that provides asset-agnostic privacy. Most of this is, old in the sense of like a year or two old, so old in blockchain terms. Namada is built on top of Tendermint consensus. We use we use an unreleased Tendermint version, but we will be using Tendermint with ABCI Plus, which is not ABCI++, but soon it will be. Marco's going to kill me. I'm sorry, Marco. Tendermint's amazing. It has so many ABCI versions that we can choose exactly the one we want. Namada features both cubic slashing and a trust-minimized Ethereum bridge, which I'll talk about briefly, but mostly I will talk about how we do multi-asset private transfers and how we crafted an incentive scheme to treat privacy as a public good and why. First, multi-asset private transfers. So Namada features something called the multi-asset shielded pool. The multi-asset shielded pool allows users to do kind of exactly what it sounds like, which is send money privately using any asset. In particular, the multi-asset shielded pool allows us to provide a shared privacy set for all fungible and non-fungible assets, just tokens. And it has small and efficient proofs, keys for optional disclosure. It's available on the internet. I know you can't. I considered making the links like the full thing, but then it was just super long. So you can find the slides online and click the links. It really is online. It's not fake. But the basic idea of the MASP is to provide one large shielded pool for everything so that when an observer looks at the blockchain, they have no idea what asset you were using. And even anyone validating Namada has no idea what asset you were using, so it's quite difficult to censor. How do we do that? Well, basically, a way of summarizing how the multi-asset shielded pool mechanism works is it's like multi-asset privacy with just one weird sort of cryptography trick. The MASP starts from, as I said, old crypto, quote unquote, the sapling circuit. All of the really hard work in the sapling circuit was done by the electric coin company. For some reason I wanted to call it the elliptic curve company. I wonder if that was intentional. Okay, the elliptic curve company, also known as the electric coin company, they did like all of the real work. We just kind of modified it a bit. So all credit to Dara and Strad and some of the amazing circuit designers at ECC. The MASP works by adding an asset type to each note, calculating an independent value base for each asset type, and that is surprisingly enough. So let me explain why. Let's go back to sapling. I know sapling's old. Do some people remember sapling? Who remembers sapling? If you've used Zcash in the past few years, you've probably used sapling, either slightly in the past or to turnstile your assets. So sapling in 2 slides. First slide, notes. Value in sapling is stored in notes, so it's like the UTXO model. And notes in sapling consist of 4 elements. You can think of notes as a tuple with 4 elements. The first element and second element are the diversifier of the recipient's shielded payment address and the diversified transmission key of the recipient's shielded payment address. So these are just to specify who can spend the note. V is the value of the note, just a integer. And RCM is a random commitment trapdoor. So we see here that there is no specification of what asset because sapling only supports one asset, Zcash or a SEC. How do we check that a transaction balances? So sapling uses this cute balance check based on homomorphic Peterson commitments. And the cool thing about homomorphic Peterson commitments is that they are homomorphic. So you can do this. You compute commitments, value commitments for each. There are 2, you see here there are 4 notes involved. So these are 2 spends and 2 outputs. And you compute value commitments using something called gZAC, which is the value base for ZAC, which just in the sapling protocol is just a constant. Then V1, V2, V3, V4, those are the specific values involved in your transaction. and R1, R2, R3, R4, along with a value commitment randomness base. Those are randomness, like trapdoors. So using this, you can use this to compute the value commitments, and then this, the second check actually happens in public because these are like homomorphic, so they don't reveal your values. You check that when you sum the spends and subtract the outputs and subtract the value balance, the transparent difference. So if you're like shielding or unshielding, value balance is non-zero. You check that that's equal to h raised to the binding secret key. So this, because these commitments are homomorphic, holds if and only if your values actually balance, which means that the sum of your spends less your outputs is equal to the difference in transparent value change, and you actually like knew the randomness. So we can modify this by just adding new value bases. The first way we do this, so the first thing we want to do in the MASP is to add an asset type. And this is quite simple. Just take our 4-tuple note all the way back from the original sapling and add. We're actually gonna create 3 things here because we need to do some user-friendly derivations. So we first start out with the asset name. And the asset name you can think of as like Bitcoin or Ethereum or like my fun penguin token. The asset name is the thing users are going to know and refer to the asset by. From the asset name, using, it doesn't really matter from the circuit's perspective, but using a hash function, we can derive the asset identifier, which is a 32-byte string, so a fixed-length string that uniquely identifies the asset. A slight caveat to this, or just a new point to note, which I'll explain in another slide, is that the asset identifier, not every 32-byte string is a valid asset identifier. We want it to be a valid, we want it to be a Blake 2S preimage of a valid asset generator, so we use some simple rejection sampling to derive asset identifiers from asset names. And this just like simplifies our life, otherwise it would be more annoying. The asset generator is a valid Twisted-Edwards curve point on JubJub, and that's what we actually use as the value base. So if we go back here to this balance check and sapling, you see that thing gzec. That's the value base for zec, and it's just a constant. And the only thing we're really changing in the MASP is that we're computing that value base now kind of dynamically, and we're computing separate independent value bases for different assets. So how do we do that? We take the asset name and we derive deterministically some asset identifier that needs to be valid. And for it to be valid, we need the Blake 2S image of the asset identifier to be a valid Twisted-Edwards curve point. And there are actually 3 ways that can fail. So what are they? 1, it could be a small order point. This is very unlikely, but we still need to test for it. 2, it could be an integer, which is at least the order of the underlying field, which you would think we could take modulo the order, but the problem is that that's not uniformly random, and we want it for security property reasons to be uniformly random. So we reject those, and we reject when there's just like no point with the given y coordinate, which happens approximately, but not exactly 50% of the time. And just iterate a nonce until the asset identifier is valid. So using that method, we can derive from an asset name, which is going to be like tracked in the protocol. There'll be some registry of assets. We can derive asset identifiers that correspond to valid asset generators. Any questions on this so far? Cool. So now we modify the balance check, and the only thing we're doing is we're just using our additional value bases. So here, instead of gzec, we have GA1 and GA2. Those are the value bases for asset 1 and asset 2. We compute the input and output commitments as before, just using these different value bases. And we, the only thing we do to modify the balance check is that we add, there can now be VB1 and VB2 are transparent changes in asset 1 and asset 2. And as many assets as you have, there can be that many transparent balance changes. Of course, we can like look at what the 0 ones we don't need to bother computing. But because the value bases are independent and we still have homomorphic Peterson commitments, this holds only if the assets balance independently. So if I have 5x and 5y and spend to create 5x and 5y, this first v1 minus v3 will check that like 5x equals 5x, and the second v2 minus v4 will check that 5y equals 5y, which is the property we want. We want to check the balances are independently conserved. And the basic security property here is that assuming the elliptic curve discrete logarithm problem is hard, provers cannot obtain a relationship between these generators. So we have like the kind of regular security here. And as a result, we get multi-asset privacy. Multi-asset shielded pool transactions can include spends of any number of assets. The observers cannot, including the validators of Namada, cannot distinguish which assets are involved, and we retain all of the great benefits of sapling, viewing key, key derivation, etc. But let's go back to our users. And our users are lazy, and they are strategic, and they want to do things which are cheap, and they want to only pay for something like privacy when they need it. So we can think about privacy as a public good in the following way. For most transactions, users probably don't care about privacy, or if they like consciously reflect on it, you know, do I really need privacy for buying coffee? I mean, am I going to get prosecuted for buying coffee in this specific instance? Probably the answer is no. And if I have to pay for this, you know, I'm only really going to pay for privacy, or if I have to go through extra trouble to get private transactions, I'm only going to do that when I have some strong reason to do that. Because the private benefit for me of transacting privately is, you know, low or kind of negligible or hard to think about except in specific cases. But there's a public benefit to my transacting privately, which is that even if I don't care about, you know, whether this specific transaction of buying coffee is private, when I choose to do that transaction privately instead of publicly, other people get a larger shielded set. So there's this public benefit. And for this reason, we think that this public benefit of privacy should be somehow captured in the incentive design of private systems. Because when a user makes this choice, we want them to, you know, if they are giving benefits to other people by transacting privately, even if they don't receive private benefits for doing it, and if we can find some way to send a little bit of that flow, of that value that other people are getting back to the individual, then we have a system which is better incentive aligned as a whole, and people will have more privacy. So for this reason, we made another circuit. Traditional to Namada's tactic of taking the sapling circuit and modifying it in the minimum amount of ways possible. This is a separate circuit, but it kind of interoperates very cleanly with sapling, and I will explain how. So the basic idea here is that for designing incentives for private transactions is actually really hard for some pretty fundamental reasons. There are kinds of, you have to balance between wanting to design an incentive mechanism that gives people a reason to transact privately and not suddenly making yourself vulnerable to denial of service and not incentivizing garbage, because the thing you want to incentivize is like real transactions being private, and the protocol has no idea what a real transaction is. So it's like there's some fundamental impossibility there. But what you can do, which is slightly more limited, is incentivize value at rest being private, which means that if people keep value in the shielded pool, they can accrue some incentives. And if people sort of transact, you know, there's a layer of indirection here, but if people are transacting privately by default and keeping their value in the shielded pool as a virtue of that, they will receive incentives for this. So we built a circuit called a convert circuit, which just does that. It distributes rewards proportional to the amount of a particular asset, and the length that amount has been in the shielded pool multiplied by some proportionality constant for the asset. This works by, actually, it works by making assets non-fungible. But because we're in the shielded pool, we're okay with this because it doesn't entail loss of privacy. So basically, we tag, in our system, we have quantized time, but it doesn't matter. You could also do this without it. We have proof of stake epochs, say once a day, and we tag assets with an epoch. So instead of it being like, you know, X coin, it will be X coin epoch 1, X coin epoch 2. Users can use the convert circuit to upgrade their assets to the latest epoch, and when they do that, they can claim some rewards. So what this means is that assets earn a kind of, I'm not sure about this term. We're going to have to think about it. Yield is dangerous word. But assets earn a sort of privacy yield over time, which differs from DeFi yield in that it is risk-free. You're not like taking AMM, impermanent loss risk, or something else. It's just a subsidy for providing privacy for other users as a virtue of holding value at rest. And it's important to note that this is not, I mean, there are multiple kinds of privacy. So if you think about the zero cash style, Zcash style, and MASP style transaction models, you might care about privacy in terms of what inputs could your transaction potentially have come from. And this incentive mechanism is very good for that because it incentivizes value at rest, and value at rest corresponds pretty directly to potential inputs which your transaction could have come from. But you might also care about privacy, like how many people sent transactions within this 10-minute time window, and given that I sent a transaction, how big is my anonymity set there? This cannot be incentivized. So we can't provide that except indirectly by this incentive mechanism giving users a reason to have more transactions just be private in general. I can repeat the question. The question was, before I go on, can I explain what users upgrade assets to the latest epoch and claim rewards means? Yes. Can you give me one slide in between? Thank you. So how do we do this? I promise we'll explain it. We made the circuit called a convert circuit. The convert circuit does another magic trick with homomorphic Peterson commitments. It's the same magic trick, we just do more of it, actually, that allows minting and burning of assets according to fixed and public ratios. So the MASP alone, if you recall to the balance check earlier, just checks that the homomorphic value balance is 0. But the MASP with the convert circuit checks that either the homomorphic value balance is 0 or that it is an allowed non-zero conversion. How do we do this? So the convert circuit is very simple. It takes an allowed conversion is just defined as a list of tuples of some asset and integer. And these can be negative, so you might take one asset and convert it to another asset. Then the first would be negative, the second positive. The convert circuit takes a public input of a Merkle root and the value commitment that you want to prove is valid. It takes a private input of path and position, which are just inputs to the Merkle proof, the conversion commitment, value commitment, and some randomness trapdoors, and checks that the commitment that you're using is a valid commitment inside the Merkle tree. So why do we need a circuit at all? The reason why we need a circuit at all is because we don't want to reveal what conversion you're using. If we revealed what conversion you're using, it would reveal which assets are involved in the transaction, and that's the thing we wanted to make private. But all this allows you to do is change the balance check. So now we get to add this term to the balance check. So if you recall back to the multi-asset shielded pool balance check, we just had these value commitment in minus value commitment out, and here I omitted the transparent balance change equals 0. With the convert circuit, now we check that the value commitment in plus this new term, this value commitment convert, minus the value commitment out is equal to 0. So this means that the difference here can be, because we have the CB convert term, and CB convert can be a valid value commitment for any conversion which is in the Merkle tree, which we just proved with the convert circuit. This means that the difference is allowed to be a multiple of an allowed conversion. And because, again, these are homomorphic commitments, we can check this while preserving privacy of the assets involved and which conversion, relatedly, which conversion was used. So let me explain a little bit more about the epoch mechanism. So the idea here is that when I, as a user, deposit assets into the shielded pool, those are going to get, you can think of them as getting tagged with the epoch. So I have Chris coin, right? Who wants to accept Chris coin? I have Chris coin. And I deposit Chris coin into the shielded pool. The current epoch is 10. So this now becomes Chris coin 10. And Chris coin 10, if someone deposits Chris coin tomorrow, that will become Chris coin 11. So these are seemingly seem to be non-fungible assets, which is weird. But because we have this MASP, we already have asset privacy, so you're not really losing any privacy by doing this. You're just always converting to the current epoch. Then in this convert circuit, or in this conversion Merkle tree, we add tuples. And these tuples allow you to convert assets of past epochs to assets of the current epoch. And they might, if you're lucky, allow you to claim some additional asset. So particularly in Nemata, we have a native asset called NAM, and NAM can be minted as, via some calculation, as rewards for keeping assets locked in the shielded pool. We do this with PD controllers, which I'm going to skip because I don't have enough time, but it's like EIP 1559++, just with an additional D term. So as a user, I can convert from assets of some old epoch to assets of the current epoch, and I can claim some rewards. And this can be mostly abstracted away from users. When you withdraw from the shielded pool, you'll always convert asset of the current epoch to just the regular asset. So it's as if you were using something without this epoch tagging. The epoch tagging is a pretty, invisible mechanism to allow these rewards to be calculated. So phase one, asset agnostic privacy chain. I'm going to skip these 2 slides, sorry. Phase two is adding bridges to other privacy ecosystems. Why? Privacy loves company. We actually put together a proposal for a bridge to Zcash. You can find it on the Zcash community forums. We might build a bridge to Alio unless someone else does, in which case we don't need to. Penumbra thankfully uses IBC, so all of our work is done for us. And the important part here is starting to think about privacy as a promise to users. So, safe use of technology is conditioned not only on the cryptographic capabilities of the underlying protocol, but also on users understanding how it works and what kind of privacy they get. And I think it would be good if we start thinking about like a wallet that only supports chains which offer this like strong privacy model, right? Because that's a credible promise you can offer to users. But now in this world of separate privacy chains, we live on privacy islands. And you can admit you've also done it once. I looked up, okay, are there private islands in the world? Can I like get a private island? And there are all these advertisements for like private islands in the Bermudas. And I thought about it, and I think these people don't understand what privacy means, because if you were the only person who owns an island and I have satellite photos, you have an anonymity set of 1, right? So privacy islands kind of suck, and they also suck in this case because private islands mean that we're competing on privacy. If you lose privacy whenever you move between islands, then if I use your chain instead of some other chain, you get more privacy, but the other chain and users of the other chain get less privacy. So these private islands have to compete for users to maximize the privacy they can offer, which is sad. So in phase 3 of Namada, we're trying to make privacy win-win, and we just do that with private bridges. How do private bridges work? Well, in principle, it sounds very simple. You just keep the transfers over bridges private. If you have a zero cash style note model, you could just like send the notes over IBC or something. And this allows all chains to share a privacy set, which means that if I use one private chain, which is connected to another private chain, both of their anonymity sets increase, which is great. The one small snag we hit here is fault isolation. So let's go back into IBC security very quickly. To explain what this means. So IBC provides very strong fault isolation because it was designed by paranoid people. And so far this has not been necessary, but IBC is designed for a world where not only validators, but also whole blockchains are Byzantine. And this design allows us to provide permissionless interoperability, which is otherwise very hard. Fault isolation in IBC works via something called balance tracking, which is exactly what it sounds like, which means that each chain tracks balances of other chains. When I send from chain A to chain B using IBC, chain A tracks which assets have been sent to chain B, and when chain B sends them back, chain A makes sure that chain B is not trying to send back more assets than it was originally sent in the first place. So this requires metering of how many assets are flowing from one chain to another. Privacy, of course, seems like it will just break this, because if you want to provide privacy on amounts and assets, then how can you meter which amounts of which assets are going to the other chain? And without fault isolation, at least in the long term, bridges just probably won't work because there will be Byzantine chains. So what do? We add more cryptography. Simple way of doing that is that we keep an encrypted counter for chain balances, and we increment and decrement the encrypted counter in the standard ICS-20 as a reference to the IBC cross-chain transfer spec. We increment and decrement the counter in the standard ICS-20 fashion. And then we somehow make sure that we can test that it is non-negative when we send back from B to A. And to somehow here, the third bullet point is the part that's like actually hard. And we're currently trialing a few protocol designs, one based on MPC and some threshold decryption, to do this non-negative test as efficiently as possible. The great part about this design, it requires some fancy cryptography, but it gives you both things that you want in all of the ways that you want them. You retain full privacy, and you retain the full IBC standard fault isolation. So we actually do have a draft protocol for this on HackMD. I think you can find it if you click that link in the slides. Okay, very quick shout out. There's a Namada, I have 1 minute left. There's a Namada trusted setup. It's happening like very soon, in a few weeks. Please participate in it. It would be super helpful. And hopefully phase 1 will launch later in the fall. Thank you. And I probably don't have time for questions, but thank you very much.
Is that a Nemata shirt, by the way? That's really cool. I think I want one. All right, I think that's it for the morning program. We have lunch downstairs. Please go enjoy it, and we're back here in an hour. So see you there. Thanks again. Hello. Hey, everyone. Welcome back. I see you're coming down the hall to the main stage. So before we just start this, I want to let you know that in the breakout room, in the club, you might have seen that sort of club place, there will be some music over the next hour and a half from Justin, who played last time at the summit. He sings about ZKPs and stuff. So you might want to check it out. It's really cool. But yeah, we have a new speaker.
I'll steal this one. Is this one? All right. And we have another speaker, Benedict Bunce from Espresso Systems, who will present to us Hyperplonk, linear time and parallelizable Plonk with custom gates. Welcome, Benedict. Actually, quite early welcome, in fact.
Yeah. Do I get a mic? Or?
Yep.
The slides?
Hello?
No.
Oh. All right.
You have the right slides.
Ooh.
I mean, we could do PowerPoint karaoke, and I'll talk about... Yeah, that looks more like it.
There we go.
Cool. Thank you very much. Yeah. Thanks, everybody, for coming. I'm competing now with a real party downstairs, apparently, so that will make it harder to get attendance. But yeah, thanks, everybody, for coming. And I'm going to talk today about something brand new that we haven't talked about before. So maybe the slides are a little bit rougher, but it's, you're seeing something for the very first time, which is Hyperplonk, which is a new zero-knowledge proof system, which, as the name suggests, is based on Plonk, but has some really exciting properties, removes the need for something called fast Fourier transform, and enables high-degree gates, which is especially going to make it more useful for large parallelism and trying to prove things about really, really large statements. And this is joint work with Binyi Chen, Dan Bonet from Stanford, and Zhenfei Zhang from also Espresso Systems. And yeah, this is work that we did at Espresso Systems. Okay. Does this work? Okay, cool. So what is Hyperplonk? Hyperplonk is a new polynomial IOP, which is a key component. I'll talk a little bit in a second about what polynomial IOPs are, but it can be combined with any sort of polynomial commitment scheme. So KZG's polynomial commitment scheme, something like bulletproofs, something FRI-based, and if you combine them, you get a new different SNARK. And depending on what polynomial commitment scheme you use, you get different properties for the SNARK. And it is Plonk-based, but instead of Plonk uses univariate, the big difference is that Plonk uses univariate polynomials and encodes things over a subgroup, versus we use multilinear, so-called multilinear polynomials, and Hyperplonk is based over the so-called Boolean hypercube, which is where the name comes from. I'll explain all of these things in more details, but this is just the overview of the features. And one thing that we made ensure that one of the reasons why we built Hyperplonk is because we wanted to have all of the nice features of Plonk, such as custom gates and Plookup. I think this is TurboPlonk and UltraPlonk. If I get the order wrong, I'm really sorry. Also Halo 2 arithmetization, but all of the cool features and the tooling that has developed around the Plonk proof system, which has been really rapidly adopted, are things that we wanted to maintain. But additionally, we wanted to remove the need for these FFTs. And the reason is that these FFTs, they basically become a bottleneck if you're trying to use a lot of parallelism or if you're trying to use prove really, really large instances. They have so-called superlinear scaling, and we wanted to remove the need for that, and that is exactly what we did. Additionally, we support really not just normal custom gates, but more complicated custom gates, so-called high-degree custom gates. In particular, if you, unlike in Plonk, if you have a custom gate and you make it too large, you basically pay for it in terms of group operations. And in Hyperplonk, you only need to, the higher degree or the more complicated your custom gate becomes, you still have to pay for it, but you pay for it in so-called field operations, which are much, much cheaper than group operations. So in effect, this allows you to use more complicated custom gates. And the proof size is a little bit larger than Plonk. So it is, Plonk is, maybe less than a kilobyte. It's definitely less than a kilobyte. And for Plonk, for hyperplonk, the proof size is about 4 log n plus some constant, and roughly it's like less than 4 kilobytes if your proof is about 1 million constraints. So what are these? Plonk is a poly-IOP, or PIOP. What is a polynomial IOP? Well, to understand that, we need to understand how a lot of these modern SNARKs are built. And they're basically built from 2 ingredients. One of them is this polynomial IOP, and the other one is a polynomial commitment scheme. And this gives you a ZK SNARK. And this really general paradigm, so instances of polynomial IOPs are Plonk, Sonic, Marlin, Libra. And instances of polynomial commitment schemes are things like KZG. You can build one from bulletproofs. There's Fry-based commitment schemes, Dark, and so on and so forth. And the really cool thing about this general paradigm for constructing SNARKs is that you can essentially take any of the things from the left side and any of the things from the right side and get a new SNARK. And the properties are sort of the combined properties of both of these things. And this talk will focus on the left side on these polynomial IOPs. So what we're doing in a polynomial IOP, if you think about it, what you want to think about is that we have some arithmetic circuit. So this is a circuit that consists of, say, addition and multiplication gates, and maybe some additional gates that we'll talk about later. And the proof system wants to show that the circuit is satisfiable. What this means is that given some public inputs x, there exists, we want to prove that there exists some private witnesses W such that the circuit, the final gate of the circuit is equal to 0, for example. And the way that we do that is using this polynomial IOP. And in the polynomial IOP, the prover sends some commitment, sends in every round some polynomial or some polynomials. In the simplified version, there's only one. And then the verifier sends back some challenges. And you do this for multiple rounds. And then at the end, the verifier can check the proof system by evaluating the polynomials at a few points. So this proof system is, we can design this proof system, and hyperplonk is such a proof system. But by itself, it's not very efficient because these polynomials may be large. And what we then do to make this into a SNARK is that instead of sending the polynomials, you send a polynomial commitment. Instead, the verifier evaluating the polynomials directly, it will evaluate, or it will receive a proof. The prover will basically assist the verifier. So the prover will claim that the polynomial has some correct value and then give a sort of an evaluation proof that this polynomial was evaluated correctly. But the question that we're concerned with today is how do we design these polynomial IOPs? And the properties that we want from the polynomial IOPs are kind of standard properties that we have in SNARKs. So completeness means that an honest prover can convince an honest verifier. Knowledge soundness means that if a prover constructs a convincing proof, then he must have known a witness. So formally, you can, or a little bit more formally, it means you can extract a witness. And then optionally, something that I will not talk a lot today about is zero knowledge. So zero knowledge means that the proof itself reveals no information about the witness. And the resulting SNARK of this compilation basically depends on depends mainly on the number of polynomials that we send and the number of queries that we make to these polynomials. And I'll skip over this a little bit, but the important thing is that kind of the cryptographic assumption that you use, so whether this proof, for example, is post-quantum secure or whether it requires pairings, that only depends on the polynomial commitment scheme we use. So if you use Fry, you get something that is plausibly post-quantum resistant. If you use pairings, you get something that require. If you use KZG, you get something that requires pairings, but maybe has a shorter proof size. The poly-IOP, though, is really the way that we encode the circuit. So it defines really also how we think about our computation. And to start out, I want to talk about how, a little bit at a high level, how Plonk works. So in Plonk, we start with some circuit that has addition and multiplication gates. And there's some public inputs X to the circuit and some private inputs W. And it turns out that you can represent the circuit always as a multivariate polynomial of all of the inputs and witnesses. And the question is that we want to, and if we have some private, some inputs, so 5, 6, and 1, then we can simply evaluate the circuit by going down the wires. So, for example, this last wire is 11 times 7 is 77. And then the circuit would basically prove that, that there exists a private input such that this output evaluates to 77. And what Plonk does is it takes the circuit and it looks at the computation trace. So it looks at the trace of all of these gates and writes basically a row per gate. So it has some inputs and a claimed output, and then we repeat the inputs as the gate 0, and additionally with the witness, and then we write every single gate here, and the first line is the left input to the gate, the second line is the right input to the gate, and the third line is the output of the gate. So, for example, gate 1 is an addition gate, so 6 plus 1 is equal to 7. And the final thing, the bottom right corner, is the output of the circuit. So what Plonk does is it encodes the circuit, this computation trace, as a polynomial. So what we do is we take some polynomial that and interpolate it to be the entire computation trace. So let's see how this works. So what we do is we have some values w, and these values w need to have some specific structure, but that's not as, w omega, it's Greek letters. So we take these values omega to the power of j for j or L from 0 to the size of the circuit. And what we do is always we make sure that the 3 neighboring values always represent one row. So w to the 3L would represent, for example, the value 6 here. W3L plus 1 would be 1, and W3L plus 2 is 7. So the neighboring values always represent one of the rows of the polynomial. So, and to do this, to interpolate this polynomial, the prover has to use something called an FFT, a fast Fourier transform, to do this. And this takes d log d time, which in practice this is not a problem if d is small, or n, actually n log n time. In practice, it's not a problem if n is small, but it does actually become a bottleneck if n gets large, and this is what we're going to try to get rid of. So in our example, this is what, for example, this encoding would look like, and the number of points that you encode exactly corresponds to the degree of the polynomial. So the degree in this case is, I guess, 11. So the 10,000 feet or 3,048 meter view of how this proof system works is that the prover encodes the correct. We need to prove 4 different things. The first thing that we need to show then, given this polynomial with the PRP, is that the prover encodes the correct inputs. So that the first row, that these inputs correspond to 5, 6, and 1. The second thing is that every gate is evaluated correctly. So that, for example, here, this is a correct addition gate, that 6 plus 1 is equal to 7. The third thing is that the wiring is correct. So you see that a lot of values here are repeated. So for example, this input on the right side is the same as the left input on here, and you need to actually prove that that is done correctly. And then finally, the last thing is just that the output is whatever the prover, whatever we think it should be. So that the output here, 77, is actually 77. So the way to do that is like this. It's a complicated, or it's actually not that complicated, but it uses many different subprotocols. And if you want to understand it, you have to understand the subprotocols, which then build up to the full protocol. And then there's also ultra-prong, which does something called lookups, which I'm not going to talk about today. But the things that I want to focus on a little bit, because they become important in Hyperplonk, are these 3 components: the quotient check, the zero check, and the circuit check. And they're very, very related to each other. So how do I prove that? I want to prove this second component. I want to prove that every gate is evaluated correctly. So this is the so-called circuit check. So the way that I do that is by having this selector polynomial, which is either 0 or 1. And it's 1 if I have an addition gate, and it's 0 if I have a multiplication gate. And the way that Planck proves that the circuit is evaluated correctly is by saying that, well, either I have an addition gate, so then py plus pw times y is equal to pw squared times y, or I have a multiplication gate, then py times pw omega times y is equal to p omega squared y. And the selector basically is 1 if it's an addition gate here, or it's 0 if it's a multiplication gate. So only this part will be active, or this part will be active. And this is too complicated. Don't worry about it. We'll go a little bit higher level soon. But basically the way that I prove this is I basically need to prove this equation here at every single point for every single value of omega, for every single value of omega in this kind of subspace. And this is called, we can think of this abstractly as saying there's some polynomial f, and we need to prove that it's 0 over a bunch of different things. So this is the so-called zero check. And the way that we do that is by showing that by doing a so-called quotient check. Again, we don't need to worry about the details here. But all of this, to make this work, we have to look at this polynomial f as a univariate polynomial. And in particular, we have to construct this polynomial f or p. And the way that we do that is an FFT. So this is a fast Fourier transform. And this has some downside. I already mentioned that it runs in time n log n. So it's not linear in n, it's super linear. So for example, if n is like 25, then this grows by, there's an extra factor of 25 that you're paying here. It additionally requires a so-called FFT-friendly field, which restricts our choices of fields and makes things less nice. And also, it has a bunch of memory accesses. To actually implement this, there's a bunch of complex memory accesses, and it's really hard to parallelize, or it's difficult to parallelize beyond a certain point. And all of these things make it really... It's okay if n is not that big, like if n is like, I don't know, 2 to the 15 or like 10,000, then this is not a problem. But once n gets large, and especially if you use parallelism, then this becomes a big bottleneck, and especially becomes a bottleneck if you're trying to implement things, say, on a GPU. So in Hyperplonk, we want to get rid of this FFT. This is the main goal. We want to get rid of this FFT. So instead of interpolating, so our idea is that instead of using this subspace of some field and using high-degree polynomials, we're going to use so-called multivariate polynomials over the Boolean hypercube. So instead of evaluating things at W, we're going to add some variables and then interpolate things basically at just 0, 0, 0, 0, 0, 1, and this is the Boolean hypercube. It's just values of 0, 1 and combinations thereof. And how many variables do I need in order to interpolate endpoints? Well, I need log n variables because there's 2 to the number of variables combinations. So I need, for example, here I have, I guess, if I have 4 variables, so I could encode up to 16 different things with it. And the polynomial that results in it turns out that it has 4 variables, but it turns out that we can design a polynomial that is linear in every single variable. So it has many, many different terms. It has, this one has, for example, 16 terms, but there's no x4 squared term here, right? It's linear in every single variable, and this actually makes it very efficient and enabled some of the other protocols that we're using. It turns out also that we then, right, so we need to, if we want to use these multivariate or multilinear polynomials, we need a commitment scheme that supports it. Well, it turns out, fortunately, that there is a bunch. And so, for example, there's a KZG-based commitment scheme that it looks very similar to KZG that we can use here, but you can also use something Frye-based, bulletproof, story, and so on and so forth. The proof size here usually is there's a factor of log n that you pay. So the proofs are usually slightly bigger. This is why also the bulletproofs, the proof size is a little bit larger than normal Planck. So how do we do this? Well, we want to remove the FFT, right? Like this, I've just said we're interpolating this polynomial differently, but still the question is, how do we do this FFT? Well, the idea is that we're actually not going to instantiate this polynomial at all. We'll just keep the polynomial in this so-called evaluation form, and then we'll design protocols, or we'll use protocols that work with this evaluation form. And in particular, we want to make this zero check work. We want to prove that some polynomial is zero over this entire space. And the old zero check just doesn't really work. There's not really a quotient check for these multilinear polynomials. But it turns out that we can use this other beautiful protocol that's been around for quite some time, called the sum check protocol. One of the first, really efficient proof protocols that existed at all. And the sum check protocol, we'll look at that in a second, gives us exactly what we want. And additionally, one of the difficulties that we have to do is that the circuit argument requires a shift. What do I mean by that? Well, we need to access P of y here, and we also need to access P of w times y. And why do we do that? Well, we need to, in every row, access one element and its right neighbor, and then its right neighbor, right? We need to always access like 3 things that are next to each other in the thing, in our computation trace. And in univariate Planck, this works really easily, or it works very nicely. I have to just multiply my variable by omega. The problem is that the shift is not really obvious, right? There's not really some obvious thing that I can multiply this 0, 0, 0 with to get 0, 0, 1. It's not quite clear how I iterate through the space. It turns out, though, that in the circuit argument, this is fine. If you look at this closely, if you look at these 2 variables, the way that we laid out things here is that the first variable always ends with 0, 0, the second variable ends with 0, 1, and the third variable ends with 1, 0. And we can use exactly this fact to access the right constraints. Still, though, this lack of shift is a problem for lookup and fancy kind of Halo 2 gates. And we also have a way of kind of implementing such a shift. I might get to it later. So if we look at the large, the high-level view of how hyperplanck works, or what it looks like, it actually looks fairly similar to Planck. It's just that we replace some of the components. So importantly, we replace the quotient check with the sum check protocol, and we also have to change, for example, things like the product check and the lookup check, because now it's not a product over H anymore, it's a product over this hypercube. So let's focus on the sum check protocol. So what is the sum check protocol? Well, the sum check protocol proves that I have some polynomial f of x, right, which might have up to 2 to the mu coefficients. And in fact, actually, it can be multivariate, so it might have even more coefficients. It might be really complicated. By multivariate, I mean it's more than multilinear. It's, for example, the product of multilinears. And I want to prove that the sum over all of the things in the Boolean hypercube of this polynomial is equal to 0. So how do I use this to prove the circuit formula? Well, really, I want to prove that, right, again, this P of x, 0, 0, I want to prove this gate formula. But I want to prove it at every single point in the space. So I'm multiplying this by this EQ thing. And the easiest way to think about this EQ thing is it's a random linear combination. It's a random linear combination of all of my gates. And what this does is it ensures that the only way to satisfy this formula with high probability is if every single gate is satisfied. So this would prove, so if I can prove this sum here, right, which is yet another, like this is just a more complicated way. I can replace this becomes my f of x, and then I can prove that then basically this gives me a 0 check. So the way that the sum check protocol works is that the prover and verifier proceed in rounds, so it's a poly IOP, and in every round the prover sends some mu degree, the prover sends in total, so there's mu rounds, and in every round it sends 1 degree d univariate polynomials. So d here is the degree of f. And what is the degree of f? Well, I know that all of these things are linear. So p is linear, P is again linear, P is linear, and EQ actually is also linear. So I got 1 times 1 times 1, so the degree is 3. So it sends a degree 3 polynomial in every round. And the prover runs in time 2 to the mu times d squared, so this would be 9, so 2 to the mu times 9. And recall that 2 to the mu is exactly the size of our circuit. But the verifier runs, right, on only O of mu, so it runs in time logarithmic of the size of the circuit. So it turns out that this protocol actually very nicely adapts itself to custom gates. So what is a custom gate, or what is this high degree custom gate? If this is our circuit formula, well, I have multiplications here and I have additions here. But really, there's not a lot that binds this to be just multiplications and addition. I could have a gate that implements, left input to the power of 5 plus y. And there's basically this more general formulation here where I say that there's just multiple gates, and this gate can be a higher degree formula which implements some more complex operations. So think, for example, if I want to implement some elliptic curve addition, then I can implement this with a higher degree custom gate. So the problem in Plonk, so why would I want to use these custom gates at all? Well, if I use more complex custom gates, then actually I can decrease the number of gates that I have. So it decreases the size of the witness, which decreases the group operations. So that's good. Unfortunately, in Plonk, though, there's this quotient check, and you have to trust me here that it increases the degree of the quotient polynomials, which on the other hand increases the number of group operations. So basically, it gives you something, but it also takes something. And in effect, what this means is that Plonk only really works for custom gates up to a factor of 5. I'll do 2 more slides and then I can stop. In Hyperplonk, I can only do custom gates up to a constant factor. In Plonk, sorry. In Hyperplonk, we want to go beyond that. And the interesting observation is that in Hyperplonk, the gates only affect the sum check. But the sum check is only field operations. So it doesn't require any sort of commitments. There's almost no additional things being sent. It's just field operations. So it does increase the number of field operations that are being done, but it decreases the number of group operations. And this is really interesting because group operations are about 1,000 times more expensive than field operations. Unfortunately, though, the dependence in classic sum check in the degree of the custom gate is basically quadratic. So you still can't go too far if you do that. And additionally, the proof size and the verifier time also increase linearly in D. And what we do is we do a couple optimizations around that. So for example, we build a sum check where the prover time is not D squared anymore, but it's D log squared D, which is smaller than D squared. There again, we do resort to some FFTs, but some really small ones, right? They're only over D, not over 2 to the mu. And also the proof size and the verifier dependence on D, we basically are able to completely remove that by simply committing to the polynomials that are being sent in every round. And for the last slide, take these numbers with a massive grain of salt. These are very preliminary numbers, especially the absolute ones. But the interesting thing to see here is that you see a bunch of lines which are over almost the same. And why is this interesting? Well, these lines represent different high degree custom gates. So there's degree 1, degree 2, degree 4, degree 8, degree 16. And it almost doesn't affect the proof size. So we're able to do higher degree custom gates up to 16. We don't know yet quite how far we can push it. At some point, there is a cost to it. Also, the question is what custom gates are still useful. But the thing that we expect is that it doesn't affect the proof size, which is exactly what we want. So yeah, thank you very much. And if I have time, I'm here for questions.
Hello, hello. Okay, yeah, I think there's one question, and I think there's really only time for one question. All right.
Hi, it's Dmitry. Thank you for a great talk. About the FFT, you say no FFTs. Is there a particular reason you want to use it without FFTs? You want to use like for huge domains or something?
Yeah, exactly. For example, for ZK EVM, right? You want to, the circuits that people estimate is like 2 to the 30 size circuits, right? Like, so we're getting into, applications that require really, really large circuits. And so that is one reason. And I think the other reason that is tightly related to it, and we're talking to some people about, supranational, about having a GPU implementation of this, is that for hardware implementations, I think ZK proof systems, now we've shut down all the mining for Ethereum. Like now, hopefully, people can invest their hardware and resources into something better, ZK proof systems. And I think we're gonna have really beautiful SNARKs, ASICs for these proof systems soon. And FFTs make this much harder. So removing this makes it much more feasible and hopefully gives you a lot more benefit when you implement this on hardware.
Very cool. Thank you, Benedict.
Thank you.
So I just have one little piece of housekeeping. I think someone has lost their phone. So if you found a phone, can you head downstairs to the sponsor area? There's a bar, and that's where he will meet you. So if you do see a phone here, it would be awesome if you can bring it back, or if you've picked one up, that's where to go. All right. Next up, I want to introduce Gershta from Polygon Maiden, who's going to be talking about the power of multi-set checks in Stark-based VMs. So welcome, Gershta.
Thank you. Is this work? Yeah. Great. So what does this mean? I'm going to talk about some optimization tools that you can use inside of a Stark-based VM to essentially do a variety of things more efficiently. And in particular, I'll start with sort of a general overview of those tools, but then we can look at some things that we do in Maiden VM using them to allow a practically unlimited stack depth, performing large numbers of range checks efficiently, and single-cycle Merkle path verification. So we can start out by talking about what multi-set checks are. They're based on multi-set equality, which is the idea given two sets, they're multi-set equal if they contain the same elements, including duplicates, but possibly in a different order. So one is a permutation of the other. I'm sure this is review for most people here. And how do we go about actually doing the multi-set equality check? So we'll have an interactive protocol where first our prover commits to two sets. You can consider it to be a vector of field elements A1 through AN and another vector of field elements B. And then we will get a random value beta from our verifier. And then we'll perform a grand product check, just like the heart of Plonk from the Aztec team. And the way we do this is by offsetting each element from A with our random value beta and multiplying them all together. And then we do the same thing with everything from set B. And if these two things are equal, then with high probability, we have multi-set equality. So how do we do this in Starks? The first thing we'll do is put it into an execution trace. When we're looking at a Stark, we're going to start with an execution trace and a set of constraints that we apply to that execution trace before we perform the rest of our arithmetization. So now we've got our two sets. And again, we want the prover to commit, and then we will get values from the verifier and do our grand product check. But we need to build another execution trace to do that grand product check. And so we can't do this exactly with a regular error. We need what's called a randomized error, where we'll commit to this main trace, which is our execution trace and constraints. We've got A and B are permutations of each other. Then we get random values from the verifier. And then we build a new auxiliary, I'm calling it the auxiliary trace, and it's another execution trace with some constraints on it. And this is where we do that grand product check. So we can do this with a running product column, where we say it starts at 1, and at each cycle, we'll multiply in the value from A, shifted by our random value. We will divide out the value from B, shifted again by the random value, and you can see that if we're multiplying in and dividing out the same things, we should end up with 1 at the end. And so this is what the constraints look like that we need on our running product column. We just need to have two boundary constraints at the beginning and the end, and then the laser is what I was going for. Then we have our transition constraint here, where P, our running product column at the next row, is equal to P at the current row, times the value from A divided by the value from B. And from now on, I'm going to show this main trace that we commit to first in black, and the auxiliary trace that we do in the second half after getting the randomness will always be in purple. So now, the next thing that we would like to be able to do is do a multi-set check between two subsets. Instead of having all of A is a permutation of all of B, we actually only care about, say, 4 values, and all of these dashes are just values we don't care about. We'd like to skip them. So how can we do that? We can do that by using selectors to identify the values we do care about and the ones we don't. And we'll just add 2 selector columns and set it to 1 when we want to include the value in our running product and 0 when we don't. And now we'll compute some intermediate values. So instead of including A plus alpha into our running product, we'll use a selector to choose when we include it, and when we don't want to include it, we'll just use 1 and our running product doesn't change. And this is now what that transition constraint looks like. Same as before, but now we've got our intermediate value instead of just a straight up value of A. And there's one more thing that would be really useful to be able to do before we can actually look at these optimization tools I promised. And that is, let's suppose that we have a tuple of 3 elements instead of just a single element in our set A. Same thing in our set B. We'd like to still be able to do checks over this. And to do that, we need to compress these rows, these sets of values, into a single value. And once again, we'll use random values from the verifier. So once again, our prover commits to A. We get some random values. And now we will just do a linear combination and shift this again by a random value. So we'll compress everything, and later on I'll refer to this as compressing the row into a value for the rest of the talk. And now this is the first tool. This is sort of a mental model that you can think about for how we can do things efficiently. The goal here is, let's say at cycle T, I have A, B, and C in my main trace, and I know that I want to use them later, but maybe not for thousands of cycles. I don't want to have to keep them in my main trace the entire time in between, because I don't need them in between. So what can I do to use them here and then use them again down here and make sure in between that I actually am staying consistent, maintaining consistency? So the idea here is to build a virtual table, and by virtual I mean it does not go in the execution trace. This is just in our minds here and in our implementation. And I'll just add A, B, and C as a row to the virtual table, and later when I want them, I'll remove them from the virtual table. And now I can construct this running product column to actually keep us honest and make sure that everything is consistent here. I'll compress this row into a single value, and when I insert to the virtual table, I'll multiply it into our running product column. And when I remove it from the virtual table, I'll divide it out of the running product column. And so what you should be able to see now is that when we are actually consistent there and here, our multi-set check proves this. And these are the constraints. Once again, we'll use some selectors to make sure that we actually construct these values correctly, our value for insertion, our value for removal, and then this is the running product transition constraint for that. And I'm not showing the boundary constraints of any of these. It's because it's the same. We're still saying it's going to be 1 at the beginning and 1 at the end. This is the other main tool that we use to enable a lot of our constructions. We call it a communication bus. The idea here is you've got 2 different segments of the trace, and you want consistency between them. So you can think of it as there's sort of one segment of the trace that maybe is doing your main computation. Maybe it's your stack or your processor. And you'd like to offload things that will be expensive here into some sort of specialized component in the trace that can do them much more efficiently. So an example might be if I want to do a bitwise operation, I could have a specialized bitwise component. I'm just going to call these the requester and the provider. And the idea is here I do an operation on A and B, and I get the result C. And the prover sets this result non-deterministically, and then sends this request to the bus. And then the provider actually proves that the computation of A operation B equals C. So the requester is going to divide out the value from the bus, and the provider is going to multiply the value into the bus, and once again, we'll see that everything holds. And this is what the actual constraints on that bus look like at this point. We've again got a selector to say, yes, we want to send this request now. We've got a selector over here saying, okay, we've computed it and we want to send it back. And then we select, and you may notice there's a little bit of an error here. This should be R0 from the next row rather than R2. But we're going to select the values that we send based on the columns there. So, and here, again, is our running product transition constraint. It should look very familiar at this point. We've got our bus value in the next row equals the bus value in the current row times the value from the provider divided by the value from the requester. And now, we have everything we need to actually look at the constructions that I mentioned at the beginning. So virtual table, communication bus are the main things that we're going to use. And in MIDEM, we can look at how we have practically unlimited stack depth using just a virtual table. So here is a stack execution trace. Some stuff happens early on, and I did not mention this earlier, but these are clock cycles. We're starting at cycle 0 and going to cycle n, and most of you hopefully grabbed that from the execution trace. So let's say at some point we have the state of the stack is like this. This is the top of the stack, S0, and then S7, and now we want to actually push another value on. So normally we got to push a value, the stack is full, we're going to have a problem, and the stack's going to overflow. Instead, what we'd like to do is say, okay, we'll just take this value 20 when it falls off the end of the stack, and we'll put it into a virtual table. So we'll just create a new row that has 20 in it. Let's give it an address so we can keep track of it later. So we'll use this clock cycle for the address. And let's point back to the last row in the virtual table. In this case, it's the first row that we're adding, so we don't have a previous row. So that's fine. So then we compress this into a row, into a single value, and we'll multiply our running product column with that to keep it in there. We'll push again. And now we've got 12 is going to fall off. So we'll add to our virtual table. So now we have 2 rows in our virtual table. And we'll multiply that compressed value in. And so you can see that the product of the elements here in the column is exactly the set of rows that are in our virtual table. And finally, we will drop. And so now the stack shifts back to the left. And we would like to put our 12 back onto the end of the stack here. So we'll remove this row from the virtual table. We end up with something that's just a single row now, and when we remove it, we divide it out. So this is exactly the same virtual table that I showed earlier, but now you can see how it's used to enable stack depth that is essentially unlimited. One really interesting thing that we get from this, so far we've been looking at all of our running product columns. They start at 1 and they end at 1, but actually that doesn't have to be the case. What we could do instead is we could consider preloading this table at the beginning of execution, and then so we sort of create our table and we set the values at the first row of our running product column to contain the values representing the rows in this table. And so as long as we have the correct boundary constraint, we can have something else in this table when we start, and we could analogously do the same thing at the end. We could end without actually emptying that table back off. And they don't have to be the same either. So we don't have to end with R0 times R1. So to summarize the Stack Overflow table, we've enabled practically unlimited stack depth with just this virtual table construction. We don't need to start and end with 1. We can preload values, and we can have values at the end, and those starting and ending states do not need to be equal. The next construction, I will bring in a communication bus for this one. So this is our range checker. It is more complicated than the last one because we are adding the bus and the virtual table together. So let's start by thinking about how you would go about doing range checks. So in an 8-bit range check, we'll have some set of values. These are the values that we're range checking. And we will have some set of constraints over this sort of range checker construction, and I won't describe all of them. But one thing that we'll require is that we start at 0, we end at 255, and at each line, at each row, we either increase by 1 or stay the same. So now to provide range checks to the bus, this only shows providing the checks. It does not show somebody requesting the checks. There's nothing being divided out. So this is really just 1/2 of the transition constraint. To provide checks to the bus, we're just going to multiply in V, shifted by our random value. There's sort of a problem with this because if we want to request, we actually now need to request every single value that's in here, even if the requesting component doesn't actually care about having a range check for that value. Another limitation is that now we can only provide as many values as the length of the trace, as many range checks as the length of the trace. So we'd like to do a bit better, and the first thing that we can do to do better is to add some selector columns to define flags. And we'll let these flags tell us how many range checks we're actually going to send to the bus. So when we have 2 zeros, we'll say that's this flag, and we'll send 0 range checks to the bus. Or we could send, if we have 2 ones, we'll send 4 range checks to the bus. So now we have a lot more control. If there's a value that nobody actually cares about range checking, nobody's sending requests for it, we just set zeros in here, and they don't have to be sent to the bus. And this lets us do up to 4 n range checks because we now have a way of sending 4 values instead of just 1 value at a time. This is what the transition constraints look like for this. Again, this is just sending the values. This is not the requester's side of the constraint. You can see here, when our F3 flag is set here to send 4 values, we send V offset by alpha 4 times. So now things start to get even more dizzying as we try to provide 16-bit range checks, because 8-bit range checks really aren't good enough. And so the last construction kind of lets us down. So this is the big picture of what we really want. We really would like to have somebody that can request 16-bit range checks anytime they want. They send them to the bus. So you can consider maybe this is the stack, and we send over 4 range checks to the bus. And here we need to have some 16-bit range checker that provides range checks. So what's going on here is this 8-bit section is exactly the same as what we just looked at. I've added one new column. And this column is 0 when we're doing the construction we just looked at with 8 bits, and it's set to 1 when we're in this new 16-bit section. So we're only going to provide range checks from this 16-bit portion. So from the stack's perspective, we request them. Over here, we provide 16-bit range checks. And now, what is going on here? Well, what's going on is that we're using the 8-bit range checker to range check differences between the values in the 16-bit range checker. The reason that we're doing that, if we considered just extending the 8-bit construction that we had, we'd have to go all the way from 0 to 65,535, stepping up by 1 or by 0 each time, and it's just not practical. It's super long. There are a lot of values we'd really like to be able to skip. So this is how we can skip them. In here, we're going to put just the values that we actually care about, and then we'll use a virtual table to we'll calculate the difference as an intermediate value, and we'll just range check the difference using the 8-bit range checker. So this virtual table is being used for internal consistency on our range checker. There is one caveat here, which is that our 8-bit range checker can only range check up to 255. So if imagine, say the stack wants a range check for 4, and it wants a range check for 500, we can't actually do that without filling in a value in between. So we can have a gap of at most 255 here, which is what's going on here. This is what the virtual table actually looks like. We've got sort of up here, this is adding 2 values to the virtual table. So the 8-bit range checker can add 0, 1, 2, or 4 values, as we discussed before, using these selector columns. And then the 16-bit can only remove 1 at a time because it's just removing this difference right here. So we build up this virtual table that looks like this. We add 2 zeros, we add a 1, and here's our running product column. And then down here, we start removing rows from our virtual table. So we divide these values out again. And so we should start at 1, we should end at 1, just as we looked at before. And we've maintained internal consistency there. So now this is the full picture of our range checker. We've got our requester sending values. Over here, we're providing 0, 1, 2, or 4 16-bit range check values. And here, the 8-bit range checker is sending 0, 1, 2, or 4 values to the virtual table. And the 16-bit section is removing them one at a time. And if this holds, then we know that our range checker is internally consistent. If this holds, then we know that all the values that we're range checking are in fact being proven here in our range checker. So the key points, we combined this virtual table and communication bus, these 2 tools, for a more powerful construction. We can now send different numbers of requests and responses to the bus at each cycle by using flags from selector columns. We can also use different constraints from different components to do the same thing. And we've enabled large numbers of arbitrary range checks, 16-bit range checks efficiently. So over 3n arbitrary range checks for long traces. And even with short traces, where we have sort of fewer than n unique values, we can do up to 3n total values because of those columns that we had. This is the final construction that I want to show you, our hash chiplet, using a communication bus. So we can, with it, do single cycle Merkle path verification and a few other things. The first thing that you might want to do if you have a specialized hasher is just a single permutation. So we use rescue prime as our native hash function. And all we'd like to do, let's say we have the stack here, which starts out with some initial state of 12 elements. That's the size of the rescue prime state. And then we'd just like to get a permutation. And so the next row in the stack is just going to be is going to be the result of a single permutation of rescue prime. So what we'll do is we'll send our input to the bus, and then we'll also we'll request this input to the bus. So we're dividing it. We'll request this output from the bus as well. And over here in the hasher, we're going to do the same thing. We will multiply them by the input, and then here we will actually do this permutation. We have the constraints that enforce that it happens correctly, and then we'll send the output. So the key here is that we're no longer sending just one value from each side. We now need to distinguish between an input and an output. Talking about Merkle path verification, let's say that we want to prove that D is a leaf in the tree with root G. So we need to do a couple of hashes here. And the key point is that the input now looks different than what it looked like before. And we're also sending a different output. So before we were sending the entire state, now we're just sending the middle, which is the root node. And so we kind of need to distinguish between the different hash operations that we're doing when we send these things to the bus. We also need to distinguish between sending the input here and the output 8 rows later versus sending the input here and sending the output, some arbitrary number of rows later, which is going to let us have arbitrary depth. So that's sort of the summary of what we can do with our hash chiplet. We will define mutually exclusive flags for each of them, define unique value computations, and then perform everything else the way that we did before. So we have some constraint that looks essentially like this. We include when the flag is true, we include that value. And that gives us all of these benefits in the hash chiplet, doing a lot of different operations, differentiating between the different types of values, and all of the operations being performed in a single cycle on the stack. And that is everything. I don't know if there's time for questions, but thank you.
So I think there is some time for questions. All right, we have one over here. We actually have a few minutes if there are more.
First of all, thank you. This was a very, very impressive talk. Also, this will be a noob question, but in the first part where you have, you don't have to go back, but like the communication bus where you were explaining this, is this all happening? Like there was everything happens at the execution cycle of the stack, so you also need to just include empty. I'm trying to remember what was happening on the right side of the communication bus, but so if you can help me there.
I think it's worth pulling up the picture.
Yeah,
on
right.
This.
So you had this specific prover on the right side.
Yeah.
Does this need to happen at the same cycle frequency, or
no?
Do they...
That's part of what's really cool is it doesn't have to. So I can request something at let's say this is cycle 4 or whatever, and I can actually calculate it way down here and send it back. As long as it gets sent from both sides, then our bus column is going to fulfill its constraints. So they absolutely do not need to happen at the same cycle.
Thanks for the talk. How do you, in the Stack Overflow table, ensure that it is not possible to pop something from the stack before you push it? How do you achieve that kind of consistency?
Yeah, it's a good question. So we have a lot of constraints on essentially the address and the previous and what we're allowed to put into S7 here. Not a lot of constraints, but we have a few constraints, and we have 3 additional registers that we use to help maintain the consistency here. And I just didn't have time to dive into it, of course, in this talk. But if you go to docs.miden.io, we describe it all in detail there, and you can get the answer.
Cool. Anyone else? All right. Well, thank you so much, Gosta, for the talk.
Thank you.
Cool. So there may still be a bit of music. We have a break now. We're going to go back downstairs. We have half an hour, and then we come back here, check out the music if it's still happening. And also, just a reminder of that phone. If you found a phone, please go downstairs to the bar. That's where we're trying to collect it. So hopefully we find it.
to shit on you guys. Yeah, it's just all practice, really. My voice isn't as cool as that, but you know. I think you're. Well, I'm going back to Boston first, and then afterwards. Oh, Boston. So, yeah, we have like an LP meeting. Yeah, so that's why. Oh, with mittens. No, not with it. Cool. I see people are slowly trickling in. Let's wait maybe one or two more minutes. But anyways, hopefully everyone had a refreshing break and you're ready for the next round of sessions. Or the second to last round of sessions? Yeah, I think it's actually the last round of sessions. So save the best for last, I think, is what I heard. Great. So now that most people are here, I suspect, or at least like the 85th percentile, which is about all we need. The rest are just tail events. Here, let's welcome Uma and John, who will be presenting about ZK SNARK-enabled light client and bridge for ETH2 clients. Anyways, give them a quick round of applause.
Hello, I'm Uma, and this is John. And today we're going to be presenting on succinct verification of consensus with ZK SNARKs. How do we?
Maybe it's not on.
Oh, okay. Yeah, so let's start with a 10,000-foot overview of the multi-chain and cross-chain landscape. In the past few years, there's been a ton of different blockchains that have come online, and they lie on very different points of the trade-off curve in terms of decentralization, security, throughput, transaction fees, etc. And as the number of applications has grown across all these different chains, users generally want to interact between these chains. So some of the things they want to do include transfer assets from one chain to another, and currently a lot of builders are also exploring other applications of cross-chain interoperability that go beyond asset transfer. And the current space of crypto, like one of its main promises is that it really delivers on permissionless interoperability. And so if users do want to use multiple chains and multiple different ecosystems, then we should allow these ecosystems to operate in a permissionless, decentralized, and secure fashion. And because of this, we believe that bridges are actually very critical infrastructure in the whole space. So what's the state of bridging today? There's a lot of user demand for bridging, and what does it look like? Right now, all the bridges, or most of the bridges, go through very centralized entities. In particular, most L1 bridges today are built on top of a multi-sig architecture where you have a centralized entity controlled by a set of trusted parties that's responsible for watching deposits on one chain and then signing off on deposits on another. And this is really bad because a lot of assets flow through these bridges, and it's kind of this centralized choke point of the blockchain ecosystem. And not only is this ideologically bad, it has real consequences. The multi-sig design is very censorable, and also, practically speaking, there have been a lot of hacks of these bridges. So in particular, there have been many bridge hacks over the past year or so that have resulted in over $1 billion of user funds being lost. And I would argue that this is not only bad for the users, it's actually bad for the whole space in general, because it lessens the credibility of the entire space, and then it leads to downstream consequences like regulation. Okay, so I've talked a lot about the current problems with the bridging landscape, and so let's start talking about solutions. So what does a maximally secure and trust minimized bridge look like between L1s? So if we were in a world in which on-chain computation was not expensive and we didn't have to worry about those practical limitations, then a really simple and elegant solution comes to mind. We already have a method for a decentralized group of validators to agree on the state of a chain. It's called a consensus protocol. And so we think that if we were able to verify the consensus of one chain in the execution layer of another chain, then we can use the same mechanism that's already being used to agree on the state of the chain for bridging. We call this verification of consensus. And we think that if we're able to do this, then it provides a really great solution for more secure, decentralized, and permissionless bridging.
Yeah, so before we get into how to actually verify consensus in a practical manner, let's zoom out a bit and try to understand like the high-level overview of how you might be able to build a bridge or a cross-chain communication protocol over this idea of verifying consensus. So in practice, you're going to have some blockchain like Ethereum, and over the course of its lifetime, it's obviously generating block headers, validator signatures, attestations, and other metadata as part of its consensus process. And this information is normally gossiped over the network to other validators. But what we can also do is we can propagate this information to a smart contract running on another blockchain, such as Gnosis chain. And inside this smart contract, we could theoretically re-implement all the logic we would normally run to verify consensus. And the reason why this is super powerful is because if you can verify consensus, you can sort of keep like an append-only list of finalized block headers on this like target chain, such as Gnosis chain. And if you have access to the block headers, as you probably know, we have access to all of these Merkle tree commitments to the entire state of Ethereum, all the transactions that have ever been submitted, all the events that have ever been emitted. And basically, we can trustlessly read any of this data as long as you provide a valid Merkle inclusion proof against these commitments. So why hasn't this been done yet? Well, it's because in proof-of-stake systems, verifying consensus is just a generally very hard problem on consumer hardware with not that much resources. In general, for Ethereum, there's two big challenges. So the first challenge is that there's a lot of validators, and the number of validators is something that you have to keep track in your client, which is trying to verify consensus, because you have to know like the validators' public keys and how much ETH they have staked to like accurately calculate how much their signature is worth. The second problem, in particular with the EVM, is that there are no precompiles for the elliptic curve operations, which the Ethereum 2 signature scheme is based off of, which is this curve known as BLS 12381. So the developers of the Ethereum ecosystem actually recognize that like verifying consensus cheaply is a sort of an important primitive to have for your blockchain to run light clients. So they sort of introduced this easier to verify consensus algorithm on Ethereum, and it's known as this protocol called the Sync Committee. And it's basically the way to think about this is that instead of having 400,000 validators running consensus on the chain, you select a subset of 512 validators, which are chosen randomly every 27 hours. And basically, these validators will just sign each block header, and if enough of them vote on it, it's considered valid. Now, the trade-off here, obviously, is that at the cost of it being easier to verify, you obviously have much weaker security guarantees, as you're assuming that 2/3 of these validators are acting honestly. So we explored this method at first to see whether we could basically build a light client on chain with just like these 512 validators. But we found basically in practice is that even verifying this consensus mechanism on chain is too gas expensive. Now, the practical reasons for this are that you have to store these 512 validator public keys and prove that they validly rotate every 27 hours. There's also this problem, again, which I mentioned previously, where we don't support the elliptic curve operations currently on the EVM needed for these signature schemes. So for every header you want to finalize, you might have to do up to 512 curve additions and one final pairing check on chain. So what's our solution? Well, our solution is basically to use the technology that ZK Summit is all about and to leverage the power of succinct zero-knowledge proofs. So what I mean by that is that like in your smart contract, you're going to have some function that's validating new blocks. And in practice, what we're doing in there is some pre-processing step, some check that the current validator set is valid, and then finally we check like the aggregation and the final signature check. And as I mentioned multiple times before, the big two challenges are these two bottom functions that I highlighted in red. And essentially what we can do is that we can move all of this expensive compute off-chain, just wrap it up into a ZK snark. And what we can do instead on-chain is just verify this super easy to verify Groth16 proof on-chain. And that basically makes it super gas efficient to run these light clients on-chain. And I think more broadly speaking, while we did this design originally for the ETH2 sync committee, you can essentially think of this as a roadmap to basically creating light clients for a wide variety of consensus protocols, including full Ethereum consensus. And I think this is really exciting because we're obviously seeing how ZK snarks are being used to scale the execution and throughput of blockchains. But we're also now seeing how ZK snarks can scale the interoperability and composability of blockchains by making it easier to verify the consensus protocols that these blockchains run. So we're calling this basically proof of consensus cross-chain communication or proof of consensus bridging. And essentially the idea again is to use these ZK snarks to generate a validity proof of the state of the chain. And we basically believe that this sort of bridge design where you're running light clients on the target chain that can trustlessly prove the state of the source chain is sort of the end game design for trust minimized interoperability.
Okay, so John talked about the high-level approach, and now I'm going to dive into some more technical details, in particular to the implementation we did for the Ethereum Sync Committee. So as John previously mentioned, the Sync Committee does two things. Members of the Sync Committee, for each header, they generate a signature. They generate a BLS signature for each header they believe to be in the canonical chain, and then that signature gets aggregated, and so for each header, there's an aggregate BLS signature from validators in the Sync Committee and a proof that we generate of that signature being valid. The other thing the Sync Committee does is every 27 hours, it rotates its members. It's important it does that for security reasons. And so the current Sync Committee basically signs off on the next Sync Committee public keys. And we have another snark that basically validates this rotation. And we have a trick we use in there to reduce gas costs so that we never have to actually post the Sync Committee public keys on chain because that's expensive. So yeah, we have two snarks, one snark that verifies this BLS signature is valid over the header, and the other snark that validates this rotation. And without going into too much detail of the snarks, basically we have these two snarks, and we had to develop a suite of primitives that we built in Circom to actually generate these proofs. So I'm going to just go over some of the primitives we had to develop, and we hope that it's generically useful for future work. So the first primitive is BLS public key addition to get the aggregate public key of all the Sync Committee members that are signing and generating a proof of aggregate verification. The other primitive, we worked really closely with our collaborators at 0xPerk over the summer for implementing pairing inside a snark, and we used that primitive to verify the BLS signature. And so one thing to note here is all the arithmetic we do for the pairing and elliptic curve stuff is done in the BLS 12381 field, which is different than the field that we're doing the arithmetic in the snark, so we have to do this out-of-field arithmetic. Other primitives we had to implement were the commitments to the snark public keys, or commitments to the Sync Committee public keys. So we had to implement simple serialization, which is what Ethereum 2 uses for serialization, SSZ for short. And we also implemented a snark-friendly commitment to the public keys with the Poseidon commitment. So I had previously mentioned this trick we did for reducing gas costs of storing public keys on chain. So just at a very high level, snarks have public keys and snarks have public and private inputs. And the public input is in red because it's bad, because that means if we're verifying a snark proof on chain, we have to store the public inputs on chain. And a private input is in green, and it's good because it's invisible on chain, so we never have to put it on chain. So naively, if we were to implement verification inside a snark, we would have to have the public keys as public inputs, because we have to check that the signature is from a known set of validators, right? Unfortunately, as I mentioned, storing public keys on chain is expensive, also because the set of public keys in the Sync Committee rotates every 27 hours. So we decided, what if we just store a commitment to the public keys? So you basically hash all the public keys together and store this commitment on chain, and then inside your snark, you prove that the public keys, which are now a private input, belong to this commitment. But because the sync committee rotates, we have to update this commitment, and it's not super clear how to do that. So one idea is when the current sync committee signs the next sync committee, they actually sign a SSZ serialization of the public keys. So one idea is we just use the SSZ of the public keys as the commitment, which is pretty simple. But the problem is that the SSZ is very SNARK unfriendly, and so it's super expensive to compute in every header verification SNARK, because SSZ is just a bunch of SHAs, which is very SNARK unfriendly hash function. So our idea was, when updating the sync committee, we would verify a proof that would take in the new public keys, assert inside the SNARK that it corresponds to the SSZ serialization, and then also compute Poseidon serialization of the public keys, which is very SNARK friendly. And with that, we were able to map the SNARK unfriendly commitment to a SNARK friendly commitment, and what we store on chain is just a SNARK friendly commitment. And what this gets for us is it saves us 70 million constraints, which is quite a lot, in every header verification SNARK. So yeah, hopefully this trick can be useful in like other contexts as well. And just some benchmarks. So as I mentioned, we have two different circuits. The sync committee rotation circuit has way more constraints because of this SSZ thing I mentioned. But for both circuits, the total witness generation post-proving time is on the order of 4 to 5 minutes. So our methods are actually really practical. In Ethereum, you have to wait for finality anyways, which is 2 epochs, which generally is maybe around the 12 minutes. So on top of that, you have to wait an additional like 4 minutes for proof generation. And we think that more modern proving systems can reduce this time quite significantly, and so hopefully the delay is quite minimal.
Yeah, so we've been working on this for the past few months, and everything we described in the presentation, we've actually implemented. We implemented the light client, and we've also gotten like a prototype bridge working on top of it. You can go play around with it. I think now it's at just async.xyz. Fair warning, it's in beta, and the mobile support's bad. But yeah, here's just like a few. Here's just a few screenshots of it working. It's just like a normal token bridge demo. You just choose your network. You choose your token. You say how much you want to send over, and then you'll basically just submit a transaction. And then basically behind the hood, what's happening is you'll make a deposit on like Ethereum. And basically what you have to do is you have to wait until the light client on the target chain gets updated with a block header, which can Merkle prove your deposit. So that'll happen after like 12 minutes plus like the 3 minutes for proving. And then we'll submit a transaction to update the light client. And basically, to withdraw your assets, you'll just basically provide a Merkle proof, proving that your deposit is like validly represented in the ETH state root. And after that, you'll have your assets. And yeah, you can go play around with it. It's all online. But anyways, yeah, to zoom out a bit about like what the pros and cons are of like these like proof-based bridges are first, like obviously, because we're able to borrow the security of the consensus protocol in theory, like in theory, you could borrow like the entire security of Ethereum here. Your bridge is going to have much higher security guarantees, especially when compared to existing bridges such as multi-sig bridges or bridges based on like smaller decentralized networks. Another pro is like in a world where there's like an operator implementation where anyone can generate proofs. Theoretically, for example, you could incentivize people to submit proofs on chain, and maybe they get like a small percentage of like the fees that the light client is making or something like that. And like for these reasons, it's just much more decentralized and I think aligned with a lot of the values we care about in blockchains. And like at this trade-off, there's obviously some cons. Verifying like a SNARK proof is obviously more expensive than just checking that like 5 out of 7 signatures, 5 out of the 7 validators have signed. There's also some latency that you're incurring because of the proof generation time, but maybe that can be reduced to like by an order of magnitude. And also in terms of like scalability, one challenge here is that for every change you make to a consensus protocol or for every difference in consensus protocols for different blockchains, you have to kind of like go ahead and like hand design your SNARKs, and maybe you have to get them audited and stuff. So that can be a huge developer bottleneck for building these type of bridges. In terms of like our future roadmap, we kind of want to become like a trust minimized and decentralized interoperability layer for Ethereum and other decentralized blockchains. And in the short term, we're actively working on building what we're calling these like succinct light clients for other consensus protocols. And we also want to start working on moving away from the sync committee, which only has a security of 500 total validators, and work towards a world where we can verify all 400,000. Furthermore, we sort of want to also explore applications such as governance and identity outside of token bridging. But yeah, that's what we're thinking for now. Before we end, I just want to give a big thanks to Gnosis DAO, who was generously funded us a lot for this work, and also Xerox Park, where we worked out this summer, and we borrowed a lot of ideas from the people there. And yeah, that about wraps it up. If you want to collaborate, or if you have any comments or thoughts, I'd love to hear them, and come find us afterwards. But also, if we have time, we can take questions now.
So we have about a little bit over 5 minutes if anyone has any questions for Uma and John. Yep. All
right. First of all, congratulations and thanks a lot for doing this. This was way overdue. This should have, yeah, awesome you guys are pushing this. Just maybe if you could, so you use this sync committee from E2. Can you elaborate a little bit more how you prove that this next set of signatures is constrained to be the correct one? Just to get the question started.
Yeah, so the current sync committee signs the public keys in the next sync committee. Or they do something very equivalent to this. So you just have to verify that the signature of this header that includes these next sync committee public keys is valid. And then, as I mentioned with the trick where we map this commitment to the public keys from being a SNARK friendly commitment or SNARK unfriendly commitment to a SNARK friendly commitment, that's just to reduce the gas costs of not having to store these public keys on chain. Yeah.
Great question. Are there any more questions? In fact, there should be more questions. If there's nobody who has any questions, I'm shocked. I guess you did such a good job that we have. Oh, all right, there we go. Haha. I think I saw Henry. Oh, okay. No, I think it's sorry.
Just quickly on that, maybe you mentioned it, but I could have missed it. So how do you handle equivocation if the current sync committee signs multiple seeding ones?
Sorry, could you repeat the question?
Yeah, but if they sign multiple disjoint subsequent sync committees to follow them.
Oh, this is he's saying if they basically double sign.
Oh yeah.
Yeah, so currently the sync committee, there's a honesty assumption on the sync committee where if they double sign, they're not penalized for this. So you have to assume the members of the sync committee are honest. Of course, if you validate full Ethereum consensus or validate some subset of Ethereum consensus using the duties the validators normally do, then you don't have to worry about this problem. So the assumptions of a sync committee are definitely a lot stronger than the assumptions on full Ethereum consensus.
Hey, so this is kind of a philosophical question, but do you think that it's better for decentralization overall to have a consensus protocol that has many, many validators, but no real practical light client, or one that has a fewer number of validators, but where the light client is very easy to run on any device?
Yeah, I think this is one point Uma made a few times to me, but I think basically having a lot of these, I think in principle, having one big network, decentralized network is probably better. I think the Ethereum and rollup future is actually pretty secure and pretty nice. But I think one thing is basically having multiple of these L1s is a point of meta decentralization, where maybe you don't have so much lock-in into, for example, the EVM, or for example, you're too much relying on the ETH consensus protocol operating correctly. And by having many of these other L1 chains, you can sort of hedge against sort of bugs being introduced into a piece of software that's so important.
Yeah, I think also your point about it's, you know, in other consensus protocols, maybe you have like less validators or something, and it's easier to have a light client. I think if we accomplish one of our goals, which is to verify all 400,000 or, you know, someday maybe it's more Ethereum validators and verify all of their signatures and verify the consensus in a SNARK, then you can have a light client with a lot of validators. So I think this is kind of like working towards that future as well. Obviously, it's, you know, technically very, very complex, but I think it's possible if we're able to do it, yeah.
Cool. I guess I'm all the way back here, but are there any last burning questions? Oh, all right.
Hello, guys. Do you still use Growth 16 as your ZK proving system?
Yeah, we use CirCom. We used CirCom to make these circuits, so that uses Groth 16. Or I guess it also has Planck, but we use the Groth 16 version. But one of the main benefits of CirCom and Groth 16 right now is that it has a really stable, really trusted, used on-chain verifier, like for example in Tornado Cash. So it actually makes it practical right now. But as like these newer generation of proving systems get more proven out, especially with zk EVM and stuff, we definitely want to like re-implement this stuff and get all the efficiency advantages.
Thank you.
We've got a question from the chat, the live stream chat, all the way back here.
All right, go for it.
Jeremy asks, if I make a malicious ERC20 token, for example, only transfer to my address on one L1 and bridge it to another, does it emerge as a, quote, normal ERC20 on the second L1? Does sync committee check code?
Yeah, I think this is like a problem any bridge has or something. So I think most bridges like deal with the sync committee does not check code. Yeah, like we're mostly making this like cross-chain communication protocol for getting one chain state on another chain state, and then what you do with that, if you choose to make a token bridge, like you have to figure out like what cases you're going to handle.
All right, well, let's give it up one more time for Uma and John. Hi. Here. Yeah, you're next. Let's wait like 2 minutes maybe? So for people to circle out and in. And then.
Will I be able to use my laptop? Can I, like, I have some updated slides, is it possible?
Okay, here, let me go check with Henrik. Unfortunately, that would be a question for Anna, but you didn't use it. Up next, I guess, sorry, I was told I have to go on stage every time I speak, unfortunately. So up next, we have Alex from ZK Sync, who will be presenting on a somewhat spicy topic, I think, of ZK EVM, compatibility versus equivalence. So give it away for Alex. Everybody take it away.
Hello, everyone. Thank you. So I'm from ZK Sync, which is the project aiming to bring EVM compatibility to the world of ZK rollups. We built the very first functional ZK rollup on Ethereum, which is now known as ZK Sync version 1, and it's live on mainnet for 2 years with simple payments. And back then, it was hardly conceivable that we will be able to do generic programming in such a short period of time. But here we are. We introduced the concept of ZK EVM 1.5 years ago, raised a significant amount of funds from different investors led by Andreessen Horowitz last year to implement it. And we opened the first public testnet for ZK EVM in January last year. And now it's very stable, and we're about to launch on mainnet in just 43 days. We're very committed to this date. So ZK Sync is a mission-driven project. Our mission is to accelerate the mass adoption of crypto to achieve personal sovereignty. And every design decision we make technologically is considered from this perspective. So whatever we're going to discuss, always keep this in mind. This is the central judging point for us. So, and this is why we had to embrace ZK EVM. It was clear already 2 years ago that EVM kind of is going to win the protocol race across all the standards that were emerging. It became de facto lingua franca of the Internet of Value that is becoming true with Ethereum and other blockchains. This is like JavaScript. It's going to be sticky for a very long time. There are a lot of tools, services, libraries written for EVM specifically, and it's just going to stick. Alternative L1s are pivoting all to EVM. Have to support it. And ZK, I don't have to explain it at this summit. It's the holy grail. It's the only technology we have that actually breaks out of the blockchain trilemma. So the combination is what brings us to ZK EVM. Now, if we are talking about ZK EVM, we initially set out to build something compatible with EVM standard. There's been, since then, a lot of talks about equivalence as a separate concept. Compatibility is not enough. You have to build fully equivalent to satisfy all the developer needs. But the reality is it's a spectrum. It's not a binary switch. And Vitalik recently, a few weeks ago, had a really good blog post about this, introducing several types of compatibility, degrees of compatibility, from just mere source code compatibility to what you could call full equivalence. And they are nicely put on the spectrum of performance and compatibility. And you can see that we were trading off performance the higher on the compatibility we go. So I want to give a detailed overview of the types and give you some intuition on why, what are the trade-offs, what matters, and why it is so from the perspective of ZK environment, and where we are with ZK Sync. So as you can see, the types are basically just adding one by one features. Type 4 is the very basic one where we take source code, we can deploy anything written for EVM, and it will just work in exact same way as you expect, or basically the same way, right? But you cannot deploy bytecode, and the API might not be 100% compatible, and you certainly don't have full block root equivalence. But the higher you go up, you just add one by one those features. So there is a really big difference between type 4 and everything above. Type 4 is native compilation. When you take the source code and you compile it into RISC-like architecture, it's not exact RISC standard, but it's reduced instruction set. We do it using LLVM compiler from Yule, and we use Solidity native compiler to get to Yule. And we also have a Viper compiler, which compiles directly to LLVM intermediate representation, and from there to our ZK EVM instruction set, which is optimized for being provable in the ZK environment. So it's optimized for us to be able to prove the execution trace of a program that runs the ZKVM opcode set. In order to do this, we had to carefully choose the opcodes to make them really optimal for the ZK environment. So like if you're going with an architecture that was designed for PC, for Phenomenon architecture, you will not have this optimal property of having all the opcodes as small as possible, as close as possible in the cost profile to each other, so that you really have this micro basic blocks, because in the ZK circuit that proves an execution trace, at each step, at each cycle of the circuit, we have to implement all the constraints for this one step. So like essentially the cost of each cycle is the sum of all of our opcodes. So that means you want as little opcodes as possible, and you want them to be like really, really mini, really basic, like not taking too much complexity. Instead, implementing the complexity through like using multiple opcodes if you need that, and optimizing that at compiler time. So this gives you the lowest possible transaction cost from like on the prover side from all the other approaches, like by orders of magnitude, probably by more than one order of magnitude. We will see why. But like this is a really important thing. But the second important thing is it gives you the ability to experiment and go beyond what is possible with EVM and implement new features in an efficient way that is important for user experience and developer experience. For user experience, one good example is account abstraction that we support in zkSync version 2. So you can do multi-call out of box. So you just do one click in MetaMask or your wallet, and you can execute multiple calls. You can support smart contract-based wallets out of the box, like Argent wallets, working natively without having to like instantiate them and do like complex operations to pay to just get the wallet, etc. But developer experience is really important, and it's going beyond just like pure convenience. You can take libraries that are written for, like in any modern language that supports LLVM frontend, like Golang, C++, Python, Rust, and you just can compile them natively into LLVM and use them as libraries and connect them to your smart contracts. And using the really low cost, like absolutely push to the bottom execution costs, you can do like quite complex computations, whether mathematical or like compression or like doing some transformations, whatever you need, like complex stuff, like processing large arrays of data, working on like doing voting, for example, on certain subset, on a certain snapshot of your blockchain state, etc. So this is something you would lose. This second point you would lose if you went for full EVM equivalence, like for like essentially for any degree of compatibility above type 4. The main disadvantage of this approach is that obviously we won't support opcode level compatibility, so all the tools that work at opcode level won't work. So we will need to re-implement them. Luckily, there are only a few of them. So mostly it's debuggers and tracers, and we can just work with the vendors to, like, there are a few of them that are popular. We can just implement support for zkSync, ZKVM, and they will work also. Okay. This is type 4, and yeah, as I said, like we embrace it at zkSync from day one of our launch initially, because it's really critical to our mission to be able to support like real mass adoption. Mass adoption means excellent UX, where users have better UX than they would expect from like neobanks and all Web2 applications. So you really don't want to bother them with inconveniences, with like multiple clicks, etc., etc. And you really want to be able to support the use cases that require the absolute marginal bottom of the costs, such as social networks. Like we're talking about orders of magnitude. So there is a difference between 10 cents per transaction and 0.1 cent per transaction. Like it's quantitative, but it really leads to entirely new use cases being unlocked. that are not possible if your transaction costs are in the range of cents and not like microcents, millicents, etc. But all the types above type 4 are, let's call them CISC, like complex instruction sets, because you have to interpret or like natively execute EVM opcodes, and they are complex. Some of them are simple, like add, sub, mul, like jump, compare would be basically what we also have in ZKVM instruction set. But you have some really ugly ones like push 32, where you're manipulating 32 variables of your stack, etc. Or working with storage, working with some precompiles, like hashes. So there are two ways you can try to solve this. One would be to implement a circuit that natively supports all those opcodes. As you can see, the cost of a cycle will grow, will just explode. Because you will have to maintain, at each cycle, you would natively have to implement all these complex instructions. And yeah, this would be the most expensive, prohibitively expensive approach in my opinion. Second approach would be to try to interpret CISC. And that is actually doable, but it just gives you this order of magnitude or more overhead. Because if you remember here, each opcode is really small. It's just like one cycle, right? But then to be able to interpret this opcode, if you just encounter add, you would need to add micro instructions that read the opcode, make a choice, what branch do we have to go, compare, execute, and then update the counter. Each of that would be a separate transaction. And then you would add a lot of them for really complex instructions, but you still would add an order of magnitude more to simple instructions. So that is still suboptimal. But it is doable. And in fact, we don't want to stop there. It is completely possible to implement this interpreter just as a contract on the natively compiled contract, which you can write in assembly, in Rust, in Solidity, in whatever is most convenient to write. Right? So this would make ZK Sync instantly a both type 4 and type 3 system. Or in this classification, we just go up to type 3. But we would be able to support both native code compiled into RISC ZKVM and bytecode that for some reason people don't want to migrate. Maybe because it's super sensitive on security and they just want to be, they don't trust the new compiler yet. So they want to use the old tested code, which is bottle tested with a lot of money on layer 1. Or maybe it's just some legacy code that just needs to be running for whatever reason. Maybe some small, or maybe a good example would be deploying to the same address on multiple chains, right? So you really want to preserve the same bytecode, so you can prove that it's the same hash as the same instruction hash of the contract code hash as on other chains like layer 1. So that would be doable by just implementing this simple interpreter. In fact, there are these interpreters already written in optimistic rollups because they need to execute EVM inside EVM. So one option would be to take this code and adjust it. Another option is just to write something from scratch in Rust, which I think is going to be way more efficient. And then to get to type 2.5, we only need to support 100% of the API. What that means is all the cryptographic functions, all the hashes, and all the precompiles. The hashes we're basically going to support from day one. When we launch on mainnet, like what we currently have on testnet, and when we launch on mainnet in 43 days, we will have Kchuck and SHA-256 natively supported. They're quite cheap, thanks to Plonk and custom gates and lookup tables. They're not not much more expensive than Patterson hashes or algebraic hashes. So we are actually natively using them. Other precompiles we expect to be supporting by the end of year. The most complex one is probably the pairing computation, BN256 pairings, and maybe other pairings in the future. So, but there is work going on this, so we will support them. It's not a big deal. And that's the only difference between type 3 and type 2.5. So as you can see, the performance is essentially the same like you could get some boost in performance if you avoided normal hashes and would switch to algebraic ones. But like, if you really want to do that, you're much better off with type 4 anyway. Then you're probably writing your code optimized for ZK environment. Now, if you want to go up, or actually, yeah, before that, it's important to notice that when we start with type 4, it's like starting with a really powerful machine that can, like, like a new MacBook or like some new processor that can simulate older systems, mainframes or like MS-DOS or like older versions of Unix. But you cannot really do the other way around. You cannot take an old like 80s, 90s machine and run a modern macOS on it. So you really have to start at the bottom and go up, because you cannot do it the other way around. And this is why we're doing this. But if we wanted to go up higher, it doesn't really make sense for an L2. So the type 2 would mean that your guess calculation is exactly the same as in Ethereum, with like at every opcode is metered in exactly the same way as it's done on layer 1. And block root hash would include like consensus mechanism and all the storage updates, etc. So from the application standpoint, it's like it doesn't matter, because you don't have access to, you cannot introspect state on Ethereum really. So having consensus there would deprive you of the ability to experiment with consensus layers in layer 2. But like that could be pro and con, but like having guess metering is really disadvantageous and counterproductive, because the cost profile in layer 2s will always be in favor of computation and like and like cheaper storage over layer 1. In layer 1, you have wild difference in different types of resources, how they are metered compared to layer 2, right? So if you force people to meter it the same way as it's metered on layer 1, you will be either not having the advantages that layer 2 offers you, like really cheap computation, really cheap storage, or you will be opening yourself to a denial of service attack vector. Neither way is good. So the only thing why you would want to use the type 2, type 1 systems potentially would be to try to prove Ethereum itself, like the blocks, like every single block of Ethereum, and going back to Genesis, or like latest re-Genesis. But that would actually only give you the ability to quickly sync a node. Not much beyond that, because every new block would be coming like really fast every few seconds. Probably we don't have the proof latency yet for like a couple of years to be able to generate the proof so fast for like Ethereum, especially with like all the inefficiencies of type 1 compatibility. So it's really not a big deal. So you would be like, if Ethereum wanted to become a fully succinct chain, what they could do is just reduce the block limit to like from 12 million gas or 30 million gas to just like 500,000 gas. Make the blocks really lightweight and like kind of force everyone into L2s, and keep the L1 just for the verification, like raise the gas, raise the storage costs like really high, and reduce the block, the gas limit, so that like full nodes only work with a few storage slots that are actually commitments from rollups, and everything else is happening in the rollups. This is a much easier way to approach this than trying to go for full type 1 like equivalence. What would be real equivalence? So yeah, that's why we're starting with type 4 and going like really fast to type 2.5 with ZK Sync. That's it. Thank you very much. Really happy to take any questions, and I also want to add that we are actively hiring, and if you are interested in zero knowledge proofs, or if you're like want to do engineering, like whatever, like we're open in all roles, both technical and non-technical. So please talk to me after the call, after this talk. Thank you for attention. We're really happy to take any questions.
As usual, does anyone have any questions? Wow,
really? All right, well, I have a question, actually. Yeah, so it's not just an L2 problem for the metering resources, actually. It would be essentially any ZK chain or with succinct verification, right? The difference between metering for certain resources also comes from the fact that you now have succinct proofs for certain things. So your computation cost is also different. So it wouldn't just be an L2 difference between an L1, it would also be the fact that you have, your state transitions are verified by succinct proofs. No? Or is that incorrect?
So the difference comes from the fact that you're trying to measure the costs of running a full node.
Mm-hmm.
If you're running a layer 1 full node, you have to be able to access storage really fast. So first of all, you're using computational resources, which are limited because you're running it on a single processor. You cannot use take use of multi-core because it's always executed sequentially until we have some really fancy parallel processing of transactions. So that's one thing, and you have to account for the fact that you're running it on tens of thousands or hundreds of thousands of machines, right? So you have to add this overhead there. With ZK, you don't have this because you only run it once on your prover. It gives you some overhead, maybe 100x, maybe 1000x, but that's it. That's flat, and then you can add 1 million full nodes, and they will all take that. And for the storage, it's coming from the fact that you have to maintain SSDs that are really efficient in random access. That's the problem. With data availability, when you just put the bandwidth, when we push the storage data from storage to call data, all you need to do is just download a chunk of data directly, a continuous chunk of data from the network. You don't have to jump on disk from point to point. So that is any layer 1, if you have a succinct layer 1, you will probably have the same profile as rollup, yes.
Cool. Oh, all right, we have one more, or at least one more question.
So the big benefit of Web3 is the fact that it is permissionless and stuff. How big is the risk, in your opinion, of some big company like Starkware conquering all the rollups and just forcing old Web 2 censorship in Web 3?
No, that's a terrific question. That is definitely the risk is increasing because at L2 it's very tempting to have higher centralization because you're safe anyway, right? You can have a single centralized operator who will be sequencing transactions, and then we're all roll-ups, so it's the same security as Ethereum, and then you give this one entity the right to standard transactions. So we need to be racing now to decentralize L2 sequencers ASAP. All of their roll-ups. Whoever doesn't do this doesn't have a right to, they can be doing some corporate chain. I cannot talk for Starkware, we don't want to become a corporate chain. We want to build a permissionless protocol in the spirit of Ethereum. We are fully aligned ideologically with Ethereum. We're fully embracing the ethos of Ethereum. So we're going to be fully open source, permissionlessly open source. It's very, very important to us. So we haven't open sourced version 2 yet. We're going to do it after the audits. But when we do, together with the launch, it's going to be MIT Apache license. So anybody can fork it, not just open source for read-only purposes and copyright version, right? So that you can fork it away if the chain that we initially launch is not fully decentralized, is not embracing the ethos. You should be able to move away. This is why we're supporting priority queues for forced exits, and they are going to be working in the batch mode so that you can do mass exits. So if you have, the way it's going to work is you're going to have some decentralized consensus running the sequencer. It can have some trade-offs. It can be less validators. It can be more validators. But if some chain, and there will be multiple chains, maybe as L3s, maybe as separate instances. If some of them are censoring transactions from the user should just say, screw you, we're going to mass exit to a different instance run by someone who is not censoring because they have a better decentralization.
Are you aware of any proprietary I don't know, technologies by Starkware that give them benefit over ZK Sync?
Proprietary?
Yeah.
Well,
patented, I don't know. Is this thing at this point?
That is not a thing because what they're building is Cairo. Like it's a completely different direction from what we're doing. They're diversing, like they're essentially diversing from Ethereum. They're telling you have to learn this new language, re-implement all your code in it, re-implement the entire ecosystem, all the tools, all the libraries from scratch, and just use those libraries. And then you're gonna use it under Polaris license, which is under copyright, and you only may use it with one single sequencer that is designated by this multi-sig or whatever, like engraved in the Polaris license, right? And then you don't have a choice. You cannot fork away. So like that's the classical lock-in, which might be beneficial if you are a corporation. You want your SLAs, you want guarantees. So you're gonna go there and you're gonna use it, and then you're gonna have your support or whatever. That's not our way. Our way is to be compatible with Ethereum, so that like you don't have to learn stuff. You just take existing code, take existing libraries. We support like Web3 API completely 100% with all the reads, writes. Based on that, we have integrations now with Chainlink, with the graph, where you can use those APIs just the same way you would use them on layer 1 on other rollups, and you can fork away. That's the most important thing. You should be able to fork away. That's what makes blockchains beautiful. It's a little harder with layer 2s. There are some specifics with upgradability that make it really hard to. You cannot fork away in all situations. If there are vulnerabilities that are immediately requiring fix, that is still a hard problem that I don't have a perfect solution to. But for normal operation, if you're just being censored by validators, you should be able to mass exit away.
Well, I think this is the last question, unfortunately, because we're about to get to the break time. But
but yeah, I just wanted to ask, because it seems like in order to allow for the censorship resistance, we need both validators and provers that are acting in the best interests of that cause. But then, given that the provers are, like you said, working on an overhead of like 1,000x to what a verifier would be doing, what incentivizes people to run provers?
Provers are actually easier. So the validators are more at risk of centralization because we want the best UX. Best UX means low latency for transactions. You want transactions to be confirmed instantly. The provers can be fully permissionless. So once a block is formed by the consensus of the sequencer, anyone can be building that block. So there will be some provision, some sequence which is expected to run so that you don't have a race, like that two people do not work on the same proof at the same time. But that is minor. Like anyone who has the block data from the consensus can be building the block. And the proofs are going to be decentralized very broadly because we are using GPU accelerators. Like we brought the latency down to just like some seconds, like half a minute, because everything is run in parallel on different GPUs. The GPUs give you a boost of several orders of magnitude of improvement over CPUs. And when I say a boost of performance, I always mean the costs. Like the latency is going to remain flat, because like the latency is determined by the number of steps of recursion, and at each step we do like 20. We can aggregate 20 different proofs or like more, and then you just have like 3 steps that give you blocks of basically arbitrary size of tens of thousands of transactions. Each step takes like 15 seconds on a powerful GPU. And these GPUs are abundant. We have a lot of them now freed up this morning with the merge, and they're not going anywhere. And like we will always have a lot of GPUs like running on computer, gaming and machine learning and all this stuff, which we will be able to reuse. And the best thing about GPUs is they are very decentralized. They are in the hands of a lot of people. So we'll be able to build a network of decentralized provers that just like do this job and we aggregate. So like provers are less at risk. Validators, because of latency, is more important. But my guess is we will have several instances, maybe like as an L3, and like L3s are coming very soon to ZK Sync, where like some L3s will be optimizing for latency, maybe for high performance trading, but some of them will be optimizing for censorship resistance. And you will have hundreds of thousands of validators to make sure that you actually always get your transaction included.
Great. Thank you so much, Alex. Let's give it up one more time.
All right, we have a break. This break is sponsored by Ethereal Ventures, and I just want to say thank you to Ethereal for sponsoring that. We can head downstairs. Be sure to be back for our last talk from Henry, talking about private DEXs and the park bench panel. And I don't know if you all know what that is, but it's a very interactive panel setup where people are kind of getting on and off the stage. If you have things to say, you have to come for that. I do it every time. It's very exciting. All right, so we'll see you back in half an hour.
All right. I think we are pretty set. I think this is, unlike the last time, it's about 95 percentile, so the 5% tails, I think, could be cut off now of people incoming. Anyways, so hopefully you had a refreshing break before the last session. And in particular, we're going to have Henry de Valence, who's going to talk about a topic very near and dear to my heart, which is how to build a private DEX. Harder than it seems. Anyways, give it up for Henry.
Front run. All right. So, great. So, yeah, my name is Henry. I work on Penumbra. I'll be giving you this talk on how to build a private DEX. And to kind of start off, this is sort of a little bit of a joke, but also a little bit real. We have this somewhat sad state of affairs, which is if we imagine a Venn diagram where one part is chains that people use, and then the other part is chains with privacy, then it's like almost two circles, and the intersection is like basically the people at this conference, right? And I say this as somebody who spent like the last 5 years trying to build privacy infrastructure. I don't think this is because of lack of trying, it's just like a very hard problem. And actually a lot of the most successful deployments of ZK that we've seen so far have actually been on the scalability side rather than the privacy side. And so I think that points to some kind of issue of like, we're just somehow not thinking about this right or something, right? And for me, and how we got started on building Penumbra, the thought was like, okay, well, what if we tried to build just like one useful application? So I personally am not smart enough to be like, okay, I'm just going to sit down, I'm going to come up with this like perfect idealized programming model for private programmability. It's going to like burst out of my forehead, and that'll just be like the perfect thing, right? So what if instead we just try to build sort of one thing that has some kind of fixed functionality, figure out how we could make that useful, and then after that, see whether or not we could generalize anything. And that's basically what this talk is going to be about. It's about some kind of vague ideas of how you could generalize the approach that we've come up with into some kind of more general programmability system. So just from a kind of like product perspective, how would you provide useful functionality on a private ledger? If you're going to build one application, what would it be? For us, we kind of landed on trading as a use case to get started. And the thought process there is that trading is, in one sense, it's kind of this like minimum viable transaction. A lot of the time people will think of like, oh, like payments, that's the simplest possible thing you could do on a blockchain. But actually, a payment is really quite complicated because whenever you have a transaction, the counterflow of that payment is going to be recorded off-chain. So if you want people to use it, now you have to sort of build and scale this whole parallel social infrastructure. Trading, you can have a transaction that in itself is economically useful for that person. And trading is also really interesting because it's an area where privacy, thought of as control over the disclosure of information, is not just this kind of abstract principle or human right or whatever, but it's something that has a very quantifiable near-term financial value. People don't want to get front-run. And so you can actually sort of potentially move out of, oh, we're going to build this privacy product to we're going to build something that is better because it is private. So that's kind of what we've landed on. So what we're building is this private proof-of-stake L1 that has a cross-chain shielded pool that can record any type of asset, and an integrated private DEX. And so before getting into sort of what's the interesting technical idea or challenge, the next thing that I want to try to convince you of is that useful blockchains revolve around public shared state. And this is actually really relevant for building a private system, because if the goal is, oh, we'll just like make everything private, I think you end up actually not building a system that's very useful. So for instance, considering a market, if you made the entire state of the market completely private, you end up with something that nobody really wants to use because nobody has any idea like how much liquidity there is, what's the trading volume, what kind of prices are people getting. Instead, you have to figure out like, okay, the point of the blockchain is to be this kind of coordination fabric. If you don't have any public shared state, then all you're using it for is some kind of like messaging or settlement layer for some kind of off-chain coordination, and that's basically like a kind of fancier form of payment channels, which don't really seem to be that useful. So how do we get then to being able to have private interaction with public shared state? I think this is kind of the fundamental like big thing that we have to figure out in order to build useful private applications. And to explain a little bit about why this is such a problem, we can kind of recap what may be familiar to some people in the room, the key differences between the state model of a transparent or a shielded chain. So let's say we have this transparent chain like Ethereum. The basic kind of mental picture is that we have this big global mutable state. We have transactions that we've come to consensus on, and we're just applying them in sequence, and each transaction is like locking the state, doing stuff, unlocking, and then we do the next one, and so on. In order to make this private, we first have to move to composable state. So I guess this is kind of like rewinding backwards to Bitcoin, but the idea is instead of having like one big global state, we'll have this tree of little state fragments, and then each transaction is only going to have some determined set of inputs that it consumes, and it composes those together to form new state fragments that get appended into the chain state. And the reason that you want to do this is so that you can replace all of the state fragments with commitments to the state fragments, and then you can replace the actual sort of clear text transaction contents with a proof of a valid state transition. But this diagram is like a little bit of a lie, or it's not quite capturing something important, which is that what's actually happened is that we've successfully moved all of the user state off-chain and replaced it with these commitments, and the only on-chain thing is just this proof pi. But that means that the execution has moved off-chain, and so this only works when there's no shared state. Because if, for instance, I want to interact with a DEX, like say I want to trade on Uniswap, if I'm going to move the execution off-chain, then one of the inputs to my state transition that I'm supposed to be supplying this kind of sealed, verifiable proof of is going to be the state of that AMM. And the state is just going to change out from under me. And I also can only be touching my own state. I can't interact with anybody else's shared state or anybody else's state fragments because I don't know what they are. And I'm making ZK proofs, so I have to have knowledge of the whole complete state transition. So what this points us to is actually that we need some kind of better computational model for concurrent state. And the big idea is if we think, if we forget that we're in blockchains, right? Just imagine that we're doing systems programming and we want to build some kind of like really high performance, like parallel concurrent system. The way to do that is not to like take all your app state and like put like one big global lock on it, right? It's actually not even to have like finer locking, like you could do that, I guess, but a much, much better and cleaner way to do concurrency is by having independent actors that are each controlling or responsible for one piece of state, and then you have message passing between those, and that's how you avoid the need for some kind of explicit data synchronization. So what would that look like in the context of a blockchain? Well, we could get some kind of actor model for blockchains where instead of having each transaction acquire a global lock on the whole state and then do some synchronous function call, we could say a transaction is going to pass a message to a contract. Then each contract can execute exactly once per block on input of all of the messages that were sent to it in that block. And this allows the contract to do batch processing if it wants, or it could do whatever kind of arbitrary application logic it wanted. So for instance, if you had an auction, you could sort the messages by the bid or something. And the user state is going to execute asynchronously off-chain using ZK proofs. So as a side effect that I won't get into in this talk, this also, in my opinion, mostly solves MEV. But the interesting thing here is okay, when I say we're going to do some kind of async execution of the user state off-chain, what does that look like? So we're going to start, instead of having the ability to have all of our inputs and outputs, we know that we're trying to communicate with some contract asynchronously. So we need to have some kind of way to take our private inputs and then send a message out to the contract. But at that point, we can't continue executing. We can't continue preparing this sort of pre-sealed state transition because we haven't got the result of the contract execution. We haven't received a message back. So what we're going to do instead is we're going to mint to ourselves an NFT that will record the intermediate state of our execution. So here I've got this kind of little schematic diagram. The circle is meant to represent okay, that's going to be the state of the AMM or the DEX or whatever. And these hollow boxes are the outputs that we know we're going to want to mint later. And so the idea is that this state NFT is modeling that future computation. And technically, the way that you do that is you just Merkleize all of the execution state using a SNARK-friendly hash, and then you use that as the asset ID for this NFT. That means that later, after we get a message back from the contract, in some later block, maybe the next one, we'll get this message from the contract, and then we can consume the state NFT and then open that Merkleization of the intermediate execution state, show that we're modeling the correct future, and then use the message from the contract to mint the private outputs that we were supposed to get. So the trade-off for this is that the execution is now potentially spread over multiple blocks, but on the other hand, you can actually have private interaction with the public shared state. So as an example of how you can, that's a fairly general kind of abstract description, but to see how this works concretely, let's see how we can do some batch swaps on Penumbra. So this is looking at the private state part of it. So we have our private input that some user wants to contribute to the batch swap for some block. What they're going to do is actually verifiably encrypt their input amounts with a threshold key that's controlled by the validators. That's going to be their message to the contract, effectively. They mint to themselves this private state NFT. And now the chain, when it's processing these messages, will have this batch of inputs. The threshold encryption is actually going to be additively homomorphic, so they can sum up the ciphertexts, compute an encryption of the batch total, and decrypt that. And now the only thing that's revealed is the aggregate flow into this trading pair in that block. At that point, you can execute the DEX contract just once per block, get the batch outputs, and then that can be fed into this secondary swap claim transaction that consumes the user's swap NFT and mints their private outputs. But what's really cool about this is that because we're actually executing each contract, in this case it's a hard-coded DEX, but we're only executing it once per block. And so that means that we can amortize the computational cost of whatever work we do over all of the transactions in the block because we know that we're only going to have to do it once. And so that lets us actually do a substantially cooler and more sophisticated thing, which is instead of having to do kind of middling gas optimization of every single transaction that we're going to be interacting with this DEX 1,000 times a block, we can just group all the inputs of all the assets in different trading pairs, batch them all together, decrypt them, and now we have this kind of like global view of all of the trading intent in the block that we can just globally resolve using optimal arbitrage, like get all the prices in line. We can do like multi-hop routing, and all of that is happening only once per block. So like if it takes a little longer to run, it's like not that big of a deal. At the end of that, you get all the prices, and now you can feed back into the second part of that private state flow. So this is pretty cool. We're still obviously just focused on the one application to start, but I think this is a kind of interesting thought experiment of how we could build like a really useful asynchronous programming model for doing interaction between private user state and public chain state. The other thing that's pretty cool is that actually this works. So if you want to go and like use this, the full kind of like cool globally optimal DEX part is not implemented, but the sort of interesting part of how do you interact with the state model, how do you have this like future in the shielded pool, you can go play with that at the moment. If you go to guide.penumbra.zone, there's instructions on how to play with the testnet. So cool.
All right. Are there any questions for Henry? Really? Everyone knows how to implement a private DEX already, and it's perfectly good? All right.
Hey, thanks for the talk. You mentioned that you're spreading out the execution of the contract over multiple blocks. Is it locked in for those multiple blocks, or can you anyway?
The contract execution is once per block. What is spread over multiple blocks is the user state. So, for example, in the swap application, as soon as the user submits their when a user submits a transaction with a swap in it, as soon as they see that that transaction has been included in a block, they have control over this swap NFT that already has the effectively the value of whatever their outputs are. It's just that they haven't sort of driven that to completion. So there's still this kind of atomic execution on the public chain state. The part that takes potentially a second phase is sweeping those outputs from being represented as here's the receipt for your participation that you could redeem to actually redeeming it. But either way, the execution has happened by the time that they see that they have control over that node.
Yeah, first I want to say this is super cool. Thanks for sharing. I was curious, on the execution layer, besides being able to support this function call at the end of the block, are there any other changes? And then, yeah, first.
I think, yeah, the main thing is the ability to have an end block phase. The other piece that is kind of a little bit, TBD is if you weren't doing this as hard-coded functionality, you have to think about okay, what does the trust model look like, right? For us, because the DEX is kind of integrated functionality, we can say okay, well, here's a way that you can burn these tokens, mint this thing. Later, you can do a mint of your output tokens and prove that that's honest, and that's all fine because we're pretty sure that those state transitions are correct. Whereas if you were going to allow arbitrary user code, then how do you know? You can't necessarily. You need some kind of fault isolation. And the kind of interesting perspective there is there's actually some kind of analogy lurking in the shadows between this and the kind of Cosmos maximalist, everything is an app chain that communicates over IBC, except that instead of doing IBC between these things, it's all the messaging is just done on one chain. So it's sort of app chains on one chain.
Yeah, I was asking because I was curious, maybe I know in your case it's really important to have this function called the end of the block, but I think your programming model, for example, could work on Ethereum, and maybe you have some relayer node that calls some function to do the end of the block transaction, or maybe there's like multiple block latency or something like that. But yeah, just thought it was super cool.
You also could, in principle, you could kind of multiplex this type of execution model over some other system in the way that you described, where people can make a transaction where the transaction is like registering the message or saving it in a queue or whatever, and then there's some kind of thing that's going to trigger the end phase. If you want to have low latency, I think that's kind of a challenge. And you might end up with like sort of weird issues where you're kind of like aliasing the time resolution. The other sort of philosophical point of wanting to have this kind of batched actor model is the idea that, and this is kind of getting into the MEV point, at least in my opinion, a lot of the MEV is the result of people designing mechanisms that operate at a higher time resolution than is actually provided by the consensus mechanism. And then because there's this like attempt to sort of have a higher sort of fidelity of time than is actually provided by consensus, you get all this like kind of bullshit mechanical arbitrage about the intra-block ordering. And so the other piece of this approach is it's sort of saying like, look, you shouldn't build mechanisms that can operate at a higher time resolution than is actually provided by the underlying consensus. And so really, you shouldn't even be doing any processing in the transaction handling at all. Like all of the processing should be in the end block handler.
Cool.
That's just a philosophical idea, not an actual like concrete system design, idea. Like it doesn't actually work like that. There's reasons.
Are there any more questions?
What proving system is Penumbra using? Is it Graph 16 or bulletproof space design?
So this is kind of funny, actually. As you can maybe tell from the talk, the emphasis that we've sort of had so far is like the hard part is figuring out the data flow and the data model. And so in order to be able to like iterate on that, we've actually been using a really cool proving system that's called protobufs, in which you take all the witness data and you just like put it in a proto, and then you like don't look. And that sounds extremely stupid, and in a way it is, but also, the thing that's cool about it is that you end up with a software object that has exactly the same interface that you're going to end up having when you have circuits, but where you can like just change it, in 30 seconds if you decide that you want to change your data modeling. So for example, like in the coming weeks, we're probably going to like redo the whole data model so that we have like 128-bit note values to have better compatibility with sort of ETH issues. And that type of change is like a lot easier to make if you don't actually have to go and like reprogram all your circuits. So sometime this fall, we'll then take those as a sort of like machine executable spec and then turn them into Groth 16 proofs, which is probably the real answer that you were looking for.
Well, I have a question, actually. This is more of a philosophical point, but do you think the same trick of kind of batching execution can actually be achieved on different other like protocols that aren't just DEXs, Because it feels like it relies a lot on the fact that you can, kind of batch execution. But is this all? Do you think it's more generally possible, and we just need to do more research on it, or?
So what I would say is that there's kind of two different uses of the word batching that are mixed together there. One sense is from the kind of specific DEX application sense, there's an idea of like, okay, we're going to batch all of these like trades into one trade and only execute the one trade. But also from just a general like system design perspective, there is some kind of batch execution in the sense that if we were to generalize this to arbitrary contracts, each contract would be receiving a batch in the sense of like, here's a list of all the messages. And then depending on the application, they may or may not be able, like it's going to vary how much work they're going to be able to overlap between processing of each individual items. But in general, like, if the interface is that you get all of the messages, then your application can choose, does it make sense for me to batch? Can I reuse work between different items? What is that for my specific application? But if the interface that your contract has is like, I'm getting all these things independently, then you just can't do that at all. So I think in every case, it's like definitely not worse and probably better, even if you can't necessarily get to the sort of, so like hilariously optimal thing as on a batch swap where you can just execute one trade.
All right, we have time for one more question. If there are no more, I think I will ask for Anna to come on stage. No? I think? No? No more questions? Really? Zero? Okay. Well, thank you, Henry, for presenting how to privatize a DEX.
So that wraps up the last talk of ZK Summit 8. We've made it this far. Wow! But it's not over. Wait, there's one last thing. We do this every time. It's a park bench panel. We're going to need a little bit of time to set it up if you do want to grab a drink or something. But it's an interactive panel where we have a starting group of panelists who have been selected and will be joining us shortly. We start with sort of one or two questions. We do kind of a regular panel thing, but then we open it up to questions. And it's really important that you bring your questions, comments, thoughts, because that's the only way it works. Basically what happens is as one of you asks a question that maybe has a pretty strong opinion in it, you're gonna be switching places with one of the panelists. And then we do that kind of over and over and over again. We ask them the question that was asked, we go out to the audience again. It's a really cool way to hear from a lot of different voices. And yeah, I hope you'll participate and hang out. But I think in the meantime, we need about 5 minutes or so to get set up. So if you want to grab a drink, head back here and we'll start. Are we good? Cool. Okay, welcome back. Welcome to the last session of the ZK Summit 8. We are going to do the park bench panel. This is always an experiment. It's sometimes a little messy. And as I said, it's really important that you prep your questions. Without questions, the thing doesn't work. So I need you to have some hot takes and good questions. So I think we often use this time to also talk about somewhat controversial things. And so I think our first question that we wanted to talk about was, what is ZK EVM and what isn't ZK EVM? Oh, intro round. Oh, good idea. Okay. Let's start with there.
I'm Zaki. I work on a variety of blockchain projects. I have something called Similier Finance. I've been working on a thing called Cosmos for a long time. Some people have heard of it. And that's what I'm here for. I don't know. I've been I'm a ZK fanboy for a very long time, and that's how I think I ended up on this panel.
I'm Henry. I work on Penumbra, which you may recall from the previous talk. So yeah, we're building a private DEX, I guess.
And yeah, I'm Alex. I work on Aleo, also a longtime ZK and ZK podcast fanboy, which is probably also how I ended up on this panel.
Okay, I'll ask the question again. What is ZK EVM and what isn't ZK EVM?
So, there's I will frame this thing so there's this 4 kinds of ZK EVM blog post that Vitalik wrote, which is an attempt to systematize this actually very difficult question, right? Because it basically anytime anything happens in ZK EVM, and the last big ZK EVM thing was Paris, Polygon comes out with their we've made a ZK EVM and everyone else's ZK EVM is not a ZK EVM, and then everyone else with the ZK EVM says they're all their other counterparties are also not ZK EVMs. So this does seem to be a little bit of a kind of a Mean Girls kind of thing going on, where you're either in or you're out, and the in group is being the one true ZK EVM. I think one of the biggest challenges of this is that ZK EVMs are right on the cusp of being turned from being research projects into something that you can tangibly sort of understand end to end and build upon. And it's going to be probably the ultimate question, I think, is you can tell you will know a ZK EVM just so this reminds me a lot about when people were building the first proof of stake EVMs, and it was there was are you bytecode equivalent? Are you RPC equivalent? All of these things. There was this huge conceptual framework. And you know what actually mattered? What actually mattered was if the developer community could adopted your thing and decided that this was good enough for them. So EVM equivalence ended up being very much this good enough question in the BFT proof of stake setting. I think the same thing will apply in the ZK EVM setting.
I have no skin in the game, so I don't know. To me, a ZK EVM is something that somebody makes, and they write a blog post about here's our ZK EVM, and they explain what it does, and then people can argue about it. I don't know.
Hot takes. Also, if anyone makes a meme of Mean Girls with all the names of the projects above the characters, bonus points. Yeah, so I guess I don't have much to add. I think Saki gave a great answer. My quick take, I think, is that in general is kind of the lower down you try and achieve EVM equivalence, it seems like there's a performance trade-off, or you have to kind of make compromises in certain things. That was really the thrust of Vitalik's post, I think, and I think that's kind of what we've observed with the different ZK EVM implementations. And so I think it really comes down to the community of people around this that will end up adopting something, and they'll really decide at what level does it matter if you're down to the bytecode compatible, or if it just okay, if it's fine to at a higher level, if that compatibility is okay. Of course, Ethereum has huge network effects, right? They have the entire ecosystem of dApps. They have a whole ecosystem of Solidity developers, people who are familiar with that model. And so I think that's why people try and really closely hew to it. But I think potentially there's a lot of really interesting constructions coming out that are much more performant. different ZK VMs that kind of give you a big performance boost, which potentially will, I think, over time, you'll see people building on those ecosystems, and we'll kind of get I think, probably a diversity of different VMs or ZK VMs that serve kind of specific use cases.
Can I pivot the question a little bit?
Sure.
Okay, so maybe to make this question more relevant to the people who are on the panel, Henry has this like sort of half-baked maybe VM idea, and Alio has a more baked VM idea, but neither of them are emulating anything with existing network effects. And you're like trying to restart your own network effects, and we have lots of people who are here, whether it's the ZK EVM people or the RISC-0 people, who are trying to take advantages of the network effects of something that already has network effects. How do you think about that?
Yeah, so I think, my opinion is for any new protocol or product, you have to differentiate and offer something that is unique and new. I think I hear a lot of time because so Alio, we're building our own language called Leo. It's a high-level language that compiles down to an IR Alio instructions that then gets I R1CS. So it's kind of a new ecosystem that developers have to learn to build in. And I hear a lot of times like, oh, well, who wants to learn a new language? And I actually don't like that question, because I think everyone in this room and most developers I've ever interacted with, if something adds value to what they're doing, if they see something as legitimately interesting, they will absolutely learn it. Look at Rust. Rust is a new language, right? So and most of the projects today in this ecosystem certainly use it. So people thought Rust was interesting and useful enough and provided some value such that, okay, they're going to go ahead and use it. So I think it's really just a matter of, of course, on Alio and every project that's starting from the cold start, you have to figure out, okay, how do I want to be different? I think that's really the starting point, is how do I want to be different, and what's the value that I can add? Maybe that you don't have to say it's better than Ethereum or worse than Bitcoin or whatever, right? Whatever you don't really need to compare it in that way, but I think it's what is fundamentally different. What can you do in this world that you can't do anywhere else? So that's how I think about it.
So I guess maybe I'll say a bit about how we think about network effects, and then segue into sort of ZK VM generally. The strategy that we have is basically, try to build one useful application, and try to have sort of a very, very narrow initial scope, but build something that is just like genuinely better because of the privacy features that it has. So we're not actually trying to build some kind of like programmability thing. The talk that I gave about like, here's an idea of how you might do that is really just an idea that it's a possible generalization of the concrete system that we're trying to build. And so the overall strategy of Penumbra is like, okay, how do you build like a DEX that's better as a DEX because it has these privacy features? And then once you do that, you're going to end up with a bunch of users who are using the product because they're getting some kind of value out of it. And once you have that, now you have some kind of audience that might be interested in interacting with some kind of future programmability system once it exists, right? And so that, I think, is a different kind of network effect. It's a much more direct, like, let's just build like one thing, rather than let's try to build some kind of environment where other people can then build a thing. I think that if you get that to work, it's like obviously much more powerful, but also it's a much harder lift as a project, because now, for all of these other people who are going to be writing applications, you're just kind of like another project, whereas whether they do or don't do that, for you as a project, that becomes this kind of like life or death thing. The second point on kind of ZK VMs generally, I think that the existence of really any kind of ZK EVM is just a really incredible like technical tour de force as a matter of like SNARK engineering. However, having to have compatibility with EVM bytecode is not really just about the bytecode. It's about the state model. And my personal belief is that like the state model of Ethereum was like designed to be a like transparent system. And when you try to make that private, it's not just a matter of like, oh, well, we'll make all the we'll like snark all the state transitions or something, but if you have a notion of privacy, you have a fundamentally different data model, because now you have different entities that are supposed to have access or not have access to different pieces of information. And so it's not, to me, it feels like the programming language or the bytecode or whatever is actually this like, second order, like downstream thing of the more fundamental thing of like, what does it mean? Like, what is the data model for like private computation on chain, right? And for example, with Aleo, there's, you can effectively have sort of like every transaction be its own little like micro rollup or something. For us, we're trying to focus on like, how do you have interaction between like some like public computation and some like individual like private data, and try to have some kind of differential privacy or something there. But I don't think that it's like really clear what it actually means. I mean, in the sense of like, I have my opinion, but that's not the same as like a market validation, right? And I guess the concern that I have is that if you start by saying like, okay, we're going to take the path dependence of Ethereum and then like make it ZK, you may end up like sort of paying an enormous amount of cost to do all this like complicated proving, but then it's like, great, well, now we just have this like centralized sequencer. So, what was that?
Cool. All right. I want to see, do we have another mic? You have a mic, right? Are there any questions, comments, ideas? Oh, there's one arm right up there. All right.
I feel like someone who actually makes a ZK EVM should like
might want to weigh in on that.
Might want to weigh in.
Can you make sure the mic is on? Sorry, just give it a second. What number is that? There we go.
Oh, now we're here. Yeah, I regret I was not on the panel when the question was asked, but
well, I can
still give my answer.
You might be up here in a second, so.
It's interesting that we're using in ZK EVM. We're actually not using the ZK property properly, right? Like it's not for zero knowledge. It's standing for zipped with cryptography, to use the succinctness to scale computation. So you can think of it as like just computational layer, just like IP protocol is for data and SSL protocol on top of that is for privacy. Similarly, we can build protocols on top of ZK-VM that provide privacy. My question is about privacy because you guys are working on privacy mostly. And it's going to be a controversial question, of course, like a spicy one. So,
hot takes.
We see an attack on privacy happening recently with Tornado Cash being put on our FAQ list. And it seems like a systematic approach, and like it's been boiling for a while with elliptic chain analysis, like the soft censoring of transactions by exchanges, and now like straight on attack on the privacy protocol. How do you feel about the path of development of these regulations? What can you share about your ideas? Like, how do you see the space developing? Like, is it going to affect all the privacy protocols? Do you expect like compliance? Do you expect non-compliance? Like how you think about the situation for the future?
Okay, we're gonna have you come up, but first, why don't you answer that question? You're gonna be taking Alex's spot. Alex is gonna switch for Alex. Keep it easy.
That's good. We can just roll. There's enough Alexes
Only
in this
Alexes
room. We can
are allowed
just
to
fill
sit
this
here.
chair all day.
All right. Go ahead.
So I can take a first stab at that. So first of all, I think the OFAC regulation, or the action against Tornado Cash that you referenced, I think there was some news yesterday that I thought was encouraging personally, where they laid out a path where, okay, if you had interacted with that contract, you could potentially clear your name effectively by going through some process. So I think the process that they proposed was a little bit burdensome and may not really be what I hope we end up at, but I think at least now there's some understanding, a more pragmatic understanding from the view of the regulators. Now, I think my personal belief with existing decentralized systems today, let's call them Bitcoin and Ethereum since those are the two biggest, is that model is so much more radically transparent than the existing financial model of banks that I really think that it's going to be difficult to, if we imagine a world in which Web 3 overtakes Web 2 and Finance 2 overtakes Finance 1, I think without without stronger privacy guarantees than those existing systems offer, it's just not going to have people adopt them. I mean, I think look, I think we have to be honest with ourselves on a lot of the volume that happens on Ethereum. You know, people do DeFi and they do NFTs, and I think a lot of people view that as fun and interesting and cool, but very few people, I think, are getting their paychecks there. Very few people are doing what I would consider real economic activity. And, you know, if I send Guillermo one USDC on Ethereum, not only do I know his entire bank account effectively, but everyone who's ever interacted with him and their entire accounts. And I think that model, like, to me, that just seems like to be a fundamental blocker for adoption. Now, I think you raise an interesting point where do you need to bake everything in one layer where you have privacy kind of guaranteed all the way up, or can you separate it in layers? I mean, I think there's legitimate points on either side. I mean, obviously, Alio's taking the approach from the bottoms up because we think that gives you the strongest, most unbreakable guarantees there. But I think, you know, it's really interesting to see how this ecosystem evolves. But overall, I guess the last thing I'll say is I don't think any of us can escape the need to be compliant at some level. But I think what we can do is advocate for, and the best way we can advocate for what we're building is proving they're useful. Right? And that's why I really like what Henry said a minute ago, where it's like he described privacy as a feature of a product that people actually use. Right? I think this is something that I don't think we as an industry focus on enough. It's like, hey, let's really talk about like how does this matter to some consumer, right? What's the consumer-facing product, and then building back from there.
I mean, one thing that I think is just like interesting about this is there's some regularity to transactions on Ethereum that I control, like sort of making, paying invoices and stuff like that. And the attempts to hack me are directly correlated with like the regularity of those payments. So basically, like, I feel like this is like kind of like the most practical thing that I've been seeing as like exposure to is like, oh, like the attacker sees that like typically we pay invoices around this time of the month, and then like spear phishing is just like pervasive like that time of the month. Which has been an interesting exposure, like privacy exposure, and I think potentially a good articulation of like why that might matter. I think also Henry has like a really good rant about like how IBC is a good mitigation against these things, which I'd like to hear.
Well, setting him up.
All right. I mean, that wasn't what I was going to lead with, but sure.
Set spike.
So I think, yeah, like there were some good comments on the kind of like regulatory side, like explaining like the value of privacy or whatever. To me personally, as a builder, the thing that seems like the most useful thing to do is to build products where the privacy is like clearly this kind of core enabler of what that does, right? So for instance, if you're trying to have like market making on chain, and somebody can just like open up a block explorer and see like who are the top 10 performing LPs, and I'm going to build an index out of their strategies. Like effectively, you cannot do like good market making in that kind of environment. And so if you build products that just like are better products because they have privacy in them, I think it's just a much better place to be, both in terms of like having a larger user base and a kind of like more tangible near-term argument for why it's important. I guess, yeah, on Zaki's sort of like, request for comment, I think the existence of IBC makes the type of censorship that was done a lot harder because all of these different sort of chains just communicate with each other permissionlessly. There's not some kind of particular set of, this is like the address of whatever. Like you would have to like block entire chains or like entire bridges, right? And so I think there's like a lot more collateral damage if a censor was trying to, put a stop to like some particular thing. I also am not really sure that the tornado cache OFAC designation was this like carefully calculated like next iterated step in this like big long game or whatever. Like to me, it actually seems like a kind of like ham-fisted, like, you know, someone told us that we had to do something about this thing, and this is something that we can do. You know, like if you look at the actual law before that is supposed to give that power, it talks about like sanctioning specific persons. So like, I don't know, did we accidentally like grant legal personhood to a smart contract? Whoops, I don't know, like that'd be a kind of funny implication. But none of this really seems to be thought through. Like the fact that there's like viewing keys where you can like see exactly what your account activity is and like demonstrate that to some third-party auditor. Did that matter? I don't know, apparently not. So like, what's the point of trying to like build a system that has regulatory like capability built in if the regulators don't really seem to care?
I thought it was interesting that like with this license thing that got announced, they did not ask for the viewing key. It seems like that would be like the logical step in like getting a license as a US.
Again, to Henry's point, I mean, this might just be ignorance on the part of some of the bureaucrats who wrote the rule. I mean, I think there's often, and speaking as someone who's worked as part of a U.S. government bureaucracy before, I mean, it's oftentimes, you know, people like to think of it as like the Illuminati, but sometimes it's a little more like Office Space, and so, you know, so I think, yeah, these things will evolve. But I guess, and I know I need to pass the mic to Alex, but the last thing I'll say is, you know, look, I'm actually really optimistic about this. I mean, if you go back in the history of cryptography, I mean, I think we've made enormous progress. I mean, there was a time when the fundamental cryptographic algorithms that we all rely upon were export controlled. They were like, and it was like illegal to take them around the world or like tell anyone about them, right? There was a time even more recently with crypto, like there was legitimate talk of would a government ban Bitcoin or ban this stuff? And I mean, that's at this point just seems so remote as to be ridiculous, you know? And I think we're kind of on this next frontier of this technology. And, you know, I think it's of course like early days. It's too early to say which way it's going to go, but I think there's a legitimate path for it to become accepted and legitimate and welcomed even by institutions and governments. So we'll see.
Cool. Thanks, Alex. Come on up, Alex.
Alex, tap in.
All right, do a quick intro. Alex G. Let us know who you are.
Hello, everyone. I'm co-founder of Matter Labs, which is the creator of ZK Sync, the first ZK EVM.
The first.
All other ZK EVMs are not ZK EVMs, right? Not just the first, the only.
No. We were the first to introduce the term, the first to implement the prototype, the first to open the testnet, and we will be likely, hopefully, the first to hit the mainnet. But the others are also ZK EVMs, of course.
All right. I want to open the floor. Are there any other questions? Anyone who might want to weigh in on anything that's been talked about? And I will wait. We do need questions for this to work. Comments, thoughts, anything?
Considering that we now have a variety of trustless setups, my personal preference recently has been bulletproofs. What's the continued justification for deploying new crypto systems using Graph16 and other trusted setups?
That's opinionated.
You said hot takes.
Yeah, hot takes gets up. Although Bulletproofs doesn't have a trusted setup.
He said trustless. I think he said
trustless
setups.
setups. Okay.
No setup.
Oh, got it.
Yeah, I mean, like, the setup is like one engineering axis out of like, you know, a dozen or whatever, right? Like, personally, if I don't, this is just my opinion, right? But I think that if you have a situation like, say, like the sapling ceremony, I actually really wouldn't use the term trusted setup for that. I would say that's a decentralized setup. And I don't think that there's really a meaningful technical risk there compared to, say, like, oh, I wrote the circuit wrong. I like didn't constrain something. Whoops, there was an inflation bug. Like, whatever. Like, those all seem like way bigger risks to me on the security side than, you know, 299 out of like 300 participants were all collectively dishonest, and like there's like, you know, the one holdout that they like wrench attacked into colluding with the attack or something. Like it just, and then the other thing that's nice about Groth 16 is that like it has like very good constants. And if you look at like I think in practical terms, like who is the marginal user of some privacy system that is like, you know, I would be using the privacy system, but it has this like setup. Like I think that much more important is like what is the actual performance of the system? How does it work? Like for Penumbra, for instance, like it's actually pretty important that you be able to do the proving quickly, because you want market makers to be able to respond to price information with reduced latency, and you also don't want them to be on this like separate sort of transparent thing, because the point of like the whole game plan for Penumbra is like you use the market making to bootstrap the privacy set, right? So then actually having performance is like kind of probably also like directly important for privacy. So I guess like what I would say is like there's a lot of different engineering axes, and I think that like the specific kind of security of having a setup or not is like not that high on the list. There's other reasons why you might want like a universal system, but I think not for security, in my opinion.
Well, the obvious answer, like on the surface, is that it's a lot cheaper to verify Groth 16 on Ethereum, like on a system like Ethereum, where it's quite expensive. So like Groth 16 verification costs around 300,000 gas. A full Stark verification is currently at 5 million gas. That gives you a lot of like 20x, almost 20x, like 18x difference. That enables you, for example, to do more frequent checkpoints, because you need to amortize. You need to wait for enough transactions in this batch that you're rolling up, if you're using it for a rollup, for example, to justify making this checkpoint and verifying the proofs. So it would be great if if Groth 16s are going to be used still in the future, that they are made as universal as possible, that they are just approaching, like targeting certain proof system where the parameters, the verification keys are passed externally as inputs, so you can reuse it many times, which gives an incentive so for many people to participate in the ceremony and make it more secure. But over time, for like in the long run, I think that we'll absolutely have to avoid doing trusted setups. You cannot build the internet of value, especially with privacy, that no one can actually see inside and check that it's still keeping integrity on something which like depends on 300 people. Like no matter how legit and prominent those people are, like to have institutions move to crypto and move all of their transactions there, it must be completely transparent, and that's where we're coming to in a few years, I think.
Oh, seems fine. Like, you just like make the setup bigger. Like, I don't know. I think that there's not like one of the things that's cool about Groth 16 is that because you actually have a hard-coded statement, like the wiring is free. So that's kind of like a fundamental thing that is cool about that from a performance standpoint. And I don't think that goes away. Like, I think that the solution is just that we like get good at doing setups, which is actually what's happened, right? Like comparing the trajectory of like the first like Zcash setup to the sampling ceremony to like all of the ones that are currently ongoing. It's like, okay, this is like a thing that it's like a collective coordination problem that people who build the coordination technology like get good at coordinating. I don't know,
Cool.
seems fine.
I don't know, like every ceremony requires a lot of attention, a lot of diligence in like how you actually prepare your machines for that. Like you might have 300 honest participants, but all of them, for convenience, just use some software that they download from this link that the participants, the organizers gave them, or they participate from a browser app where they do everything in browser, which is like, like you want a lot of different eyes, a lot of different implementations.
I agree, but I don't think that that's actually a problem with the setup. I think that that's just a fundamental problem with making a circuit. You also have to get the circuit right. You have to have assurance on that. What happens if somebody puts some kind of subtle bug door in the constraints that allows
that
them?
is transparent. That is auditable. You know it. There is a chance that people will discover. Here you can do it theoretically, fully covertly, and not letting anyone know. And this is especially problematic in the context of private systems. With open, transparent systems, we will at least notice that, if something happened in ZK Sync with Plonk, with ignition trusted setup, it would be obvious that the setup is compromised. But with a private system, it would not be obvious. There can be things that go wrong and no one knows, right? Like some hidden minting of assets, etc. So I think for wide use of privacy, we really want transparent systems in the future. But that's not an urgent problem.
I think we're gonna move on, if that's okay. Henry, I think you're off, and I think you're on. Thanks for being on here, Henry.
And I have to be on a Twitter Spaces at 6, so you gotta get me off this.
You have to get off soon?
By 6.
You have 21 minutes.
I have 21 minutes.
Okay. Do you want to introduce yourself?
Sure. Hi, I'm Luke, also known as Kayaba online. I volunteer around Monero, and then I have my own project as well.
Nice. All right, are there any questions, comments, thoughts, anything on what was just said? Alex, there's someone right there.
Oh, sorry.
Could someone describe what is the difference between schemas based on inner product argument versus the existing solutions? I mean, the trade-offs.
So that's a question. So that's not an opinion. So yeah, I think.
So the question is, can someone describe? My answer is, I'm not sure. I can't.
Did Benedict already leave? I was going to say.
Can you say it again? Describe the difference.
Inner product argument, which is the pasta curves.
Yeah.
In Zcash. They have a way to do this without trusted setup, but apparently there are some speed or performance trade-offs, which I'm not aware of. Maybe someone knows.
Yeah.
What is this?
There was an episode I did recently with Halo, Dara, and Strad, and we talked about that, and I don't remember. So you can listen to it. Yeah. I think we talk about something like that.
That was what I was thinking about with this question. I think the trade-off is what, inner product stuff versus KZG. It seems to be the current trade-off space of people who are building these general purpose protocols, but I am not the person to try and explain this either.
Cool. All right, any other questions, comments, ideas? Back there. Nope, there.
I guess my question's a little bit pointed at ZK Sync. Seems as you're up there on the stage, I get to ask you a question. It's really cool what's happening with the ZK EVMs, but do you think there's more of a fundamental architectural kind of a different approach you could take rather than, because right now with the EVM contract, the state has to live on effectively on a single machine, right? There's a capacity to how big the state can be, right? And so is there a thought into the direction that could go into expanding that into a different kind of architecture as opposed to something like EVM? I know there's obviously shards and stuff, but ultimately the data still has to fit in a smart contract. Because with ZK Sync right now, I understand you put all the data back onto Ethereum, right?
So there is no fundamental limits on how large the state can become and how we can process it. We could use some parallel transaction processing techniques to like prepare the block before it's being proven, and proving always happens in parallel. We can parallelize all proving really well. So it's not really a question of how you structure specifically ZK-EVM, it's just how you build your blockchain in general. One thing that ZK-EVMs can do differently from Ethereum is actually diverge from Geth and the existing Ethereum clients that are optimized for the broader usage, like for having a lot of full nodes run on consumer hardware, on ordinary laptops, and build special clients that are optimized for being run by validators, where you have higher requirements, where you can say, let's keep all of our state in memory. So it's going to be a lot more expensive, but like in the context of having only like a dozen of those validators actively running the consensus, it can be a good trade-off. And this is what we're doing. Like, we're not using Geth. We're building something that will be potentially more efficient than Geth as a full node. But that's not specific to ZK-EVM, in my opinion.
Do you have any thoughts? If not, he's going to take your spot.
Cool. No, the sacrifice is accepted.
Okay. All right, come on up. And thank you for being up here, Zaki. And I hope you make your call. All right, here's a quote. Oh, wait. Any questions? Throwing it out there. Okay, there's somebody there.
Hello, guys. So after DeFi 2020 and NFTs last year, I think now it's a comment for me, of course, but I think it's identity season.
Oh.
And how can we leverage zero knowledge to protect identity of oneself on the blockchain? Do you have any thoughts on that? And
sounds like a comment.
Yeah, comment / question.
Is your name Alex? Because you have to be named Alex to sit here.
My name is Alex.
Okay. Is it actually?
No, it's not.
Oh, damn. I thought we were on a roll.
Got you.
Okay. It was 80% chance. Okay. Does anyone want to answer the question about ID, ZK ID, or ID on the blockchain?
So this isn't really my field, so I may sound like a total idiot here, but I'm going to try my best. To put this kind of in Monero terms, I'm not here to shill it, it's just the best way I understand it, and if I'm going to give my best answer, I have to rephrase the question a bit. There's talks about a transaction protocol, and one of the things it's doing is it's working towards, I'm really not trying to shill Monero, I'm just sorry. Yeah. But my point is they're taking a public key, just as we all know them, except this public key is actually the aggregate of multiple public keys, each for their own purpose, and because yada, 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 discrete log problem, you can't change any of the individual public keys. You have to have them all correct together. And when we're discussing decentralized identity, I think the simplest way you could implement such a system is simply by having an aggregate public key. You can say, oh yes, I have the public key that says I'm a US citizen, because it's not actually a public key, it's just a point. And you're just saying, yes, the point that says I'm a US citizen is in my public key, which is what I'm using for decentralized identity. But you can very quickly and trivially create a circuit, whether it be Graph16, whether it be some bulletproofs you're running on your computer, whether it be a Halo 2 instantiation, that just blinds it. It doesn't actually change any of the value that you've embedded in the point. It just says, hey, previously I was using this value, but I know some offset that lets me transform it. So an app doesn't need to know who I am at a base level. It just needs to know I have appeared as this new static identity, and I have these properties in my public key. And obviously that doesn't solve the problem where you have multiple people creating IDs, yet you can also use ZK SNARKs to say, yes, this offset is derived from a very specific process, and because of that, I'm not replacing it with anything else, but even though I'm creating it with this specific process, it's a SNARK. You don't get to see how I did it. So part of me wonders why decentralized identity hasn't done better, because I feel like when I try to describe it, it's very simple, and that's probably why I don't work in the field, because I'm missing something. But that's my attempt at a stab at it.
Cool. Any thoughts? ID?
Yeah, no, I agree. I think it's going to be one of the next big things, because when I'm asked to like log in with Ethereum with my address, or like receive POP NFTs on my address, and like also attach for convenience the ENS name like with my handle to this address. It's getting weird because like now you're logging in, everyone knows who you are, everyone knows where like all the things you've done, where you've been, with all the NFTs, with all like, you know, like all the like and tickets to some events that you purchased. It's strange. So you really want to be able to connect in a way, you know, like this Apple ID is connecting you, like which is implemented better than Google ID because it creates a like unique email for every app that you're trying to connect with, and it only shares this like random pseudo-random or like pseudomized ID to those things. Totally, and it's actually not that complex to implement. So it's a matter of good UX and a standard that everyone will accept. So this standard question is problematic. You can think of this XKCD crypto standards.
Yeah, I think that's the problem in general, is coming together on a standard that everyone agrees on. And I think identity suffers from a usability problem too. And so when it suffers from a usability problem, you basically just get MetaMask installed in everyone's browsers, and that's it. And you know, it's there's 100 different wallet providers all trying to break into this market, but ultimately everyone's installed MetaMask now, so it's very challenging. So obviously as an industry we need to grow, and we need to obviously keep working on these new technologies. What I would say is I think we're missing a layer of, and it was really interesting, I think one of the other speakers talked about creating something of actual value for users, because that's what makes them install a new browser extension. Yeah. That's what gets them to drive change. That's what gets Brave installed instead of Chrome. And I think we need to think a lot more about what technology, and you know, so I'm the founder or co-founder of Spacetime. We're building a decentralized database, and one of the things that we're really passionate about is rethinking the whole model. So yeah, I won't go into it.
Yeah,
but
sorry, I think I forgot to do an intro to you, hey? Oops. All right, Alex, switch with not Alex. What's your name? Let's find out who you are. And we're going to do another question in 1 second. So thank you, Alex, for being on. And welcome, person who does ID. What is your name?
Alex. My name is Miguel.
Okay, different name. So just introduce yourself real quick.
Yeah, my name is Miguel. I'm working on a lot of open source software like ZK infrastructure and the game. Yeah.
Cool. All right, any more questions, ideas, comments? I think I saw a hand right there.
Hi. So, well, it depends on you ask. A strong argument against switching to digital voting from ballot voting is that the ballot voting process is it's leaky, it's faulty. It's not so has other faults, but it is auditable by everyone. And going to like a digital voting scheme would require a very sophisticated one that then puts this into like an oligarchy that can then that is then the only set that can actually verify that this was done correctly. Now this argument has a risk, a slippery slope that it can just become anti-intellectual, but I do think some of this applies to the question of let's skip out privacy for now, but like using ZK for scaling. If you go for this kind of complicated technology, you could also just be waiting for technology that is much simpler for scaling than using zero-knowledge technologies to achieve this, which is kind of the tendency that Bitcoin has. So my question here would be, like, what is your view? Does this apply to zero-knowledge technologies as well?
What?
Like this argument, should we replace, just for the sake of scalability, replace systems like, for instance, Ethereum that are much easier to audit by a broader set of developers or eyes than something than technologies that have a much more restricted set of eyes that can actually audit it.
Should you replace ZK? Should you just say the question again?
Yeah.
I couldn't
So
quite get it.
are there cases where you would say, ZK shouldn't be replacing this technology because the other technology, while it is less efficient, is much broader, can be audited by everyone?
Okay.
Say, for instance, Bitcoin.
Do you have any answers on that?
I can give it a go.
Go.
So I think what you're asking is there a downside to privacy, and is there a downside to making things zero knowledge so no one can see what's happening, right?
No, not quite. It's the technological implementation of that. So how complicated the implementation is to audit for a broad set of eyes.
Oh, okay. So
like in the same way that like ballot voting, like anyone can like check that very locally in their district ballot voting was done correctly.
Yeah, well, I would actually argue that how many in here have audited a Ethereum smart contract themselves? Or how many times, have you done it 100% of the time for every smart contract that you've used? Probably not. I think it's really unrealistic to think that everyone's going to audit every single contract that they use. And so actually, I think this is one of the things that we need to look at in Web3 is, okay, how do we make it, easier for people to look at a smart contract and understand what is it doing? And there is obviously an element of trust here, but you still have to trust that, the web dApp that you're using is still using that technology and not actually going, oh, actually I'm going to use this other contract. And obviously there's things around signing, but again, how often do we check the contract key, that we're signing away from? So I think one thing that we rely on today is the fact that people can audit, and people do audit this technology. And I think that won't change because it's ZK technology. I think, in fact, really, the fundamental thing will be we'll still have the same problem that we have today, which is we have thousands of different circuits or programs that we need to find a way that people can audit them easily. And some of those, there are ways around this, right? Rather than having the developer to be able to change everything and write very explicit code, can we create some sugar syntax to say, okay, if we're transferring from X to B, do you really need custom code to do that? Because if you have custom code, you can sneak in some stuff. Like if you've looked at the OpenSea smart contracts, they have a God clause where it's like, oh, if it's OpenSea's key, you can just do whatever you want. Yeah. Right? And so these things exist because we allow people to write custom code. So I think, yeah, that's probably my answer.
Can I just add a sentence?
Sure, go for it.
I was just going to say that I think no matter what protocol we discuss, there's going to be a few different numbers to look at. There's going to be amount of people who would like to audit it, but don't try to, amount of people who try to, and then amount of people who do. And I think if we throw ZK into the stack, the amount of people who will try to in any decent matter will immediately go down because they'll shut off, they'll realize it's not for them. And, well, yes, we can dream of a future where it's automated. We do have to consider if we practically want to get more developers involved, we have to promote a level of accessibility. And anytime we pick a more complicated protocol, that's obviously going to be a trade-off. It's decreasing the amount of developers who can participate, but it's gaining us efficiency. And no matter if we're discussing ZK or not ZK, if we're going to get more efficiency, we're always going to appreciate that.
Yeah, just to conclude, I think it's always a trade-off between education and design options. So we have to figure out what's the best option for each case, and yeah, that's it.
Are there any questions, comments? Anyone else? Let's throw it out there. You had your hand up. What happened? No? Oh, you can bring it back. You can actually bring it back to any topic we've talked about today. It doesn't have to follow. This is a very fluid format.
Oh, this is going to be even weirder, actually.
Okay.
This is really, actually, I think it makes sense for ZK audiences. I'm going to really put my tinfoil hat on.
Okay.
And ask the question, what happens if one of the cryptographic assumptions that we have for a lot of these ZK protocols is broken? On the auditability process.
Ooh.
Like, how do we know? How do we know? How do we know that this isn't like another NIST debauchery where you put in specific numbers that happen to be surely random, but probably end up having a backdoor? How are we sure? And do you trust yourself on that?
Wow, hard question.
Okay. Well, you're going to come up just because you're going to come up, but I don't know if you can answer this question.
Well, a lot of the ZK technology is based on the encryption that has been proven out. So I would say it's not just this magical new thing that we've decided, oh, we're just going to try this. But of course, as you mentioned, there is concern. And I think that's why we need more people creating these different types of algorithms rather than taking them from the government, which is definitely not a good idea. We could maybe take them from a broad range of researchers and have more auditing done. And I think that's really the only way. And ultimately, you know, SHA-1 was broken, right? So we need to be aware of that as an industry and be ready to move to something that's safer and something that's better.
Is this true, actually? Because there's a bunch of weird algebraic assumptions that we make for a lot of the ZK systems that we have.
Go on.
But anyway, sorry.
I think it really depends on what assumption you want to talk about. If you want to talk about the discrete log, like, oh, if that's broken, we have a lot of things going on tomorrow. Personally, I'm waiting for P equals NP hard crypto to come out. If someone got that, let me know. But then, of course, we have a variety of other assumptions. We have discrete log, sure, we trust that, we rely on it every single day. And then in threshold signatures, I believe one security of model of Frost, which I cite just because I also have worked with that, is premised on one more discrete log, which says if you know a bunch of discrete logs, you still can't find another. And as a non-academic, that kind of just sounds like the discrete log problem. I don't get why it's a different assumption. But obviously in academia, we constantly have these new assumptions. What I think it's important to look for when we're discussing ZK proofs is, one, that they're actually formally proven, have gone in review, but two, my big red flag is when they introduce new assumptions, because that either means they're revolutionary or you should be running away as fast as possible. To circle back to Monero, just because that's what I'm familiar with. I have a frame of reference, okay? We were excited.
He's a Monero guy, for sure.
Thank you, I appreciate that. We were looking at this one protocol called Triptych. It was either Triptych or Arcturus that had this property. I think it was Triptych. And it was based on I think they called it a dual discrete logarithm assumption, where it was impossible to find two discrete logarithms, blah, blah, blah. Nope, that was broken. Someone decided to do a proof of concept implementation, just try to move it forward. Nope, it was worthless. That assumption did not hold. So obviously there's varying degrees of assumptions, but if we're not introducing new ones and we're going through formal review, I'm more concerned about the implementation attack surface rather than the theoretical one.
I guess as a person who writes a lot of weird peer-reviewed papers, what is formal review to you? And specifically, does that apply to AGM as well?
Wait, you're getting up here. You guys are actually switching places soon.
So I actually stay out of the formal side of academia, so it's hard for me to comment. Hey, I just work here, okay? I'll write your code. I'm not going to build the next bulletproof. Beyond, obviously, conference inclusion, which of course doesn't magically mean a paper is valid, but obviously is a great show of confidence in it. It does kind of become an ad hominem thing, where if there's developers I respect and trust, you say, yes, I've reviewed this paper, yes, I didn't just skim the abstract, I read over it. But when you start having other developers review it, when other researchers chime in and say, yes, this is a valid proof, yeah, you believe it's a valid proof. So obviously it's about web of trust, but the easiest check mark for me is always just going to be conference inclusion.
I did hear one thing today, and this is second-hand, actually. But one of the challenges I heard today was that people were, because ZK proofs take quite a long time to prove, people are a little bit more risky on the encryption level that they'll do with them. So they'll just turn it down a little bit because it proves quicker. So that's maybe something we need to watch out for as well.
Okay,
I'll give you instant verification if you accept anything I say.
Guillermo, you're taking the middle seat. Thank you, Mr. Monero. To him. Oh, actually, yeah, to him.
Oh my, I'm up here now.
Can you answer your own question?
Did I answer my own
question?
Can you? Can I answer my own question? Oh, I certainly have thoughts about peer review in academia.
Oh, yeah.
Although I think we had
talked
some
about that
at an episode, if I recall correctly. But that involved a lot of sake. So I guess if you want to hear the full thoughts, it probably involves at least one bottle of sake.
That's true.
That's an open invite for anyone. But anyways, more generally, yeah, peer review is kind of a weird thing that is unclear to me, and unfortunately, it's kind of the best thing we have as far as I know. But if someone come up with something better, then oh no. Okay.
Oh.
But if anyone comes up with something better,
we're bringing
then
the hair color back on stage.
Well, I mean, I just want to point out that we have an industry where like the product is the bug bounty.
This is true.
That's another alternative approach.
This is very true.
Henry, do you want to come back up? You could. No? Okay. Any other thoughts, questions? People who want to weigh in. This is the last session of the ZK Summit, so even if you had like thoughts from previous talks, just to sort of get that conversation going.
All right. So let's say you don't do math for fun, and you're at your first ZK Summit, and you've had that bottle of sake, and you're like, okay, I want to build stuff for users, and we know that ZK can scale. We know that ZK can make transactions be like worth microcents. What's the most important stuff in like the last 6 months or the future 6 months when it comes to new capabilities that allows you to build product for users that is awesome or is bullshit, in your opinion?
That's a great question. I don't think there's an opinion in there. I think that's a good question, right? It's pretty balanced.
I wasn't sure I understood what was the last part of the question? Sorry, could you repeat the very last part of it?
Not including scaling and like microcent transactions. What new capabilities of like current ZK tech that's showed up in the last 6 months, or you expect to show up in the next 6 months, has the most new, useful, and interesting capabilities to build user applications? Right. So what is bullshit and what's not bullshit?
So it's like proposed use cases for ZK, basically, not scaling.
Yeah, or like.
I have an hot take on this. I think ZK can be very useful for compliance issues. Dan Bonnet actually talked about this a bit. Compliance is very important. Like, you can just submit a ZK proof and and like do your taxes and stuff like that. And I'm very bullish on compliance. Scalability was very talked about today. Privacy as well. So compliance, I think, is my hot take. So,
I mean, I'm a bit biased, but I think our blue-haired fellow right here actually had probably one of the like craziest weird ideas where ZK is kind of used for something quite new, but it required creating new mechanisms. So specifically for things like shared, like very global state, things you can do with ZK are not obvious at all that you could do before. So I think that's a very cool application. I mean, and this is, I'm assuming by kind of like cheap transactions, you mean like you don't just use the asynchronous property of ZK, you actually use the ZK part of ZK. I think is a very, like, I don't know. Anyways, that's what I'm assuming that you mean by like cheapness or like easiness. Like you don't count that as part of the cool tech that's coming up. I think that is a cool one.
Yeah, probably a couple of things. Like I think this space is moving so fast that it's hard to keep up with all the new improvements. Like every couple of months, a new paper will come out with a new exciting idea that's kind of like making things faster. And I think if we can get ZK tech, there'll become an inflection point where ZK tech becomes so fast and so good that even from a scaling perspective, right, it just makes sense for it to be used. And I think the big thing that Web3 is missing in general is that usability layer. Like, I'm not going to use an app if it like takes 20 seconds to like submit a transaction, right? And so there is coming, and it is, whether it's 6 months, whether it's a year, it's coming, where you will use a dApp and you will barely notice. And that's where we've made it. And I think then a lot of useful things can be built on top of that.
I want to weigh in on this. So you said 6 months before, 6 months in the future. I feel like the ZK for compression was an idea for a long time, like clients. It's sort of in the scaling department, but it's like making something smaller. I think we've seen more implementations of that. What you talk about, at least the way I always understand, is like using ZK or other privacy tech in DeFi that actually allows for like either strategies to be really, really well masked, which is like, it's privacy, but it's like a very unique form of privacy, or where it actually kind of recreates the way that some of these things that you study work. Those are the things that seem very kind of new in that regard. I'm trying to think of it, like, because that's what you're looking for. You're thinking like ZK use cases, because I think you're talking more like ZK optimization, like it getting faster, but like you're saying what is possible, what's becoming possible past scalability.
But I think if users don't use it, it's not possible to have like how many users don't use dApps because they're so slow? Like I feel like usability and speed is a feature at this point, because it's like I'm giving you something so much faster. It's such a shift. And I understand what you're saying. That would just be my counterpoint, is that like I think it gets to the point where it makes a big difference.
I guess.
The bullshit. Oh, what's the bullshit? What's the most bullshit stuff in ZK? Ooh. Oh, that's so harsh.
Can I?
Oh. Wait, do you want to ask a question, or do you have some bullshit
Actually,
in ZK?
I would have another question, if it's okay. Regarding security, how relevant do you consider like upcoming quantum computing solutions for like ZK, especially SNARKs?
So, I think this is more of a question about like quantum computing in general. I guess maybe I can weigh in on this one a little bit because I did work in a quantum computing lab for my PhD, unfortunately.
Oh.
But
Yeah.
anyways, the answer is at the moment exactly not relevant. Maybe over the next 20 years, probably slightly relevant. But it's shocking the progress that we have made. It is also equally shocking how extremely unsophisticated we are at doing essentially anything that is currently like truly quantum. In fact, there's been a whole set of things about like quantum supremacy and whether that has even existed, and some people have claimed it has, and then someone goes and writes like a algorithm, runs it on a supercomputer for like 2 days, and it's like, congratulations, we emulated your results. And this happens so often that the taste in my tongue that it leaves, and I've seen it in lab settings as well, is very much, we're still 20 years away. What was said, 20 years ago, and so will continue. But then again, we might say that about whatever fusion or something, but maybe at some point it'll actually happen. So I think that's the highest level version. We can get more into the details, but that would be, again, that might require the level of sake. So.
One question: are you more confident in like lattice-based cryptography or hash-based SNARKs?
Oh, I actually don't know a lot about.
That's a real cryptography question.
Yeah, like actual cryptography. Unfortunately, I know very little.
All right. Any other? So I think that was a question. So thank you for the question. But so any other questions, comments? The way this always works, right? It's like the more opinionated, the more likely we're going to do a switch.
Oh, I
up.
do have a question. Is that, can I ask the question to like everyone? Is that a cool thing to do?
Oh,
am I voting it?
I
Oh,
guess so.
all right.
Wow.
This is like a different format.
You
all right.
are hacking my format.
Sorry.
Go for it.
Yeah. I mean, should we separate this is piggybacking on the previous question. Should we separate succinctness from like what we call zero knowledge, like as a whole? Like, is that a good thing to do? Like right now, we kind of, when we talk about zero knowledge, we mix in all of these things. Is that bad? Is that good? Is that, maybe Alex will have
one of the Alexes?
one question, one answer to
Do
this.
either
I don't
of you
know.
want to answer that?
Yeah, I was kind of thinking about the answer.
Oh, and I guess one side comment is, can we do better by being just succinct and not zero knowledge? Do you know if there's a gap there? Do we know that there's a gap there, or maybe not? Maybe.
Well, I think SNARKs are by default just as succinct, not really zero knowledge. You have to do extra steps to make SNARKs zero knowledge. You have to go beyond the domain field. So yeah, it totally makes sense to separate.
And I guess why don't we? Maybe as an additional.
So I'll give my take quickly. I think like
the
increasingly you're going to get systems that are tailored to the use case specifically. So I think where the way I like to think about zero knowledge systems is they conceal and they can compress, right? So compression is the succinctness piece. I think in like cases of rollups, right, you kind of, the zero knowledge is kind of an extra nice property that's maybe like, okay, you can verify that this is correct, but the privacy, the hiding piece isn't as important. And I think you're going to increase, because everyone is aiming for maximum performance, it's inevitably going to get to the point where you rip out everything that is not absolutely essential to the use case that you're serving. That's going to be the way that it goes. So I would predict that you see these systems start to branch off and just serve one or the other thing. So I think in some cases it could be good. It depends on the use case.
There was a question back there. Who had their hand up?
I think in
Way
Plunky
back
2, you
there,
can
there
actually
was
just
someone
specify
with
you
their
don't
hand
want
up.
zero knowledge in the configuration.
Does it actually help you though?
I think it's faster if you don't use it. Yeah.
Oh, it's actually
There it
like
is.
not just marginal.
Yeah. No, they actually say in their docs like, don't use it unless you need it.
Okay, that's actually I did not know this. All right.
Sorry, no, to add on to the point, I think it's actually in a way dangerous to not separate it, because I've heard people, founders actually, telling me they were doing this wonderful ZK app, and when I ask about the ZK, it's just because we are on this one ZK rollup. Like that was it. That was the whole ZK. So I think it is actually dangerous. And there's a third thing. It's not just the zero knowledge, the succinctness. There's also just the validity of what's going on. and you could, that's a third like axis that we have to sort of separate out.
I like that. I think you can come up. That sounds like opinionated.
You've been volunteered as
commentary.
tribute.
I think you're off. Thanks for being on the panel. Do you want to introduce yourself?
Yeah. Hi, I'm Nico, and I'm a cryptographer at Geometry.
We have a cryptographer here now, so we can ask all the cryptographer
Yeah, now you can ask the hard questions.
Alex is like, let me get out of here. Thanks for participating. Thank you for your awesome answers, questions. Okay, yeah, wait, you had a point, so I don't think that, do you want to ask a question?
No, it was just
actually?
a point.
Okay. Does anyone else have any questions, comments, thoughts about what we've talked about already here, thoughts about talks that have happened? Things that you think this group might be able to answer. We do need some questions or this doesn't work, so yes. Sorry to push, but it's actually what I need.
Okay, so this question has to do with nomenclature, if you will. So, as terms matter, do roll-ups, should you consider something a roll-up or an L2 if it has the ability on L1 for Ethereum to be able to immediately change that smart contract for upgradability? So should you, if they have the ability to stop those transactions from happening and from you being able to escape and force through transactions on L2, should they actually get that ability? I don't think they should, I guess is my opinion. They should have a separate classification based upon the ability to change their protocol to kind of freeze funds within their L2. So.
Yeah, from the way I see it, rollup should just use like execution off-chain and then use the main chain, the layer 1 for security. And that's how I see it. I don't know if you want to add anything.
I mean, yeah, I feel this gets into the is a whale a fish or a mammal kind of question. Like, you know, it goes both ways. Like, you know, one feels like a much more useful classification, but the other one feels much more technically adept. So I don't know. I mean, upgradability of smart contracts from the L2 itself seem, yeah, like it isn't. You know, maybe it's a useful distinction, but I would add it as like a trademark after L2 as opposed to like make a whole new nomenclature just for that.
If I can riff on the question, maybe for the panel that might be interesting is, there's a lot of discussion around where economic value will accrue in a world of L1s and L2s, right? So in your opinion, will the majority of the economic value accrue to the L1 upon which the L2 is built, or will it accrue to the L2, which could potentially serve multiple L1s?
Can you actually hold that? Because I want you to come up here.
Sorry.
And then can you ask that again? Yeah, please come up. Please come up.
No, you're right. You got to open it now. So.
Thank you for being on the panel, and welcome. Okay, you're gonna have to.
So I'll restate.
Actually, just
Quick
quickly introduce yourself, and then Alex, if you can just.
Hello, I'm Brian. I am a grantee with the Ethereum Foundation. So.
Thanks.
So
say that again.
the question restated. In your opinion, between the L1 and the L2, in the L1 and L2 paradigm, does most economic value accrue to the L1 upon which L2s are built? Does most of the economic value accrue to L2s, which could potentially process transactions for multiple L1s? So that's the question. Where does the economic value accrue? I see Guillermo squirming, which is why I asked this question.
Do you want me to answer? Sure. So I guess my opinion, I think as we move forward into the future and onboard like a ton of users, I think that we will see the value accrue to applications more than we will to the actual network. As much as I think the networks will actually continue to accrue value, I think that if we see true economic value of the real world come onto networks, I do think that they will hopefully surpass what's actually happening with the L1s. So I think L2s are going to take those applications and they're going to probably do like whole L2s that are like wrapped up in that one application. And I think they will see a ton of value accrue to them.
I actually think if it doesn't happen, if the applications don't get more valuable, then the project has failed.
Agreed.
Like the whole thing. Like it sort of has to.
Yeah.
It seems strange that we constantly just focus on Rails as the primary
But for the
economic
applications,
driver.
I mean, applications to be secure, there needs to be economic value at some level, right? Where you're settling, certainly like in a financial application, where it's settled, this is the idea of Ethereum, right? Is why it's secure is because the miners have this huge economic incentive to play by the rules. That's the whole premise. So I guess that's I agree. So great. First of all, great dodge of the question. The application should be the one. But
yeah, like the problem with this question is that, and I feel this way about a lot of weird economic questions, is that the kind of silly thing to say feels right, but it's probably totally wrong, and we'll have no idea until it actually happens. So you know, like we can talk about like weird supply and demand curves and being like, oh, like of course, like the thing that should, you know, that everything is running on should have at least as much value as the things that are running on it. And that feels like a totally sensible argument. But my suspicion is that it's completely wrong, and we'll have no idea why. And then someone will make some horrible model, you know, 5 years from now and be like, oh, of course, it was like obvious, and everyone should have known that was not the case. That the L1s would indeed accrue as much, or not accrue as much value as the L2s that are sitting on it, or something. So. I will dodge the question as well, but I will do it with a something that sounds intelligent, which is we have no idea, and in fact, I don't think we'll have an idea. But it's going to be really fun 5 years from now to be like, to write some paper that says, obviously, we should have known ahead of time that indeed, and it's going to be peer reviewed, and everyone's going to be like, oh, yeah, it was obvious, you know, reviewer 2 is going to tell you, sorry, I rejected it because this should have been stupid. You know, we all did know that back in, whatever, 2022 or something.
I have one final hope to have my question answered, but
no hope. I'm also going to dodge that. Like,
it's gone.
What do we mean by value, right? Is it just the gas fees that we're spending on different layers, or is it something we charge users for a service, other than just computation, right?
That's a good question.
And I don't know.
This panel is just an expert question dodging. Like, reframe the whole paradigm, like completely redirects us
to ask questions.
So I do want to. Oh, okay. So because there is another question, so I wasn't sure if we should wrap up now or after. So Alex,
yes.
I think you're up.
Oh, me?
You're taking Guillermo. Guillermo, if you don't mind being the mic person, and there's a question right there. Thank you, Guillermo. No, I think he had it. Yeah, he had a question.
Oh.
I didn't actually have a question, I had a comment. And the comment was not actually going to answer the question, it's also going to dodge the question.
Serious?
I think the value, if we get it right, will be actually for the users of these platforms, right? Like, ideally, if you can have like a system where you own the data and it's all privacy, so you have it and you can prove stuff about your information, then all of your information and that value goes back to you, right? And so actually a lot of these economic systems will eventually just kind of be very competitive in terms of like competition in terms of providing the service, whereas the users hold the key to all the data. Anyway, sorry, not answering your question.
So the TLDR is, like anyone who saw Ariel's talk earlier today is, I don't know.
Wait, Alex, why don't you answer the question?
What's my own answer?
Question. Yeah.
I think so my own answer is I think anything that supports applications that people will use or use it in the way that we think of Web3, wherein we have this economic incentive at the base layer, that will be what accrues value. I think the L1, L2 framing is wrong because I think there's a potential that things we think of as L2s today could serve multiple networks and then kind of over time transform and become some root layer. But I think there will always be this root of trust. And I think, again, in this paradigm which you've all accepted, where this game theory and the economic security model, I mean, if we don't have that economic security model, you don't really have a blockchain, in my opinion, right? I mean, I don't know. I mean, maybe that's a more fundamental question. Is a blockchain a blockchain without an economic security model? Plot twist.
Did you want to say anything more? Because I'm going to bring him back up.
No, I was going to say, like, I'm hearing dodging your own question. Like, these
dodged my own
L2s becoming L1s
okay,
and confusing.
You're up here. And thank you for being on the stage. And you've already been here, so you don't have to introduce yourself again. And I know there's a new question here,
yes.
Or comment, or dodge. Ball is what we're playing now, I guess. Okay.
Just a question. So I'm wondering, do you think like the succinctness of validity rollups or enshrined rollups is like the only end game for blockchains and distributed ledger technology, or like if you want to build 1 billion user application? Or can you actually build these applications on like Solana or Cosmos or other sort of scaling solutions?
No. I think the architecture for existing blockchains, of course, sharding will help, but you're just taking an architecture and making more of it, I think is not the right way to go personally. I think rollups are able, and if particularly, I can't remember who it was here, maybe it was you who were doing these like micro rollups.
Oh yeah. So with that Alio, every transaction you could think of, effectively.
Right, and I think like
model.
taking that data and doing these smaller rollups is actually the way to go, and that's something that we're looking to implement as well in our decentralized database, is to have the ability to basically split the data out, and because you've got a ZK proof, you can actually take data from one place and prove it in another place very easily, so you don't need to have this conglomerate global hash that just lives, right? You can actually, prove any piece of information anywhere else. And I think that's the future of scaling, and a lot more computation, because SNARKs will enable us to do all the computation, or a lot of the computation on the client side. Actually, what these blockchains will become is verification networks. And all of the data will be owned by you. There may be some level of data that exists on the network because you're not online all the time, your phone's not online all the time. But fundamentally, yes, we do need to re-architect the way that we do.
Yeah, I agree with that. I think that was very well said, and I think answering without dodging, I think the answer is yes. This is the model, and in fact, I think you've seen this this whole concept of rollups has kind of expanded to this concept of a modular blockchain, and really even at a more fundamental level, it's separating execution from state storage and separating all the different parts from each other, right? And this is one of the reasons why I think if you look at a lot of these SNARK-based systems, the key bottlenecks are often how big is the proof, right, for a decentralized, because a decentralized system, every node has to store the whole chain, right? So this is like how big is the proof, and is there an ability to recursively prove it down to be very small? But even if there is, that's fine for clients, but somewhere, someone has to store that state, right? So the state is one part of it, but then the execution, because you're proving off-chain, it actually opens up this amazing new dimension for applications, right? If you're not limited by the runtime of like an EVM, you could run a program for 50 years, spit a proof out at the end, and have the network verified. And that's something you can't do on Ethereum, right, today. That's like a fundamentally new model, which is cool. But the bottleneck becomes verification time. And this is one of the reasons why we talked a little bit earlier about SNARKs versus IPAs or STARKs. This is one of the reasons why, despite all these really new interesting proof systems, SNARKs have remained the tool of choice, because the verification time is cheap and the size of the proof is constant, despite no matter how large the computation grows.
Do you think, was that a question or a comment?
Me?
No, his. I was kind of in the middle. I wasn't sure. Are there, actually, the question here is, are there more questions, comments? Because if there aren't, then we'll wrap. But if there are, then we'll continue.
Can I just give someone time to think of another question? Maybe just add on to the end of that?
Sure. You guys
I think there's going to be an absolutely huge opportunity as well. If you think about how big an industry cloud computing is, I don't think people realize that, right? Cloud computing is massive. And if you took all of that computation that happens on the cloud and you put it onto the client, that's a lot of value now going to the client, and that's just going to be super interesting.
Okay, in that case, you are coming up. Let's get some new faces.
Yeah. You're coming up. Sorry. Get out of here.
No, thanks for coming up. Do you want to introduce yourself?
Hi, my name is Philip. I work as a research associate at a venture capital firm called Rockaway, based in Prague.
Cool. Welcome. Are there any other? Okay, there's a question over here.
Hey, can you hear me?
Yep.
A little bit of an opinionated question, but going back to the one that everyone dodged about where would value accrue. Curious to hear, do you think where value will accrue will change depending on your time scale? So 1 year out versus 3 years versus 5 years versus 10 years. Do you think 10 years from now it'll be application level, but 5 years it'll be L1, 3 years it'll be L2? Do we think that may be a better mental model? Do you think it will change over time like that?
I can hear you trying to put comment in there. But it's a good question.
I'll take a stab since I articulated the original dodged question, which I myself dodged. I think it will absolutely change. I think it'll change based on what parts of the system become less or more expensive over time. And there's a lot of factors there, right? So it's technological improvements. If you think about Moore's law, just Moore's law and what that's enabled over time for computing, that's made certain things that used to be extremely expensive commodities that everyone just assumes are free now, right? And I think you could, the same thing with storage, right? As we've all gotten used to having, terabytes, on our laptops around, which is like before like terabytes were, that concept was extremely expensive. So I think as the hardware kind of matures, I think different things are going to be viewed as cheaper. But of course there's a market. I think the market will also determine for different applications, like whether storage or like state growth or maintaining state with some reasonable degree of retrieval latency is more important than executing something. So I think it depends on the time scale, but also it depends on the application.
Can I add something on that?
Before you do that, I want to switch out.
Okay.
So, do you want to come up? I feel like there's more questions. I saw some other hands, so that's good. Okay. Actually, wait. He's going to introduce himself. You have to wait for him to get here.
Hey guys, I'm Matt. I'm building private multisigs on Aztec and Alio.
Cool.
Yeah, so I actually think the economic model is going to change completely. Like today, we think about companies in a very different way, and I think the future of Web3 companies is going to be completely different. So today, as a company, you build a product, for example, and then you get monthly or yearly annual profits from that, and that goes basically back to the shareholders who put in some money at the beginning. And I think actually what we're seeing with DAOs that have been created and around protocols is actually you take the value at the beginning, so you tie the value proposition of your protocol to your coin, and so the more usage your protocol gets, the more the coin goes up. So all your initial investors get returned once in a big amount, a big chunk of money, they get returned. And so that's great, they're done. And then we can use the rest of the kind of economic system can actually balance itself and not be as much for profit anymore. So
I mean, this is the dream.
Yeah, I mean, that's the dream.
I think there's a lot of other stuff happening that pushes those prices around than utility, if you look at the top 10.
And actually if you look at most protocols, there's no reason why the price of the coin should go up based on what's happening on the protocol. And you can build that in. There is economic systems to build that in. And the Graph is one of the people who are doing it right, and they actually have a system whereby it's called the utility token model, and you can basically tie, using a kind of taxi medallion type methodology, you can basically say, okay, if you want to make money on our platform, you have to stake some amount of money in, and that makes it work.
Mm-hmm. Any other thoughts, questions, comments? We're kind of at time. Maybe one last one?
I did have one comment on that.
Okay, yeah, or we take it from here. Go for it.
My opinion is actually more in Guille's camp about you never really know, and it's going to be a complete up in the air thing that we'll look back on and be like, oh, that made sense. But I do think it'll be, like, there's so many different ways that it can go that wave function will collapse, and everyone will be like, oh, of course it went down that path. But, like, Cisco was, during the initial internet build out, was the most valuable company, worth $500 billion at one point, that everyone just projected that, oh, that one's going to be the one and they're going to charge the most, and that wave function never collapsed until it did. And then it went down 80%. And Facebook became the most.
I think that's a good point to end this on. We don't know. We don't know anything. Zero knowledge. All right. Thanks, everyone, for the Park Bench panel. It was a lot of fun. I believe we have another slide we can maybe put up, which is our last slide. I don't know if you have this. Maybe you do, maybe you don't. I don't know if you do. Yes. Okay, so we are now going downstairs. There is drinks. There are drinks. I can say that correctly. And Least Authority has a special kind of gift drink that you should definitely check out. They have written, there's like a textbook called the Moon Math Manual. I don't know if you've heard of it. It was in the Gitcoin rounds. I think I've mentioned it on the show in the sponsorship spots. But yeah, you should go check it out because it's connected to that. This is like a ZK tech textbook that we've been waiting for. That's at least like a first, they're starting to come out. It's not the only one, but it's really, really cool that they're doing that. So please enjoy the drinks, and thank you all again for coming to the ZK Summit 8. See you at the next one, I guess, right?